which product to buy, or recommendation engines, right? One of the examples is this Google Compose that you can see it is auto predicting what next you're trying to say, right? Or if I take it, see, these are, let's say, day-to-day things that you are doing, right? I can tell you some things which are even more complex, right? Some things which are even more complex, like, let's say, the videos from Boston Dynamics. How many of you have heard of Boston Dynamics? So Boston Dynamics is a company which was made, let's say, which is a US-based company, and they majorly deal in they deal in robotics. It is not here right now in, let's say, US and in Europe and in India. It's not there, but China has already started something called as, let's say, facial recognition based payment systems. So I know you all are, let's say, familiar with, let's say, PayPal's scheme, right? Or you're familiar with Venmo, or you're familiar with the what do you have, Paytm, right? You're familiar with these terms. But in China, what is happening, you don't need to have, let's say, any kind of a biometric information or a pin based mechanism. You can just use your, let's say, face. It detects your face and your payment is done, right? So I don't see. Oh yes. In Beijing, they have started this new thing that if you're trying to do a jaywalk on the road, right, they would, let's say, take through the image recognition system. They can understand that you did a jaywalk, and they will post your image for the one whole day, and they'll humiliate publicly to you. So China is doing, let's say, these kinds of let's say, steps there to make sure that people don't misguide them, or, let's say, I mean, they're reducing, let's say, forces there, and they're putting all these things. I know Alibaba has also implemented this thing where when they call their employees, right now, when you go to a firm, you have some kind of a registration system, right? That you will either, let's say, have your ID card shown, or you will have a biometric that you press your finger and the gate opens up for you. They give you the entry, right? In Baidu's session. Baidu is what? Baidu is the Google of China. You can think of it like this. So because Google is not allowed in China, so they have built their own, let's say, search network called as Baidu. So Baidu's offices, and when the employees goes in, they don't have any kind of a ID card, or they don't have any kind of a biometric mechanism to do this thing. They just take your face recognition, done. Entry is done. Can I give you one more example? Let's say, I know some of you will relate with me. You will see that the moment you enter any kind of a retail store, you will see the most expensive products in front of you, like TVs, right? They'll put television sets, they'll put, let's say, MacBooks, they'll put these laptops, fancy laptops, and all those things. Why do they do this thing? Is because they want to psychologically, let's say, hype up the amount that you are coming here to spend. Let's say you made a mind that today I'm going to do a monthly shopping, and my budget is, let's say, $1,000. Now, the moment you enter and you see your favorite thing, right? Let's say this favorite let's say PlayStation is there, or your Xbox 5 is there. You see the price is somewhere around, let's say, I'm just quoting it, right? Please don't take me. Let's say it is 9,000. Suddenly in your mind, this 9,000 has become very high. You'll say, oh, no, 9,000 very high. Let's go ahead. And when the next product that you see, which is, let's say, only for 6,500, this automatically becomes very cheap for you, because 9,000 has been set as the highest bar for you. And now you say, okay, 6,500 is still cheap. I should buy this thing. So that's all. Let's say these kinds of strategical decisions are being taken through machine learning and deep learning. What we do is we trace that how a human or customer, let's say, is traversing inside the ground, how much time are they spending in buying groceries. I don't know if you have noticed this or not. When you buy groceries, you spend the minimum time. But when you buy cosmetics, you take the maximum time. Do you agree or not? Some of you will not agree with me, but next time when you go there, right, try to see this thing. Whenever you will buy groceries, you will quickly buy them. You will say, okay, I want this, kept it, that's it. But when you buy something cosmetic, you'll compare things, right? You'll compare this one is good or not, that you'll take 10,000 decisions. You'll call your friends and family and try to figure this out. These all things, make this kind of decision that where is the most, let's say, ideal position to put the ad. And I did this with my client, and we figured out that place which captures the maximum. How many of you have heard of Amazon Go? So this is this kind of a store there, and it is a humanless store. There is no human. You just go inside. These are, let's say, these are entry counters. You show them the app, and then you roam inside. You pick up whatever you want to do. You put it inside your bag or wherever you want to put it. You just put it, and then you go out. Nobody stops you. Nobody does, let's say, anything to you. Just walk in and walk out. So you would be thinking like, what? Yes, exactly. That's the case. So Amazon Go is this new, let's say, kind of a state of the art, retail stores that they have made, where they say that it's a humanless thing. You don't want any human to, let's say, supervise you or do, let's say, billing for you. You just go there. Amazon Go now, let's say, know that what you have picked up and from where you have picked up and what quantity do you have picked up. It knows everything. It knows everything in and out, and it can actually calculate this thing whenever you go out. It checks you out, and then you see a bill that is there on your Amazon app. That is what is called as a use of full-fledged deep learning, machine learning, sound-based systems, image-based systems, and whatnot. Right? So in fashion industry, the machine learning is coming out, deep learning is coming out at a very high pace. Now, how it is coming? So let's say if you saw this, let's say I worked for another at my client. I worked for this Southeast Asian client. They gave me a very interesting problem. They're saying that what people are doing is people are there in COVID and they are inside their houses. So their interest to buy new products is decreasing. I said, yes, that's true. And you know what is happening? People are seeing other people only on televisions or let's say on Instagram or let's say on some kind of other social media network. I said, yes, that's true. And what these people are doing is they're, let's say, you know they don't know that how on which store to go and where to buy these clothes that they saw this influencer wearing. So I said, why can't they just type in, right? So that they said exactly this is what we're doing right now. That whenever a customer let's say they see this beautiful, let's say, influencer and she's wearing something, right? So what they'll do, they'll come to our platform and they'll try to type that thing. Let's say that she was wearing this blue ribbed denim jeans. Just take an example. So they would, let's say, come and write down all these things, ripped denim jeans, and it is not as expected as she wants. She wanted exactly like what this influencer was wearing. So we said, yes, this is a true topic. Or let's say if your favorite, let's say, K-pop star is wearing this blue checked, let's say, shirt. I know that K-pop don't wear checks, but just taking an example. So people just go and write down these things and they never get the product that they are really looking out for. Correct? This might have happened to you at your store also. Whenever you go to your, let's say, your stores at Levi's or let's say Zara, you go there and you try to describe them. You don't get what you are actually thinking, right? They'll get something totally opposite of what you're saying. So we made a system there, that if you see any kind of an influencer or anybody, let's by influencer, well, let's say anybody, if you saw that person wearing this thing, click a photo, upload that photo on our, let's say, e-commerce website, and we will try to bring the nearest, let's say, cloth that we have according to it. People were so happy. People were so happy that they can get this kind of a feature. Once they come on the platform, they, let's say, snap a photo, they upload the photo, and the nearest looking, because visually, see, how do you wear clothes? You visually see the clothes, you don't hear the clothes, right? You see the clothes. So it was now becoming very easy for our clients to, let customers to understand this thing, and we could, let's say, do something called as image search. So right now you search for something on Google and then you say what you type a query, right? Google query, correct? You write it like this. Now, if I say to you like how Google also does, this is the, let's say, the platform, and in this thing you can upload an image, and it will try to, let's say, bring the exact image there. Same thing we did in our platform also, and customers were really happy. So these are, let's say, some use cases that are there in deep learning and machine learning, right? Now let's come to the next topic, and I know most of you might have this question. What is this? I have heard these 10 different terms there: machine learning, deep learning, data science, artificial intelligence. What are all these terms? So the first word that you might have, let's say, I just open up a board. Sorry. www just sold out to me though. That thing. It's like super wonderful if you're using to. Here it is. So give me 1 second. I'll just stop annotation. Here it is, and this thing and this thing. Okay. So yes, we are talking about this thing called as, there are four terms. Let me write it down. The first one is called as data science. The second one is called as machine learning. The third one is called as deep learning. And the fourth one is called as AI. NLP. Okay, very good. Any other term? Reinforcement learning. Okay. Any other term? Computer vision. Yeah, computer vision. So one of my friends is vision. One of my friends is computer vision. I have written CV there. Okay. Neural networks. Okay. Neural networks. Okay. Any other term? Or NN. Okay. Let's now. Okay. So now you are going into details now, right? Okay. So let's talk about the first things, and the first thing is data science. Now, what do you think? What is data science? Data science is made up of two words called as any kind of a science that is applied on data. That is called as data science to generate insights. Now, let's say I have a very small, let's say store, a very small store, and I'm selling, let's say, game DVDs. And let's say you are my accountant. And if I ask you a very simple question that which DVD are we selling the most? That is also data science. As simple as this. As compared to if I ask you that what is the statistical analysis which says that how our game CDs are being sold as compared to, let's say, weather, you'll say what? Yes. So you might not think, but let's say games have to do something with weather also, right? So think of data science as anything which is generating insights, right? Any kind of, let's say, generating insights. One of my friends says how it is different from data analyst. See, data analyst is a job, right? Data analyst is a job which does this thing. So data science, let's say, is what? So let's come back. See, let's come back. Let's come back to data science only. Data science is what? Data science is any kind of a science that is applied to generate insights. Generate insights is a very important term there, right? You are doing some kind of mathematics, some kind of statistics, some kind of a probability. You might do anything, but that thing is to generate insights. And that insights can help you generate more revenue, or let's say make strategic decisions. Correct? Now, this is not new. You might think that this is, let's say, okay, something that we have learned only in, let's say, the past 10 years. No, we have been doing this since for ages. Data science is something that we have been doing this for ages. Next thing comes that is called as machine learning. Now, the problem with the data science was that it was generating insights. Very good. But can it help me advance, and can it help me predict my future also? You say, what? I say yes. See, you are my accountant, right? I just asked you that which game are we selling the most. Now, if you could tell me in the month of May, how many DVDs can we sell? So I would, let's say, order them in advance. Correct? Can you predict that what would be my sales for May? Now you'll be thinking, what? Can we predict the next future also? You will think that am I the god there? No, you are not become a god there. The only question is that if, let me ask you, let's say if let's say there's a certain graph of our DVD that we are selling, let's say in last year, January, Feb, March, April, and then blah blah blah. Let's say this graph was like this, and then down, then it goes up, 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 and then it goes down. It again goes up, it goes down, and then it's going up, up, up. What is the next thing that is going to happen? Will it go down or will it go up? This will go down. This will go down only. But did you become a god when you said that it is going to go down. No, what you did exactly. One of my friends says we try to decode the pattern. Exactly, that's a pattern that it goes a small hike, then a big hike, then a small hike, big hike. It will again take a small hike, then again a big hike. That's a simple pattern that you recognized, and you're trying to predict the next outcome. That is what exactly your, let's say, machine learning also does. Based on the patterns inside the data, based on the patterns. See, first of all, find patterns and predict. That is the thing of machine learning. So do you know how did we game up, how did we, let's say, step up our game? So in data science, what we were doing, we were just generating insights. Now with machine learning, what we have done, we are finding out patterns, and we are trying to find out, let's say, predict the patterns, correct? Now, machine learning has a certain thing. It says that I am very good at tabular data. What is tabular data? Tabular data means any kind of a data which is captured in the CSV, which can be, let's say, represented into rows and columns. Correct? Now, it works very well at machine learning. Machine learning works very well at tabular data. That was it. But let me ask you a question. Is all the data always in tabular format? You will say yes, stocks, stock market, sales, finance, everything is in tabular only. Then which data is there which is not in tabular format? Tell me one thing. If you are a library, you are a manufacturing, images, videos, speech, correct? Text, they cannot be written in, let's say, in a cells and rows, right? So what happened was there was a need, suddenly there was a need of, let's say, kind of a machine learning which can work on these images, videos, speech, sounds, text. So that is why it was called as deep learning. And this person, is doing the same thing, find the patterns and predict. But I will write down again, find pattern and predict. And the second thing is they are good at what? Good in cognitive data. This kind of data is called as cognitive data. What is cognitive data? Images, videos, speeches, text. Now, how does deep learning do all these things? See, machine learning is more of a mathematical approach, right? It is still like a mathematical approach. Deep learning is more of a human approach. It is more of a human approach. How does a small kid understands that this is a phone, this is a mouse, this is a laptop, this is a screen? How does this kid know all these things? Because the kid is seeing this from a very long time, right? They're seeing this for a very long time. They are seeing that people use this thing to achieve something, right? The kid is watching this thing for a very long time. That's exactly what we do in deep learning. We show some samples, and it exactly tries to mimic how a brain should have done that same thing, right? That is why it is called as neural network also, right? It is not called as it uses a neural network system. Deep learning algorithms, they use something called as neural network system. Now, what is a neural network system? You can think of it, let's say for today, you can think of it as a system which tries to replicate a human brain, the learning of a human brain. Do you understand? Data sciences to generate data, machine learning to predict something, but only on tabular data, generally on tabular data. And what is AI? What is deep learning? Deep learning is, let's say, again, finding patterns and predicting, but on cognitive data by using an approach how human thinks, and that is neural networks. Now, one of my friends was asking what is ANN? ANN means artificial neural networks. We as a human really have neural networks there. Those of you who are from medical background might know this kind of a structure. And pardon me for my bad drawing, but you might have seen this kind of a structure in your biology. I don't know biology or what chapter you might have seen this thing. This thing is called as the neuron that is present inside your body. It is connected from your brain to every moving part of your body, right? So this whole is not called as dendrite. Only the lower part is called as dendrite. So only this part is called as dendrite. This part is called as dendrite. This part is called as axons. This part is called as nucleus. And this particular whole thing is called as the neuron. And there are multiples of multiple like this, and they're connected from your brain. That's exactly how, let's say, a human also thinks, and that's exactly it works in humans, and that's exactly how we try to mimic this thing in deep learning. So you can think of deep learning and machine learning. What is the difference? That in deep learning, we learn how a student learns. And we keep on showing the sample again and again, again and again, again and again, and we try to build a memory inside them. Correct? Now then, Shivam, what is this called as AI? Artificial intelligence. Artificial intelligence is the final product that comes out. Now, I showed you that final thing, right? That Boston Dynamics thing. Now that Boston Dynamics is a final product. Do you think it is just made up of, let's say, machine learning or deep learning? No, it was using all the things. It was using, let's say, data science. It was using ML. It was using deep learning. It was using some standard static rules also, right? When all these things, they come together to make a final product, that product is called as artificially intelligent product. Correct? Now let's talk about, let's say, I said a word called as cognitive data. I said a word here called as cognitive data. Now this cognitive data can be, let's say, images. It can be videos. It can be speech. And it can be text. When you are dealing with images and videos, this is called as computer vision. You see something that is called as vision, but if you see it through a computer, that is called as computer vision, right? What is, sorry, I wrote it in LP, I should have written it text, sorry. This thing is called as text. Now text is called as NLP, natural language processing. Simple terms, natural language processing. So those of you who are confused by, let's say, NLP and computer vision, don't worry about it. Okay.
Supervised learning, of course, is the form of learning where you kind of provide data. Along with the data, you also guide the algorithm towards a specific direction, and say that, hey, look, this is an apple, this is an apple, and this is an apple. You're basically saying, think of a structured form of learning, a supervised form of learning. So in this particular case, whenever you have labeled information, such kind of data, or when your analysis is sort of, or when your learning process is sort of directed in a specific fashion, in such cases we call it a supervised learning problem.
Unsupervised learning. Now see here, whenever I say that, you are going to do machine learning, you always think of data, right? And data has two parts. One is, let's say, input, and the other is output, correct? Let's say this one becomes your input, this one becomes your output. Now, one of the most classical examples of, let's say, input output is, let's say, if you want to calculate the price of a house, if you calculate the price of a house, you want multiple features, like what is the square feet area of the house, how many floors do you have in the house, how many parking areas, do you have a lawn or not, right? All those things, they become your input. They become your what? They become your input. And based on these inputs, locality, multiple things. Based on these inputs, you will calculate a output. This is what you all have studied, let's say, in all of your life, that this is what machine learning is, that you will train your model to understand this pattern between the inputs, input and output, understand the pattern between input and output. And at one point when the model is trained, we will only give the model input only, and it will return output to us. Correct? This is what we all have learned. Before even that, I say supervised learning, obviously not guide, right? Supervised learning. So what was the, in training, what do you do? In training, you would have, let's say, a pair of input and output, not a pair, but let's say data of input output. You will apply some kind of algorithm there, right? And in return, the algorithm will return you out what? It will return you a model, correct? And in the prediction phase, what is going to happen? In the prediction phase, you will only give your input to this model, and the model will return you what? Output, correct? This was supervised learning. But now the world is not such a good place. You will not have, let's say, input and output every time. There are certain instances where you will not have input there. And one of the cases is like, let's say, if you are how many of you have shopped on Amazon, or let's say how many of you have gone to Netflix to watch a movie? Almost everybody, right? Now whenever you go there, they already recommend you something, that you can start with this, let's say you can start with that, you can start with this. Now how do they know all these things? I mean, it makes sense for people who are, let's say, watching Netflix for a very long time. So now they know, they have the input for you. They know that, okay, this person is watching a lot of, let's say, humor. He's also watching a horror. So next time we can, let's say, give him a horror humor kind of thing, right? This kind of thing. But let's say if you're a very fresh new user, you just made your account right now, how can they tell you to watch this particular movie? What is the basis for that? Have you ever thought for this thing? Certain times you only have input, you don't have the output to tell. Netflix, because you just joined the platform of Netflix just right now. Netflix does not know what is your flavor. Exactly. One of my friends says there is no historical data for the end user. I totally agree. There is no historical data. Then how does Netflix know that you can watch this or that?
Just a quick info, guys. Test your knowledge of AI by answering this question. Which of the following is not a stage of AI? A. Predictive analytics. B. Diagnostic analytics. C. Cognitive analytics. D. All of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
General recommendation. I would say we're not living in now 90s where general recommendation will work using location. Let's say right now we are in United States of America. So what will you recommend? We all are living in United States of America. So what they can do, right? But you all are exactly somewhat correct. You all are somewhat correct. Now, rather than, let's say, going there, what they will do is they will make a user table. I'll tell you. They will make a user table. They will have, let's say, that what is your age, what is your gender. One of my friends says location. So Netflix asks certain questions to you when you make your account, right? Your age bracket, your gender, your location, and then certain data that comes out of your, let's say, cookies from the browser. Some data that comes from other tracking websites. They get all these data from you. But fun fact is they still don't know that what kind of a, let's say, genre do you like on movies. They still don't know this thing. What they'll do is now, my friends, and listen to me just for 5 minutes carefully, right? They already have, let's say, tens and thousands of data already in the database, and they know everything about them. They will say, go in the database and take out all the users out of it, right? Take out all the users out of it and fill this table. This you can do very clearly. Yes, you will say that we have all our historical users, and I can bring, let's say, the age, gender, and location from them. You will say very good. Now you will put your new user data info also. New user info. In unsupervised learning, what is there? There is only input. There is only input. There is no output. We give this input to a algorithm, and this algorithm in return tell you that what in which cluster does it forms. What? You guys are like, what is happening? I don't understand this thing. Let's now understand this thing, this training phase into this graphical format. So let's say you are Netflix and a new user has just now joined in. So what you will do, you will ask your engineer that give me all the information about the previous, let's say, um, you know users. So you will say, sir, some users are here. Let's say you will draw these users. Some users will be here. Some users will be here.
Now, when you draw this based on these three features, age, gender, and location, when you draw a new, let's say, when you draw the new user, let's say the new user is somewhere here, this orange one, which cluster do you think he belongs to? Or which group do you think he belongs to? Does he belongs to C1 group, C2 group, or C3 group? What do you think? C1, why? Why do you all think that this particular user, this C1 user should join, sorry, this user's closest distance? Exactly, because this particular new user is very close to this C1, let's say, cluster group. Okay, let's come back to our problem now. What was our problem? Our problem is that we have, let's say, all these details about the historical, let's say, users. There is this new user info there. We draw this kind of, let's say, map, and we say that, this new user is very close to this C1 group. Now, what can we do with this thing? We have figured out that, let's say, it is very close to C1 and blah, 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 and all these things. What is this going to help us? This thing actually tells us that if we are close to the C1 group, now because the C1 group is a historical and we know everything about these users, tell us that what genre they are very interested in. What genre they are, let's say, what genre they are very interested in. So let's say this particular is, let's say, about drama and action. So what we'll do, we will also recommend this particular user drama and action. You understand now the whole, let's say, scheme of this thing? That whenever you join a Netflix, right, what is happening? You are being compared, you yourself, your profile is being compared with tens and millions of other users. And then you are actually, let's say, drawn on a graph, and then we see that which group do you really belong to. Now let's apply the same thing into our offices also, right? Whenever you join an office, or whenever you join a college or a school, you all make a group. You all have a, let's say, you do not talk to everybody in the class, right? You just talk to selected people only. Why? Because your wavelength, your thinking, your psychological, let's say, mapping is very close to these people. That's exactly what Netflix and, let's say, Amazon, they also want to do, is they want to find, let's say, that they what they want to do is that, let's say, they have this customer base of tens and millions of, let's say, people. They want to cluster them together, that these people are thinking alike, these people are thinking alike, these people are thinking alike, and they make these clusters of people. Now, whenever a new person joins us, their job is just to check that which cluster does it belongs to, very close. And we now understand that what is unsupervised learning, correct?
The more popular or the more advanced form of learning is what is called as reinforcement learning. And reinforcement learning is basically, in a lot of ways, how a human being actually learns. I mean, the kind of environment that we are set up, that's what is essentially called as a reinforcement learning. So in the case of a reinforcement learning, you might not really have a lot of historical information. You might not have a lot of historical data to learn from, but what you would have is, you essentially have an environment. Like, for example, in this case, take the example of this particular road. And say there is a car, right? The car has no knowledge about this whole environment. The car has no knowledge about this whole environment. And all that it knows is there's a road and I'll have to go through that road. So what happens is that the agent observes, or the car observes, it goes ahead, it decides, okay, let me go ahead, let me walk straight. So it selects an action. The action is, let's say, let me go ahead. So the machine goes, or the car goes ahead, and it crashes into this particular board. The moment it crashes into the board, then the environment is going to come back and say that, hey, look, you made an incorrect decision, so I'm going to deduct 50 points from you. So now what happens is, now the system learns that, oh, okay, so when I crash into this particular board, I'm going to lose 50 points. That's not a good outcome. So then what the agent is then going to do is, the agent is going to then try another outcome. So the agent will go, instead of crashing, it takes a right. The agent goes ahead, instead of crashing into the system, it takes a right. The moment it takes a right, because it hasn't crashed, it gets a 50 point. It gets plus 50 points. That way, you've reinforced the fact to the system that, hey, look, when you don't crash, you're going to get more points. When you crash, you're going to lose points. So you're reinforcing a certain kind of behavior into the system. So to begin with, you might not have a lot of information, but as you keep going along, You've designed your system in such a way, you've designed your environment in such a way that it acts in a certain fashion whenever a certain kind of outcome, whenever a certain kind of action is taken. So yeah, like for example, how you would play a game of chess. Think of how you would play a game of chess. So at the beginning, you might not be a pro at it. So you start playing the game of chess. You make a move, and then you suddenly realize that, oh look, I've made an incorrect move and I lost my queen. So from the next time you learn that that's an incorrect move. So you try something else. Then again you lose another piece of yours, and then you try something else. So there are a bunch of options that you have, and out of those options you try out different options, and then from there you explore that certain options will lead a positive outcome and certain options will lead into a negative outcome. So if you're optimizing for a positive outcome, you will always try to choose options that will lead you towards a positive outcome. So by what you're doing with reinforcement learning is you're essentially designing a particular environment, and then asking your car or asking your player to automatically try and learn from that particular environment. That's the beauty about reinforcement learning. You don't need any historical information, but you're essentially designing a framework through which the machine in itself can explore various things. The process is going to be slow, but surely you will always get to a certain point where your systems start to perform really very well. Classic examples are all gaming systems, right? Your Microsoft recently came up with an algorithm that was able to crack Pac-Man. Um, Pac-Man is one of the most silliest games that you and I can ever think of. But imagine how difficult it must have been to actually train an algorithm that can really go through all of that and capture all those grains without losing. And that has happened by training a reinforcement learning system for a couple of days, a couple of months, and after that, it kind of got better at it. So yeah. So I hope that kind of clarifies what supervised, unsupervised, and reinforcement learning is. A key point that you have to understand is with supervised and unsupervised learning, you have historical data. But with reinforcement learning, you might not have historical information. You let the system learn as it goes. Yeah, use case self-driving cars. Yeah, I mean, yeah, their testing frameworks are essentially reinforcement learning algorithms. They get better by the day. Cool. So broadly put, these are a bunch of ML algorithms. A lot of folks must have already tried a few of these. You must have learned a few of these already. Like for example, in the supervised learning bucket, you must have come across regression, decision tree algorithms, random forest algorithms, and so on. Similar, I mean, just like another classification algorithms. In the unsupervised learning side of things, you must have come across clustering techniques, association analysis, Markov models, and whatnot. What we are going to learn is we're essentially going to learn similar to your supervised and unsupervised learning techniques. We're also going to learn right now, of course, reinforcement learning. We haven't really learned much on reinforcement learning. That would require another form of learning altogether. We will get there when we have to. But right now, in the focus is essentially going to be just like how you've learned regression techniques and classification techniques. Under the classification and regression techniques, we're also going to learn another form of deep learning technique based on neural networks. We'll learn neural networks and we'll essentially progress from there. Similarly, using the deep learning frameworks, you can also actually solve unsupervised learning problems, and we'll talk about it. Basically, under the supervised and the unsupervised learning bucket, we're essentially going to learn another set of techniques. Limitations of machine learning. The limitations of machine learning, of course, are that machine learning algorithms require large volumes of data. Yeah, lack of creativity, because machine learning algorithms, of course, will require, um, you know, they're not really complex algorithms. Yeah, traditional ML algorithms are not very complex algorithms, so they don't have a lot of complex learning approaches. But of course, the idea, of course, is that you would want to enhance these traditional machine learning techniques using complex techniques like deep learning that we're going to learn in the next few hours. One of the most popular applications of deep learning is your translation. machine translation, and image recognition, object detection, machine translation, machine comprehension, speech to text translation. All these are all deep learning applications. And I think that's just, it's just brilliant the way deep learning has changed the way people have started looking at unstructured data, and how people have started being able to were able to actually extract more and more information out of unstructured data. Okay, so let's talk a little about how deep learning models actually work. Firstly, the concept of a deep learning models, broadly speaking, what happens is that there are, broadly speaking, we have three types of layers. We have something called as an input layer, hidden layer, and an output layer. The input layer is where,
Okay, guys, a quick info. If you're looking for an end to end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So, the details are available in the description box below.
information or data is going to be passed into. So that's basically the layer where uh, all raw information is being sent into. What happens in the hidden layer is a lot of features about the data is getting captured, and in the output layer, what happens is we are going to learn about, if the person is a male or a female, or if there is a dog or a cat given a particular image. Doing some kind of a classification can happen as an output. Like, for example, if you look at this image, the input layers is where you pass raw images, just like how you see here. In the hidden layers, what happens is certain we learn certain key characteristics about that particular image. And from various, as you move from one hidden layer to another hidden layer, the kind of features that we capture are going to be very different. The early layers are going to capture very raw features. The later on, the layers, the deeper layers are going to capture more and more complex features. But with the help of these features, what we can then do is we can basically, instead of actually remembering the image in itself, the layers internally will capture more and more complex patterns. So using these layers, what we can do is we can perform some kind of classification algorithms or some kind of regression algorithms and so on. We can apply regression or classification techniques. The point that you have to understand is, the more the number of layers, the more complex the algorithm is. The more the number of layers, the more smarter the algorithm becomes. You also have to understand that the reason why we call it a deep neural network is because at times the number of hidden layers can go up to 20 and 30, 50 at times as well. And what that means is, when you have those many number of hidden layers, or those many number of layers in between, uh, the algorithm is going to be super complex, which means that you end up learning a lot more complexity with you end up extracting a lot more information from the data. So because we have more number of layers, we call it deep neural networks. That's where the term deep learning came from. The ability to train deeper and deeper algorithms is what deep learning is all about. Deeper and deeper neural networks is what deep learning is all about. So if you look at it, a neural network basically is a computing model. Think of a computing model whose this is essentially how a neuron in our brain works. Think of each hidden node as a neuron in our brain. So if you think of it, our human brain is made up of a lot of neurons, and it's not independent neurons. These neurons are basically entangled with each other. These neurons are sort of tied to each other, right? They all actually work together. There's a network of neurons that is available in our human brain, and the hidden nodes is essentially trying to replicate that network of neurons. Think of each hidden node as a neuron, and these neurons are basically trying to uh, they're basically the hidden nodes, or the hidden layer in the case of a neural network, is basically trying to replicate that kind of a behavior. Let's actually dig into how does a neural network really work. This is essentially how a neural network looks like, right? So you have a simple neural network basically looks like this. So you have an input layer, and from input layer, some kind of information is being passed into the input layer. And this, what is happening here is that this information is then passed into the hidden nodes, and some kind of computation happens here, and that information is again passed back onto the output layer, and an output is being generated, right? So what we would want to understand firstly is what is the kind of computation that is happening inside here. And we'll want to learn what is the exact computation that's happening inside the hidden layer, and what is the data that's flowing inside into through this particular input layer. We want to learn that. So let's dig into it. As I said, the most fundamental element of our human brain is what is called as a neuron. A neuron basically consists of these elements. A neuron basically consists of um, you see these I think I'm going to talk about the most important parts, which is of course these dendrites. The dendrites um, are these branches like things which are kind of protruding out of the neuron. This part is basically what is referred to as all these branches like things, stems like stuff that is sort of protruding outside are what is called as dendrites. And these dendrites are responsible for receiving and sending messages. Right? These dendrites are basically responsible for receiving and sending messages from this neuron to another neuron. Okay. This is your axon. The axon is think of just axon as an impulse carrying uh, part. The axon really has no real importance, at least in the context of our scenario. I mean, it has a lot of importance in the biological sense, but in our case, it doesn't really have a lot of importance. But the axon, or also referred to as the synapse, the points that you see here, the root-like things that you see there, that is basically called as a synapse. What that synapse does is that synapse basically goes and ties itself to the dendrites of another neuron. So essentially what happens is you have a neuron here and you have the dendrites. These dendrites are basically receiving information from other from synapses of other neurons. So there could be another neuron over here, and its synapse is basically connected to this dendrite. Similarly, the synapse of this particular neuron is connected to the dendrites of another neuron. So that way, if you think of it, there is a huge network that is basically getting created. And think of a few million neurons and the complex network that your brain would end up your brain would end up creating, right? What we are trying to replicate with the help of our neural networks is that complex structure of our neurons. There is an input and there is an output, and between your inputs and your outputs is a complex network, and that complex network basically takes inputs from everywhere and gives outputs to everywhere else. So if you see, even here, look at the kind of network that it has, look at the kind of dendrites that it has. It can take inputs from so many places and it could give outputs to so many different places. So what we are trying to replicate with this particular architecture over here is that we're trying to say that, hey, I have a few inputs, I'm going to receive inputs from everywhere, and I'm going to send outputs of that particular neuron. Whatever is going to come in, I'm going to do something inside this and I'm going to send it out to an output layer. Okay, this is the biological neuron. Wonderful. Let's try to overlay this on top of a artificial neuron. What happens to an artificial neuron? The artificial neuron is essentially this. These are basically your dendrites, your input layers. If you see, there are some inputs which are coming into this particular node. Think of this as a neuron. And what happens is there is an input coming in, lot of inputs which are coming in. There's some kind of an aggregation that happens here, some kind of computation that happens here, and there is an output. There is some kind of a function that is applied and there is an output generated. Okay, there are inputs, there is some aggregation, and there's an output. This whole thing is basically one of this purple, uh, these purple circles that you see here. There are inputs, there is a computation, and there's an output. There is an input, there's computation, and there's an output. So let me give you a small insight into what do I exactly mean by a hidden layer. So here we go. In your introduction to one of your first few deep learning models, or let's say your first perceptron model, we call it as a perceptron model, but we'll learn more about it. So let's take, for example, a traditional machine learning problem.
Just a quick info, guys. Test your knowledge of AI by answering this question. What are the main goals of AI? A. Create expert systems. B. Implement human intelligence in machines. C. Both A and B option. D. None of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Right. So let's say you're trying to predict sales based on two features, x1 and x2. Right. So you're essentially trying to predict sales. So you're saying sales is equal to some function of x1 comma x2. So if you apply a linear regression model on top of this, how would this look like? This would look like sales is equal to some 10 times x1 plus 5 times x2 plus 3, something like this. Yes, this is linear regression. Simple y is equal to mx plus c. Yeah, nothing really complex. Now carefully look at this. So there will be numerous points over here, 1, 2, 3, 4. Let's say they have 100 data points. And I'm going to pass these 100 data points and I'm going to learn this equation from that complete thing. Okay. Now, what we're going to do is I'm going to simply transform this problem into a neural network representation. Take a look. So what I have x1 and x2, right? I have two inputs x1 and x2. And what I'm doing here right? I'm passing x1 and x2 into a particular hidden layer. This is my input layer. This is my hidden layer. And then I'm passing this to another output, let's say. This is my output. So for in all fairness, because I'm not doing anything here, instead of actually having multiple, I'm simply going to say this is my hidden and output layer in this case. I don't really have a hidden layer. Let's assume that I don't really have a hidden layer in this particular case. I just have an input layer and an output layer and nothing else. Let's not worry about the hidden layer for now. Hidden layer is basically some more layers in between. So I have x1, x2. Now, this is, let's say, the value over here is, let's say, some kind of a w1, some kind of a weight w2. So every time I pass a value x1 into it and x2 into it, what I'm saying is that don't just pass the value x1 and x2 as it is, multiply it with w1 and multiply it with w2. Multiply the input value here with x1, multiply the input value here with x, that the value input x2 with w2, and then pass it to my output layer. This is, let's say, my output layer. Right. So what will be the value here, anyone? This will be x1 times w1 plus x2 times w2, right? Because I have x1 coming in from here and x2 coming in from here, and this is nothing but my weight or my coefficient, right? Instead of W1, W2, let's say instead of W1, W2 over here, what would happen? I would have, let's say 10, and let's say if I have 5. So this whole thing would then basically look like, this whole thing essentially is going to look like 10 times x1 plus 5 times x2. And if I, let's say, have a bias term over here, another bias term, ignore the 3 for the moment. Let's not worry too much about the 3 for now. So now my output, my sales, is equal to 10 times x1 plus 5 times x2, which is exactly the same as my linear regression model. So my linear regression, I've essentially converted my linear regression into a neural network type representation. This is not fully a neural network. Almost there. We're almost there. We'll get there as we go along. But in a lot of ways, if you think of it, my neural network is not very different from a linear regression problem. This is referred to as a perceptron, or a neural network with no hidden layers is what is simply called as a perceptron. Or a perceptron is also nothing but your linear regression model in a lot of ways. So now the question is, in the case of your linear regression, what were we trying to do? Because at the end of the day, I would want to make a prediction. I would want to predict my sales. But to predict my sales, I need a linear regression equation. So when I require a linear regression equation, so this whole thing is essentially going to look like this. So my historical data would be, let's say I have money spent on ad, right? And number of stores. And my final, let's say, is I want to predict sales. I want to predict the sales of my business as a function of ads and the number of stores. So let's say across various years, year 1, 2, 3, 4, across different years, I've captured, let's say, the money spent on ads, money spent on the amount or the number of stores that I have, and the sales. And now I've come up with this equation. So to come up with an equation that will predict sales, I've applied linear regression, and my sales would look like sales is equal to some W times beta naught times some beta naught, or rather, just for simplicity's sake, some beta 1 times, let's say, ads, money spent on ads, plus beta 2 times number of stores, plus a constant. Let's not worry about the constant too much for now, right? So plus some constant. Let's not worry too much about the constant. For now, let's basically say that this is the equation that you would want to come up with. So when you solve for a linear regression problem, what are we trying to compute? When you apply a linear regression technique, what are we trying to compute? We are trying to compute beta 1 and beta 2, because beta 1 and beta 2, from my historical data, I'm essentially trying to compute my beta 1 and beta 2, because if I compute my beta 1 and beta 2, if I know what my beta 1 and beta 2, I'm going to say sales is equal to 10 times money spent on ads plus 5 times number of stores. So on any given day, if I know the value of ads and the number of stores, I can always compute my sales. Now that we want to compute beta 1 and beta 2, we just go about our technique, right? We apply whatever kind of techniques that are required, and then we come up with the beta 1 and beta 2 approach. Exactly the same way, even in the case of your neural networks, we are trying to achieve the same thing. So I have my inputs. This is x1, or rather in this particular case, money spent on ads and number of stores. And here I'm basically performing a summation. This is beta 1 and this is beta 2. I want to compute the right values of beta 1 and beta 2 in such a way that whenever I multiply the value of ads and the number of stores, I get the value of sales. I want to identify what that value of beta 1 and beta 2 should be in such a way that whenever I perform that kind of a computation, I get the right value of sales. So these values of beta 0 and beta 2, they are called as weights. In the case of linear regression, we call them as coefficients. In the context of perceptrons, we call these as weights. Right? This is basically how one can actually solve a simple linear regression problem with the help of a neural network. But now the question is, how do I actually solve for beta 1 and beta 2? How do I get the right values of beta 1 and beta 2? I need to find out the right values of beta 1 and beta 2 such that my sales are the best. I can actually come up with the right values of sales. Whenever I pass the value of ads and number of stores, I need to find the correct values of beta 1 and beta 2 such that this summation, whenever I do, which is beta 1 times ads plus beta 2 times number of stores, will always give me the exact sales. So I need to know what that exact value of beta 1 and beta 2 should be. So I need to learn beta 1 and beta 2. How will I learn beta 1 and beta 2? Just like how we've kind of learned beta 1 and beta 2 in the case of linear regression, similarly, we'll have to learn beta 1 and beta 2. So for all you know, the linear regression algorithm that you folks have learned all these years or all these months is in a lot of ways the simplest implementations of a neural network model. Okay, now let's learn how does a neural network model actually learn from here. I mean, this is great, this is all wonderful, but how do you actually solve for beta 1 and beta 2 in the context of neural networks? How are you going to actually find the values of beta 1 and beta 2? We'll learn that in the next couple of in probably the next couple of classes. We're going to learn how beta 1 and beta 2 is going to work. Do we use neural networks to identify the values of beta 1 and beta 2? So we are going to use certain techniques within deep learning neural networks to find out beta 1 and beta 2. This is a neural network, Puneet, but it's just that this neural network is not very large. It's a very small, simple neural network. Now, in a lot of, see, if you see a perceptron is a linear model. Now, in a lot of ways, I can actually, what we can actually do here is, instead of solving for a linear regression problem, I can also solve for a classification problem, same as the one that I mentioned earlier. So let's say I want to predict if somebody is going to churn or not. Churn prediction, which is basically somebody is going to quit or not. And let's say based on the bill amount and I don't know, number of calls, I want to predict if somebody is going to churn out or not in a telecom company based on the amount of bill and the number of calls that they make. Okay, and this is basically a 0 or 1 prediction. 0 means the person won't churn, 1 means the person is going to churn. Now, coming back to the bill amount and the number of calls, let's say I historically capture all possible information. So bill is let's say 200 rupees or dollars, whatever, and the number of calls is let's say 50 calls, and the person hasn't churned. Similarly, somebody's bill amount is let's say 1500, and then the number of calls is let's say 100, and then let's say the person has actually churned, and whatnot, and all of that information, basically. Okay, so now what we're going to do is, just like how we've trained a linear regression problem, we can actually train a classification problem. How can you train a classification problem? Same, two layers, sorry, one input layer with two nodes. This one for bill amount, and this one for number of calls. And what's going to happen is these two are then going to come here, and because it's going to come here, remember, this time I want a prediction that is going to be between 0 and 1. If I want this prediction to be between 0 and 1, what do I need to do? And I just cannot do a, this is going to be W1 and W2, just wait. but it just cannot be that, because I want the prediction to be between 0 and 1. What do I need to apply over here? Anyone? Sigmoid, exactly. You'll have to perform a sigmoid. 1 by 1 plus e to the power of minus. Logit, exactly, Diksha. You'll have to apply a logit transformation. Because at the end of the day, I'm solving a classification problem, not a regression problem. So if I want a classification problem, I want my output to be squashed between 0 and 1. So all that I'm going to do is just to kind of give that out as an output. My output will simply be, instead of just a summation, I'm going to apply a sigmoid transformation over here. So my output will then be 1 by 1 plus e to the power of minus W1 times bill amount plus W2 times number of calls. That's essentially what my output is going to be. Yeah. So what I've done here is, instead of just adding, in the case of a linear regression, what I just did a summation. But in the case, because I want to solve a classification problem, I just don't do a summation. I actually applied a sigmoid transformation. So I just didn't, if I were to simply do a linear regression, I would have just done stuff inside. But because I want a classification, I've essentially applied a sigmoid transformation over here. So the sigmoid transformation would make my prediction to look like that, or make my outputs to look like that. It'll always give me the values between 0 and 1. What is going to make this different and complex is when the hidden layers come in. So when the hidden layers come in, this will look very different. The same sigmoid instead of directly performing sigmoid, what I'm going to do is I'm going to have two layers. I might have something like this. So this is going to be bill amount, and this is going to be number of calls. So I'm going to pass these values into everywhere. So now think about it. So now what's going to happen? This node, the value in this particular node is going to be a summation of a linear summation of values that is coming from this node and something that is coming from this particular node. Similarly, for this one, the value that comes from here and here, so on and so forth. So things get a little complicated when you have a hidden layer. But when you don't have a hidden layer, we'll come to hidden layers in more detail later on. But when you don't have a hidden layer, this is as simple as a linear regression or a logistic regression. I hope that makes sense. Cool. Okay. So going back here again, let's basically go back and learn how this works. So imagine the inputs into, let's go back here. Let's actually try to learn from a small example, and then we can. So if, for example, let's say you have a small network neuron, and let's say you're getting inputs from two sources, and let's say the weight over here is 0.5 and the weight over here is 1 point, is let's say 1, and this is x1, this is x2, and let's say you have a right, for different values of x1 and x2. If you observe, for different values of x1 and x2, so for example, you have x1 and x2 over here, and then you, let's say you pass x1 and x2 through this particular network, we can quickly compute what will be the output from here, or whatever the output is. You can actually compute the output, and let's say this is a summation, just a simple summation. So the value that is going to come out from here is, let's say, 0.5 times x1 plus 1 time x2. So for the first value, the first one is 7, absolutely right, because it's going to be 0.5 times 10 plus 1 times 2. 0.5 into 10 plus 1 into 2, which is going to be 7. What about the second one? The second one is also going to be 7, because it's going to be 8 times 0.5, which is 4, and 3 plus 1 is 3. So 4 plus 3 is 7. And the last but not the least is going to be 17.5, spot on, perfect. So 2.5 plus 15, which is going to be 17.5. Brilliant. So right now, what we've been able to achieve is what is referred to as a forward pass. So knowing the weights, what we've been able to do is we've been able to do a forward pass. That means I've basically passed my values of x1 and x2 through the network, and I got the values as an output. I passed my values of x1 and x2 through the network and I got an output. Great. Now, what would happen if in the case of a, what would happen if I were actually using the similar network to solve for a to solve for a regression problem? So imagine, go back to the same example that we had a while earlier. I have two inputs and I have one, let's say, layer over here, and this is a summation. This is, let's say, I'm trying to predict sales. This is y hat prediction, and this is my money spent on ads, and this is, let's say, whatever you call your number of stores that you have. And let's say this is 0.5 and this is 1. Very, very similar.
Okay guys, a quick info, if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
So this is money spent on ads, this is number of stores, and this is, let's say, my sales. This is historical data, guys. This is historical data, right? So what I've done is over the years, I've gone back and I've captured what is the sales and what is the money spent on ads and what is the money spent on number of stores. So let's say this is I have spent 10 units on ads, and let's say I have 15 stores, 5 and 8 and 10 and 12. And let's say my sales historically have been 25, 12, and let's say 15, right? From where did we get these values? We all understand how we got this, because this data is historical data. This data we will already have from the past. Oh, from where did we get these? So right now I'm assuming that these are a value. I don't know what those values are, which is exactly the whole problem. I need to find a way to compute these values. I don't know how these values have come from and where these values have come from. Right now I'm assuming that it is 0.5 and 1, right? But in reality, I will have to compute exactly what these values are meant to be. So let's go through one round of forward pass again. Let's go through one round of forward pass again. Let's actually come up with some predictions, right? So what will be my predictions? So in this particular case, quickly, what will be my predictions over here? So 10 times 0.5, which is 5, plus 15. 15 plus 5 is 10. Sorry, 20 in this particular case. What will be my prediction here? 5 times 0.5 is 2.5. And then plus 8. 8 plus 2.5 is 10.5. What about the third one? 10 times 0.5 is 5, and 12. This is nothing but 17. Brilliant. Now if you observe, this is my actual y, this is my predicted value y. Do you see an error between my actual value and the predicted value? We see an error. So can we compute the error over here? So if I say error y minus y hat, error is nothing but y minus y hat. So this is going to be 5 units. This is going to be 1.5 units. And this is going to be minus 2. Perfect. So this is the actual value. This is the predicted value, and I have my error. So the total error for the 3 data points is how much? The overall error, if let's say, is I can always sum up, or I can square and sum up. Don't just do a direct add, guys. Remember, whenever you're talking about errors, you don't simply add the errors, you do a mean squared error or a root mean squared error. Exactly, you do a mean squared error or you do a root mean squared error, RMSE or MSE. Okay. So you will basically do a square and then you'll basically add them. You can come up with a basic value, whatever your value is, RMSE. Now, the whole point of doing this is that I need to come up with a model. So basically there is an error in my model. So with the values of 0.5 and 1, I came up with a particular set of predictions which result in some amount of error. But right now, I want a model which results in a zero error. I want this to be zero. If I want my results to be zero, or if I want my error to be zero, what do I want? I want to make sure that my predictions are correct. If I want my predictions to be correct, what need to be corrected? What needs to be corrected? If my error, if my exactly my weights have to be corrected, my coefficients have to be corrected, spot on, my W or my beta values have to be corrected. So something has to happen to my 0.5 and something needs to change for 1. Something has to happen here and here. What should happen? Should this increase? Should this decrease? What should go up? What should go down? Something has to go up and something has to go down. Now, you and I can break our heads and we can do a hit and trial approach over here and try out probably 100 different combinations before we can come up with 100 or 1000 different combinations and search for it in the dark to find the best possible values for this whole thing. And for all you know, I might never be able to get to zero error. I might be able to minimize my error, but I might never be able to get to a zero error at all. Does this make sense, everyone? Yeah. So I want my error to be zero. If I want my error to be zero, I want my predictions to be correct. If I want my predictions to be correct, that means weights have to be adjusted. But if my weights have to be adjusted, how do I adjust my weights? It might take me an eternity to come up with the right kind of weights. That's exactly where we will have to employ slightly more sophisticated techniques to find the best possible values of these weights. That's where we are going to leverage techniques called as back propagation. We will learn about back propagation and gradient descent, where we will learn the approach towards correcting these weights. We will find the best possible way to correct these weights. So what will happen is, for all you know, maybe this might go down a little. This might become 0.8. The moment this becomes 0.8, then I am going to run my whole algorithm again. Then I'm again going to get an error. I will see if the error is large or not. If the error is large, then again I'm going to go back and correct. So there will be a back and forth that will happen. But which weight has to be reduced? Should the 0.5 be reduced or should a 0.8 be reduced? Should it actually be reduced or should it be increased? All that will be driven by these techniques called as back propagation and gradient descent. That way, with the help of gradient descent and with the help of back propagation, we will know what should be the weights and how much the weights have to be corrected. That way, my learning becomes faster. Rather than just searching for these weights in the dark, rather than trying to find the best weights in the dark, I will find a more efficient way to find these weights. Now, the larger question is, okay, this is a very simple network right now. There is no complication here, nothing whatsoever. All that we are doing is we're basically solving for a simple neural network, right? We are essentially solving for beta 1 and beta 2.
We all have kind of learned that at the end of the day, a simple network looks something like this. You have two inputs, and these two inputs sort of you can essentially multiply these two inputs. Two inputs in this particular case, it doesn't always have to be two inputs, guys. It can be more than two inputs. It could be 10, 15, 100, how many ever, depends on the number of features you have. We are taking only two inputs for the purpose of this particular example. That's about it. So I have, let's say, x1 and x2. So this is ads, and this is number of stores. and then I'm predicting sales. So technically I'm saying sales is nothing but some function of ads and number of stores. This is essentially what I'm saying. So what I'm simply saying is that somebody can actually predict sales just with the help of ads and the number of stores. So now, when we sort of built our linear regression model, back in the day when you all were learning simple machine learning or straightforward machine learning, you kind of learned that uh, you know a model that basically looks like this: sales is equal to 10 times ads plus 5 times number of stores plus 10. This is basically a simple linear regression model, which is of the form y is equal to beta naught plus beta 1 x1 plus beta 2 x2, where x1, x2, x1 and x2 are your features, beta naught, beta 1, beta 2 are your coefficients, and beta naught is nothing but your intercept. This is what we all have learned back in the day. Similarly, this was called as a linear model, and then we learned something called as a decision tree algorithm. We learned a decision tree algorithm where we said that, hey, look, you know what, this linear regression models can be built using this. Essentially, when you build a linear regression model like this, what you're saying is that if the model basically looks like this, beta naught plus beta 1 times x, then what you're saying is that this is y and this is x. If you have your points like this model is simply trying to basically fit a line. And if this is basically this kind of a model, then in 3 dimensions, you're essentially trying to fit a plane. So this is y, this is x1, and this is x2. And this plane that we're basically seeing is nothing but your y is equal to beta naught plus beta 1 times x1 and beta 2 times x2. So these are linear models. They assume that your input features are, or your target variable is linearly dependent on your input features. But when you talk about decision tree algorithms, we suddenly say that, hey, look, okay, decision tree classifiers, the same holds good even for your classification problems as well. Classification problems, like for example, in the case of a logistic regression, all that we are doing is we're basically trying to find a line that can cut through these two data points and classify the x's from o's. This is logistic regression. But in the case of a decision tree classifier, things are a little different. In the case of a decision tree classifier, what we are saying, your data points might look like this. We're not going to try and fit one single line. Instead, we're going to draw many lines that could separate my x's from o's. So you essentially draw one line like this, another line like that, and then by doing so, what you've been able to do is you've been able to successfully separate the x's from o's. You tell me, between your decision tree classifier and your linear regression or logistic regression classifiers, linear regression models or logistic regression classifiers, and your decision tree algorithms, which of these is more complex? Is decision tree more complex or your linear models more complex? The only point that I'd like to make here is that folks who believe that the linear models are more complex, just understand that your linear models only assume a linear relationship between your input variables and input features and your target variable. They say that I can simply explain my target variable just with a single line. Right? Irrespective of how my data looks like, I can basically separate my data with a single line, is what your linear models will assume. But decision trees, on the other hand, don't simply build a single line. They actually end up building more complex spaces. Though each line is linear, at the end of the day, the kind of decision boundaries that your decision trees create are non-linear in nature. When I say non-linear, they're not a single line. They're much more complex. I hope that kind of adds some kind of a thought. So think of it, more non-linearity can be captured with the help of a decision tree algorithm than a simple linear or logistic regression algorithm. I hope that clarity persists in your mind. Yeah. So as your models become more and more complex. When I say more complex models, what we essentially mean is that your models are able to capture more and more non-linearity within the data. If I want a model to capture, let's say, for example, I have my X's and O's distributed like this in the case of a classification problem, I cannot draw one single line that can separate my X's from O's. I will require a very, very complex boundary to separate my X's from O's. I need something like this. I need something like that to separate my X's from O's. This cannot be achieved by a line. This is a curve. So what a decision tree can try and achieve is it can try to approximate that. What a decision tree tries to do is decision tree says, okay, I might not be able to create a line, but what I can do is I can probably try and create many more spaces like these. I'll try and approximate that kind of a space, right? So it'll basically try to create that kind of a space for you. So your decision trees are more complex than your linear regression models or your general linear models. Okay. Now, once this exists, or once you establish this kind of a thought process, now let's take this one step ahead. Now you tell me, between a decision tree algorithm and a random forest algorithm, which is more complex? Random forest is more complex. Why? Because random forest is again a combination of many such decision tree algorithms. So thereby your random forest algorithm can capture much more non-linearity than a decision tree algorithm. And between a random forest algorithm and a gradient boosting machines algorithm, your gradient boosting algorithms is more complex because it can capture far more non-linearity. The point being that from one model to another model, from linear regression models to decision tree to random forest to boosting models, the reason why we call certain models are more complex or more accurate is because of the ability to capture more and more non-linearity within the data. When there is more complex, when the data is more is sort of entangled between each other, especially with a classification setup, if you have the positive and negative observations entangled within each other, your complex models can actually capture nonlinearity very well. Now, the reason why I've given this background is because whatever we're going to learn right now is to basically try and capture that nonlinearity. Right? When you're solving a very complex classification problem, your neural networks with the hidden layers in between help us get that non-linearity. Your hidden layers in between help us capture that non-linearity in a much more efficient fashion, right? So think of this. What we are simply saying is that if if I'm able to capture sales as beta naught plus beta 1 times my ads plus beta 2 times my number of stores. This is assuming a simple linear combination. But if, for example, if I don't assume a linear combination, if I don't assume a linear relationship, and if I say that, hey, forget about the linear model, if I want to build a more complex model out of this, one of the ways that you can try and do is, of course, you can use the other random forest models or the other models to build. But what you can also try to do is you can leverage your neural network approach and say, hey, look, instead of just directly assuming a linear combination, this is my sales, this is let's say ads, and this is number of stores. Instead of just assuming this linear combination, I can actually take this one step further, and I can build a more complex. Oops, sorry. About that. I can end up building a more complex representation by saying, hey, look, I have my ads and number of stores, but instead of taking a direct linear combination, I'm going to assume, take a look at this. Absolutely, Sushira, spot on. You hit the nail on the head. Adding an additional layer is like performing a PCA. Exactly. So what does a PCA do? Your principal component analysis is like your principal component analysis essentially captures a linear combination of your input features. That's very, very similar to what we are doing over here. I'm taking my input features and I'm computing a linear combination over here. Similarly, I'm taking my input features, I'm computing a linear combination over here. Once I get a linear combination of my features, so this is going to be, if let's say this is beta naught, sorry, beta 1, beta 2, beta 3, and beta 4. This is going to be, what is the value that is going to come in here? It is going to be beta 1 times adds plus beta 3 times stores. Similarly, in this particular node, I'm going to have values like beta 2 times my adds plus beta 4 times my number of stores. So now, instead of just using directly adds and stores to make a prediction, I have now been able to capture another additional set of features over here. I've been able to capture a linear combination of my features, and then I'm using those linear combination to finally predict my outcome. I'm saying my output is not just directly based on adds and stores by default, but they're actually based on a linear combination of my features.
Just a quick info, guys. Test your knowledge of AI by answering this question. Which of the following is not a stage of AI? A. Predictive analytics. B. Diagnostic analytics. C. Cognitive analytics. D. All of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Yeah, so that way my input features are going to be not just my raw features, but actually engineered features of my raw features, a set of engineered features of my raw features. Does that make sense, folks? But I just want you to understand that if I have my raw features, I'm building a model with my raw features and I'm building a model with engineered features. That means I'm extracting more features out of my raw features and then using those as a part of my model. Which model do you think will do better? The model with newer features, additional features? That's exactly what we are saying over here. I have a set of raw features, and along with my raw features, let's say I build a simple model. This is just raw features, and then I'm building a model. Here I'm using my raw features, and then I'm enhancing these features, and then building my model. Out of these, which one do you think will be a better model? The second one will of course be a better model because I'm enhancing my features. I'm not using my features as is. I'm actually doing some kind of a mathematical I'm applying some kind of a mathematical function on top of my features and then using them to generate my predictions. And that's the reason why having this layer in between is really going to help. Yeah. The only difference is, right, in the case of savings is a linear combination of salary and expenditure. I can simply do salary minus expenditure and I will get savings. But in the case of BMI is not a straightforward difference of the two. BMI is basically is a non-linear combination. So BMI will require me to do something like weight divided by a height or something like that. I'm not exactly sure about the formula, but something like a weight by height or something like that. I'll have to do a non-linear combination. This is linear because I'm just adding or subtracting. Here I'm dividing multiple features. So this is a non-linear combination. Yeah, that's the basic difference. So don't worry about it too much. The point that I'm trying to drive over here is that when you have raw features, you can build a certain kind of a model. But when you have raw features with additional features, the model that you end up building will be far better than your raw model, than your raw features. But what you're trying to do over here is that instead of you manually trying to create these features, instead of you trying to manually figure out, okay, I have expenditure and I have salary, so let me create a salary and salary minus expenditure to create a new feature. What you are doing over here is you're taking the help of some mathematical functions and you're automatically trying to create those features. You're trying to automatically engineer those features. How are you engineering those features? What you're saying is that, okay, let me take ads and let me take the stores and let me add them in a certain fashion. Similarly over here as well, I'm taking ads and I'm taking stores and I'm adding them in a slightly different fashion over here, right? So this could basically end up generating a different kind of a set of features. This could end up generating a different set of features for me. Does that make sense? Okay. Now the thing about, why should I only have one layer? Can I have more layers? Why should I only do a linear combination? Can I do other types of combinations? I mean, like, who's stopping me to just do a linear combination of my features, right? I can actually do much more combination of my input features. I can take my features and then I can do some kind of a division. I can probably, instead of just having one layer, I can have multiple layers. And why do I have only 2 nodes over here? Can I have like 100 nodes over here, right? Absolutely, yes. I mean, we can do all of that. And that's essentially what is going to make this problem into a deep learning problem. So when somebody says that, hey, look, I don't want to have a single layer, I want to have like 100 layers in between, and then, hey, look, I don't want to simply apply the linear combination, I want to apply more complex functions over here. And then somebody would say, hey, look, I don't want to have like, I just don't want to have 2 nodes over here. Instead, I want to have like 100 nodes in each of these. And that is essentially what would make this problem into a much more complex problem. More complex because you have more hidden layers, and more hidden layers means you're extracting more and more interesting features, and the more and more interesting features that you generate, your predictions are going to be more and more complex. So just to kind of summarize, what we are now saying is that, hey, look, instead of building a simple straightforward neural network like this, um, for simplicity's sake, I'm going to call it x1 and x2 from now on, guys, so that x1 and x2 are nothing but my variables. And just for simplicity's sake, I'm going to call this w1 and w2, which are nothing but my weight, right? These are features and these are my weight. So the output was, until this particular point, w1 x1 plus w2 x2. But instead of making it so simple, you can also kind of say, hey, look, I don't want to keep this so simple. So I want to kind of add more layers in between. Something like, let's say somebody decides to, let's say, add one layer with 3 hidden nodes, one hidden layer with 3 nodes, and then one output layer. So in each of these, what's going to happen is I'll have inputs flowing in from here and from here. So this is again still x1, x2, w1, w2. So this is w1 x1 plus w2 x2. Similarly, from here to here and from here to here, this is w3, w4. This is w3 x1 plus w4 x2, and similarly from here to here. And then once you have all of this, everything flows from here to here. So this is going to be 5, 6. So this is going to be w7 and w8. So whatever value is going to be in here, that times w7, so the w8, and this is w9. That times w8 and this times w9. That will be your final output. So suddenly, from here to here, what do you see? Here, how many weights did I have to compute? In this case, how many weights did I have to compute? Just 2. I was just trying to solve for 2 weights. But from here to here, what happened to the number of weights? My number of weights just went up from 2 to 9, just by adding one hidden layer with 3 nodes, right? So with just computing a linear regression problem would take us a good amount of time to solve, because in the case of linear regression, you're just solving for X number of weights, depending upon how many features you have. But here, if your number of inputs are going to increase, and if you have good number of hidden layers, can you see how the number of weights go up exponentially? you actually see how the number of weights just increase exponentially, because more and more hidden layers means more and more combinations. More and more combinations means more and more number of weights. And the number of weights that you will end up having to compute will increase exponentially. That's one of the other reasons why computing or actually solving a linear regression or solving a neural network problem is far more complex than solving for a simple perceptron type of a setup, solving a simple linear regression sort of a problem. This is actually super simple. When you look at this one, this becomes super complex because the number of weights are much higher, and also because the number of the number of weights, the number of computations are actually much higher. Okay. Now, so we've been able to establish the fact that hidden layers are going to help the model, because more hidden layers means more complexity. But then when we talk about more hidden layers, uh, one of the things that we said was, we don't know how many hidden layers do we have to capture. We don't know that. Now we need to first learn about how do I compute W1 and W2. We still haven't learned how to compute W1 and W2 yet. If I know how to compute W1 and W2, I can use the similar approach to compute the multiple weights that we saw in a larger network. If we are able to solve a perceptron model, then we can use a similar approach to solve for a larger problem. So the most common approach towards solving for the weights in a linear regression problem is by using the classic ordinary least squares approach.
Okay, guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
So if you all remember the ordinary least squares approach that you learned, it's the same exact approach. So what we are going to do is quickly, so let's say this is what we have. Let's say I have two inputs. I have x1, I have x2, I have x1, I have x2, and I have, let's say, my y. And then we have my predicted value y hat. This is nothing but w1 x1 plus w2 x2. So let's say the values are 10, 5, 8, 12, 6, 3. And then let's say w1 value is 1 and w2 value is 2. And let's say this is 25. And let's say this is 30. Let's say this is 15. So quickly, is w1 is 1 and w2 is 2. Assume, the first step is assume or randomly initialize w1 and w2. We have randomly initialized w1 and w2. You can initialize with any values that you want, but then we have to keep continuously changing these values to see what's the best. A typical hit and trial approach will ask us to keep randomly changing these values, but we don't know how to change those values. So one approach that is commonly suggested is that ignore what these values are. Just kind of assume that they are w1 and w2. So if, for example, you were to make a prediction, what would this prediction be? So forget about the fact that this is w1 and w2. Forget the fact that it is 1 and 2. Let's say this is w1 and this is w2. So what would this prediction be over here? So it's going to be 10 times w1 plus 5 times w2. Similarly, this is going to be 8 times w1 plus 12 times w2, and this is going to be 6 times w1 plus 3 times w2. So this is the actual value. This is my predicted value. What would be the error? Error is going to be the actual value minus predicted value. So it's going to be 10 times w1 plus 5 times w2 minus 25. Similarly, In this case, it's going to be 8 times W1 plus 12 times W2 minus 30. In this case, it's going to be 6 times W1 plus 3 times W2 minus 15. It doesn't matter y minus y hat or y hat minus y, it wouldn't really make a difference. Actual minus predicted, predicted minus actual, it wouldn't matter because what we are doing is we're essentially going to, you can do a y minus y hat or y hat minus y, it doesn't matter because what we're going to do is we're going to compute MSE, mean squared error. This is error. So if I were to compute a mean squared error, then I'm going to compute an error square. So the error square is simply going to be the square of all of this. And then I need to sum up all of these values and then divide it by 3 because I have 3 values over here. Mean of the squared error, right? So the mean of the squared error in this case is going to be 10 times W1 plus 5 times W2 minus 25 the whole square plus 12 times W2 minus 30 the whole square plus 6 times W1 plus 3 times W2 minus 15 the whole square, the whole thing divided by 3. That is my mean of the squared error. This part is just the error. This is the square of the error. And then I'm doing a mean squared error of the whole thing, of my complete model. This is my mean squared error. Now, if my model were to be really good, if I were to assume that my model is really good, what should happen? My MSE should be minimum. Hopefully 0, but at least the minimum possible value, as minimum as it can possibly get. Right? I want this to be as minimum as it can possibly be. So to compute the minimum, so exactly the numerator has to be 0. 0 is like the best possible case, guys, but I don't know if we can really hit a 0. So that's essentially why I'm saying I want it to be as minimum as possible, preferably 0, but at least it has to be as minimum as it can possibly get. So I need to find, so my problem now has become find W1 and W2 such that my MSE is minimum. That's my problem. All of us agree on this? This is linear regression, guys. I'm not doing anything different here. This is simple, plain linear regression, right? Ordinary least squares. Okay, cool. Now, from here, what do we do? What we do is we say that there are multiple ways of solving it from here, but because we would want to solve it the ordinary least squares approach, what we generally do from here, anyone? What do we do from here? Because I want it to be minimum. What is the best approach towards finding my minimum? If you actually look at this, so I want to kind of establish this intuition in you guys as well, and that's one of the reasons why I'm doing this. So if you observe this one, this complete equation with W1 and W2, what is the degree of this equation? Forget about the 3 in the denominator, just look at the numerator part. What is the degree of this particular equation? When I say degree of the equation, what is the maximum power, right? What is the maximum index that we can get to? 2. Yeah. So when you have something of this form, right? Something like y is equal to ax square plus bx plus c. It's very similar to this, right? It's just that you may not have a bx term over here, but you could have something like it. But because in this particular case you have w1 and w2, in this case you have both w1 and w2. This particular thing is a polynomial. Will look like a, if for example you had something like this, let's say you had MSE is equal to, or let's say I simply put y is equal to ax plus b. This is a simple straight line. But if you have y is equal to ax square plus bx plus c, then you basically have a parabola. It looks like this. This is like 8th standard mathematics, 9th standard mathematics, guys. I'm not reinventing the wheel here. This is how the nature of this particular curve will look like. It'll look like this based on the value of a and b. It'll look like this, or look like this, or look like this. It depends on the value of a and b. The point that I'm trying to drive here is that the value of when an equation looks like this, it your final outcome will basically the curve will more or less look like this particular form. Will look like a parabola. We call this as a parabola. But when you have y is equal to ax1 plus bx2 plus c, so in this case, how would your curve look like? What would this be? It'll be a plane. In this case, it'll look like a plane. Yeah. So this is x1, this is x2, and this is y. This is how the plane would look like. If you don't know about this, it's okay, folks. It's absolutely fine. I think you just need to kind of sing along and just learn that when something looks like this form, when you fit a linear regression equation with multiple features x1 and x2, you're essentially fitting a plane. Yeah, just learn that. Similarly, when you have y is equal to ax1 square plus bx2 square plus cx1 x2 plus d, when something looks like this, if this looks like a parabola, what would this look like? What would this look like? This is again same x1, x2, and this is y. Any guesses? If this looks like a parabola, how should this look like in 3 dimensions? Not a circle. Yeah, it look like a bowl. Yeah, you're right. Basically looks like a bowl. Think of it like a bowl. Yeah. A parabola in 3 dimensions. It's like a bowl. Think of it like a doll. Yeah. So that's how this is going to look like. Okay. The point that I'm trying to drive here is that this equation that you see over here basically looks like this. It's just that instead of x1, x2 is essentially going to be w1, w2, and here it is going to be MSE. That means for different values of w1 and w2, you're going to have different kinds of errors. If you pick this particular value of w1 and this particular value of w2, you'll have a certain amount of error. Right? You'll have a certain amount of error. Similarly, if you pick different values of w1 and w2, you're essentially going to get different values of MSE. I want to pick a certain value of w1 and w2. I want to pick a certain value of w1 and w2 in such a way that I get the lowest possible error. I want to pick a certain value of w1 and w2 such that I get the lowest possible error. Okay, how do I get that? The simplest of the simplest math tells us that if you were to kind of get the lowest or the minimum most point, the best way to do it is you differentiate this particular equation. Here, this is the part where things can get a little tricky, guys. So if you haven't understood all of this, it's okay. This was just like a background. But what we are saying here is that if you want to find the minimum value of, so I want to find the values of W1 and W2 such that my MSE is minimum. That's the fundamental point. So how do I get this? The way I'm going to get this is by differentiating my MSE and equating it to 0. Similarly, dou MSE by dou W2 equal to 0. So I'm going to differentiate this equation 2 times with W1 and with W2. We call these as partial derivatives. We call this as partial derivatives. This is the part of this is a part of AI which requires you to learn a little bit of math. This is all 10 standard mathematics, guys. We are not learning something which is beyond 10 standard by any means, right? Um, so it's okay if you're struggling here a little. The point is that to get to the minima, to get to the minimum most value of this particular sphere, what I'm saying is that I want to get to the minimum most value of this particular sphere. I want to get to here. I want the values of W1 and W2 where the sphere is at the bottom most. Why the bottom most? Because when it is bottom, that means my MSE is minimum. How do I get there? The best way to get there, according to certain concepts of math, is that the best way to get there is by computing partial derivatives. So you can compute the partial derivatives like how you see here, dou MSE by dou W1 and dou MSE by dou W2, and that way it will give you, if you compute the partial derivative of this equation and partial derivative of this equation with W2, you're going to get two linear equations. You're going to get two linear equations. So two linear equations with W1 and W2, so two equations and two unknowns. Then you can solve for W1 and W2. Two equations, two unknowns. So you will get basically equations that look like this. So you'll get basically something like 8W1 plus 5W2 is equal to 0, and 6W2 minus 5W3 is equal, 6W1 minus 5W2 is equal to 8. You'll get two equations like this. I mean, these are arbitrary equations, of course, that I've currently put. With these two equations, do you think we can solve for W1 and W2? Absolutely. What you can do is you can just add. So you can simply cancel 14 W1 is equal to 8. So W1 is equal to 8 by 14. If W1 is equal to 8 by 14, take W1 and substitute it back in this equation or any one of these equations, you will get the value of W2. So 5W2 is equal to minus 8W1. So W2 is equal to minus 8 by 5W1. And so W2 is equal to minus 8 by 5 multiplied by 8 by 14. So this is my W2 value. So this is W1 and W2 values correspondingly. So with these values of W1 and W2, what we are saying is that this network with that values of W1 and W2, this network will give me my best possible model. With the values of W1 and W2 that I kind of was able to extract here, I will be able to build my best possible network or best possible linear model in this particular case. Okay, this is just assuming W1 and W2, just two weights that we've solved for right now. Now think about this, given this kind of a setup, this kind of a scenario, now that we've learned how to actually solve for a single layer neural network, and now that we've been able to solve for a very, very simple problem like what we see on the screen, the next question is, how do we learn when we have multiple hidden layers?
Just a quick info, guys. Test your knowledge of AI by answering this question. What are the main goals of AI? A. Create expert systems. B. Implement human intelligence in machines. C. Both A and B option. D. None of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
When we have multiple hidden layers, the problem is all the more complex, because then you're not simply solving for W1, W2. This equation is just not going to be W1, W2. This equation will be way more complex. If this equation becomes way more complex, this curve is not going to look like a parabola anymore. This will be a way more complex surface, right? Take a sheet of paper, hold it on both sides, and twist the paper in either direction, right? So take a piece of paper or a piece of cloth, and then you twist it from either sides in different directions. The kind of surface that it creates is the kind of is the kind of surface that you're going to have. We call these as hyperplanes, right? This is a simple plane, but imagine somebody is holding this plane from this direction and somebody is holding in this direction. You're twisting it here in this direction, twisting it in the other direction from either side. think of the kind of surface it will create. So you'll see a lot of bumps and a lot of crests and a lot of troughs and all of that. And we call those as hyperplanes. So when you have more weight, and more complex equations get created. More complex equations means that this will not simply be a parabola or a paraboloid anymore. This will be a super complex surface. When this becomes a very, very complex surface, the solution is not going to be so trivial. So there we will have to make a lot of approximations. So the point that I'm trying to say is that as deep learning as you keep adding more and more layers, the problem you're is going to become more and more difficult to solve. You will require more and more computational power to solve those problems. Why do we need GPUs to solve deep learning problems? The reason we need GPUs to solve these problems is because when you're solving a 10 layer deep neural network, and in each layer, if you have, let's say, like 50 or 60 hidden layers, sorry, nodes in each layer, imagine the number of weights that you're solving for, and imagine the kind of complexity that is under the hood. It'll be super duper complex. And then when it is super duper complex, when it becomes so difficult, the amount of the amount of computational power that is required, your CPUs will not be able to provide that. And that's exactly where GPUs come in. And GPUs will help us solve them in a much more efficient fashion. Now, let's just go back here and let's just start looking at how the hidden layers are going to help us enhance the model. Until this particular point, we haven't really added any hidden layers, but then we'll start slowly learning about how hidden layers are going to help us start solving problems. So now, so we have a simple x1, x2, two inputs, and instead of a direct output, let's say you have a hidden layer. You have a hidden layer, and these hidden layers are basically like this. Um, the best way to, and similarly from here to here, and from here to here, and then these outputs are then going to simply help us get from here to there. Okay. Um, Now this is the most obvious way of sort of representing this is from a naming convention standpoint. Well, different people represent these names differently. uh, from a naming convention standpoint, people call this W11 because it goes from the first node of this layer to the first node of this layer, and this is called as W12 because it goes from the first node of this layer to the second node of this particular layer. This is going to be W21 and W22. Yeah. And then you could basically call this W3 and W4. That's a decent naming convention, so to say. Now, as I said, the value of h1, and I'm going to call this h2, and this is your final output layer. This is, let's say, y. W11 times x1 plus, because W11 times x1, this is from here to here and this as well. So these are two inputs that are coming in. Similarly, W21 times x2. Similarly, for h2, the value is going to be W21 times x1 plus W22 times x2. And your value at y, your output is going to be, what is going to be the value at y? W3 times h1 plus W4 times h2. Remember one point, that until this particular point, we haven't added any kind of a bias term. We haven't added any kind of an intercept term. Remember intercept? When we talk about linear regression, we say y is equal to mx plus c. We haven't added any of the c terms yet. We will add that as we go along. Let's not worry about that right now. But just remember that you will have one more term everywhere. So instead here, you're essentially going to have C1, C2 plus C3. Essentially, you're going to have one more constant terms all throughout. Yeah, so for now, for simplicity purposes, I'm not really taking them into considerations. Okay, for the purposes of the simplicity sakes. So this is what your values at h1, h2, and y are typically going to look like. Okay, the way you could H2 is going to be, sorry, W12. W12. Yeah, perfect. So the way this is also represented, right? You could also basically represent the value of H1 and H2 with, in some form of a matrix representation as well. And we will learn that as we go along. So people also represent it with W dot X, summation sigma W into X, where W and X are two vectors, right? W1 X1 is what they also refer to this as. Uh, Essentially what I'm saying is that this could basically look like this as well. So you could basically have one row, two columns. Sorry. W11, W21, and then you can have X1 and X2. So when you do this, this is basically one row, two columns, and two rows, one column. This would basically return one single value for you. You could represent it using a matrix representation as well. Similarly here as well, W12, W22 times X1, X2. And here, this is going to be W3 and W4 times H1, H2. And then you can simply represent it using a numeric representation as well. This is a matrix product, matrix multiplication, right? Now, assuming that because in this particular case we just have like two weights flowing into H1 and H2, it sort of becomes very easy. But at times what may happen is that because there are multiple weights, you might have multiple weights, and this might actually become much bigger, and this might actually also become much larger as well as we go along. So your weight matrix can also become larger, your X1, X2 also might become larger. Net, the point being that um, the best way of kind of visualizing these matrices and these computations is by using matrix representations. So you will see that as you go along in a lot of places, in a lot of literature, you will see that instead of just representing the computation using a simple math like this, people prefer representing it using matrix representations. That way, it's sort of easier for people to understand that you have two weights and two X1, X2s, and or rather two inputs and two weights. So the combination is what we see over here. Uh, Also, what people generally do is that instead of representing it this way, they also say that the hidden layer values are W11, W21, W12, W22, and multiplied by X1, X2. So when you do this, this is basically a 2 by 2 matrix, and this is a 1 by 2 matrix. Sorry, 2 by 1 matrix. So this would return again H1, H2 values. This would basically return H1, H2 values. You can also represent this whole thing. I mean, this layer computations can simply be represented like that. Yeah, so that's the other thing that I wanted to sort of represent as well. Now, going back to the computations that we just saw. Now, so to make it more easier for us to understand, at times what people also do, because to kind of make the math a little more, or rather the feature generation. So H1, H2, as you observe, are like the intermediate hidden layer values that are basically getting generated. And we all know that the reason why we are doing this is because H1, H2 are basically going to give us additional complexity, are basically helping us add additional layers or basically additional features that are getting created at the background. And that's one of the benefit of having your hidden layers. So instead, what people also do at times is they say that, okay, why should I just do a linear combination? Can I not just apply some kind of a function on top of this? You know, instead of just doing a linear combination, I'll apply some kind of a function on top of this. Right? I'll apply another function on top of this. And instead of just taking the outcome as it is, I'll apply some other function on top of this. Right?
So why do I just want to take the values as is? Why do I just want to take a linear combination? Instead of just doing a linear combination, I can actually do much more than just a linear combination. I can actually take a linear combination and apply a function. So if you remember your support vector machines from your previous sessions, or from your previous learning, one of the things that support vector machines does is that SVM adds certain functions in between that helps us or performs something called as a kernel transformation. Do you remember something called as a kernel transformation? A kernel transformation is basically nothing but, instead of just using the features the way they are, you transform your features into a higher dimension. You apply a function and you transform your features into a higher dimension. By doing that, what happens is that you gather some kind of an additional non-linearity. You basically get some additional non-linearity into your data, or your model starts to represent more non-linearity. And the way you achieve that is by adding these kind of additional functions. So instead of just taking a linear combination, you take a linear combination. Additional to that, you apply some kind of a function. These functions that we apply, these functions that we apply are called as activation functions. Okay. Why do we apply these functions? Again, the reason why we apply these functions is because even if you don't apply those functions, the combinations are still linear. So you will really not get the kind of benefit that you want. So if you really want to capture a lot of non-linearity, that means then you require functions which are more non-linear in nature. So rather than just doing a simple addition and multiplication, if you're able to apply more complex functions, like for example, apply a sine transformation or a tan, a hyperbolic transformation, apply some kind of complex transformation functions on top of your existing data. That way, what you will get is, instead of just fitting, just basically fitting y is equal to w3 h1 plus w4 h2, you're basically fitting y is equal to some complex function times w3 h1 plus w4 h2. Here it is simply not a linear combination, but because you're applying an additional function, this model, the final layer, could actually be a much more complex representation of your input layer. So that way you're capturing more non-linearity within your data.
Okay, guys, a quick info. If you're looking for an end to end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So, the details are available in the description box below.
Do we all understand why we are applying an activation function over there? The reason why we apply activation functions is because it will help us capture more non-linearity. Hidden layers already are helping us capture non-linearity, but if you want to capture more amount of non-linearity, larger amount of variability within your features, you apply more functions. So if you apply more functions, then your your models are even more complex. Yeah, does that make sense? So just to kind of give you an intuition, if for example, in a simple linear model representation without a hidden layer, let's say forget about a hidden layer. Here, let's say I'm applying an activation function. Let's say the activation function is a sine transformation. Let's say the activation, or rather, forget about a sine transformation. Let's say I'm using, let's say, a square transformation. Right? This is x1, this is x2, this is w1, this is w2, and this is y. If I did not have an activation function here, what would we have? We'll simply have y is equal to w1 x1 plus w2 x2. Simple linear model. But when I put an activation function over here, I'm saying square this thing. Now my function is going to be w1 x1 square plus w2 x2 square plus 2 w1 x1 x2 w1 w2 x1 x2. This. Now if when you compare y is equal to w1 x1 plus w2 x2, when you compare these two, this is the first one and this is the second one, can you tell me which of these two models is more complex? So more complex because you're able to capture, this is more non-linear, right? This is just fitting a line. This
is basically fitting a curve. So between this and this is much better than this model. This is simply fitting a simple straight line, while this is actually like a curve, like a parabola sort of a thing, because it's second degree. So this will basically look like a parabola, something like this or something like this. So clearly this is a better model than the other one. Yeah, that's the whole point about applying activation functions. So when you apply an activation function, suddenly what happens, data which was previously just getting represented in a straight line, or a model which is just fitting for data in a straight line, now suddenly starts to fit for a more complex dimension, more complex shapes. And imagine, instead of just applying that activation function at the last layer, by the way, we are already applying an activation function for the last layer in the case of a classification problem. For a classification problem, we are already applying an activation function. A sigmoid activation, absolutely right. A sigmoid activation is also another activation function, because you are trying to get that nonlinearity. As simple as that. Because if you just do w1x1 plus w2x2, it's a simple straight line. But if you apply the if you apply the transformation, what it does is it basically transforms that into a sigmoid curve. This is a nonlinear function. That's the whole point of performing of applying activations. Patterns that you couldn't capture earlier with simple linear combination can be captured using activation functions. So the same thing again, guys. So why do we need activation functions? Like, for example, if you just had x and y, and if the data looked like this, you cannot really fit a straightforward model. But when you apply a transformation, like for example, if you do apply the square transformation, suddenly now the data in third dimension is nicely separable. So you can then draw a simple straight line, and then you can separate the red points from the purple points from the blue points. Same thing, right? More complex models. You can actually build more complex models using activation functions. Uh, the ones that you see on the left side, these are all the kind of very, very popular activation functions, starting from identity transformation, meaning doing nothing, right? Identity transformation basically means do nothing. F of x equal to x. That means just pass the values the way they are. Then you have binary step activation functions. Then you have sigmoid activation functions, tan h activation functions, ReLU, rectified linear units is what you mean by ReLU. You have something called as leaky ReLU, which means leaky rectified linear units, and then a softmax activation function. Out of these, we kind of know a few already. We have, in some form or the other, got exposed to a few activation functions. A few we will learn as we go along. Now, when you have an activation function, the question is, should you apply the activation function? We'll learn about these activation functions in a second. But the question is, do you apply the activation function for individual nodes, or do you apply the same activation, or do you apply different activation functions for one node and another activation function for another node? Well, you can try to apply different activation functions at different nodes, but imagine if you have a very, very large you can also apply an activation function on the output node. You can apply different activation functions at different places. But when you have larger networks, it becomes really difficult to track down which activation function is applied at what node, and it becomes really difficult to tune your models. So the popular belief and the popular and most deep learning frameworks, they allow you to apply an activation function on the complete layer, not on a single node. So that means if you choose an activation function, the activation function is the same for all nodes of that particular layer. Yeah. So that way, what happens is that it'll be easier for us to track, number one, and number two, it'll make it more. Um, it'll make your model more. The computations are actually also going to be much easier. And you will realize why that is the case when we really learn something called as back propagation. We'll learn about a concept called as back prop in a couple of days. Probably by the next session, we're going to start learning back propagation. There we will learn what is the best way to apply activation functions. But in general, the common approach is that we apply back activation functions across the complete layer.
not on a single node. So let's go back. Let's start understanding what each of these activation functions are. The most obvious one is an identity activation function. So identity activation function basically means do nothing. Whatever the value is, just pass the value the way it is. No, applying no function is an identity activation function. Yeah, that's essentially what an identity activation function is. Then the next is a binary step activation function. So the second one is basically a binary step activation function. Uh, so basically, it's a step. It's called as a step function, right? Uh, that means you are always going to return a value between for any value under 0, you will return a value 0. For anything greater than or equal to 0, you will always return 1. So it's like basically a thresholding function, right? This is very popularly done in the case of it's actually done in the case of logistic regression. Before people applied the sigmoid transformation, the binary step activation function is actually was the go-to approach, right? Let me show you what I mean by that. So back in the day, when people were solving classification problems, so we know that y is equal to w1 x1 plus w2, or let's say w1 x1, something like, let's say y is equal to mx plus c was your linear equation. And then what people did was they said that, okay, whatever may be the value, because if you were to solve classification problems like this, for example, you had income and you were predicting if somebody would make a purchase or not, right? um, right. Let's say you were to predict if somebody is going to make a purchase or not based on their income. People with lower income did not make a purchase, people with higher income made a purchase. But if you were to simply fit a linear equation, a straight line would basically go like that. So then this equation would basically be purchase is equal to uh, m into income plus some constant value c. But beyond a certain value of income, your purchase will go beyond 1, because if you look at a higher income value, the prediction will basically go much beyond 1. And for a lower income value, the income will actually go much less than 0. The prediction of purchase will become much less than 0, because this will range from minus infinity to infinity, but I would want this to range from 0 to 1. So the way people did was they said, okay, doesn't matter if the prediction, if the m times income plus c was greater than a certain value, was greater than a certain value p, then we will always return a 1. If it is less than or equal to certain value, then we'll always return a 0. That way, instead of fitting a straight line, they always used to fit a, something like a thresholding function like that. Yeah. Then later people realized that, hey, look, this is not a great way of going about it. That's when the sigmoid function came in. Yeah, the p is something that we will have to experimentally identify, right? You will set different values of p and identify the accuracy. You'll set one value of p, see what the accuracy is, set another value of p, identify what the accuracy is. So p is something that you will have to empirically identify. Yeah, but the point that I'm trying to drive here is that originally people used to do things like that, but then later on people realized that, hey, look, this is not a great way, and that's when they came up with a sigmoid function. The other point is, whatever we are seeing over here, the binary step function is also very similar, right? It will always return a certain value beyond 0. In this case, it is 0. If it is less than 0, it will always return a 0. If it is greater than or equal to 0, it will always return a 1. So if, for example, in a hidden layer, if, for example, you've applied a binary step function for whatever may be the reason, if you've applied a binary step function on a hidden layer, if the h1 value that you've computed, if this value that you've computed is, let's say, a positive value, the binary step function would basically return a 1. If it is less than 0, then it would return a 0. That's essentially what this function is basically going to do. So just to kind of take one small example, let's do a quick example and then we can move on to the next one. Let's do a small example on this. So let's say we have a hidden layer. Um, W1, W11, W12, W21, W22, W3, and W4, X1, X2. This is H1, H2, and this is, let's say, Y. So if X1 is equal to 10 and X2 is equal to 5, and if W11 is equal to -1, W22 is equal to 2, W12 is equal to 3, and W21 is, let's say, is equal to -3, then compute the value at H1. If compute the value at H1, also compute the value of H1 with identity activation, and compute the value at H1 with binary step activation. So the binary step activation, by default, the threshold is 0. This is the binary step activation. If anything it is less than 0, it is 0. Anything greater than or equal to 0, it will return 1. So H1, the formula for H1 in this particular case is going to be W11 times X1 plus W11 times X1 plus W21 times X2. So W11 in this case is -1. -1 times X1 is 10, and W21 is -3. So -3 times X2 is 5. So this is basically -10 minus 15, which is -25. So H1 with identity activation is -25, and with H1 with binary step activation, H1 with a binary step activation is going to be, remember, going back to the binary step activation, if the value is 0, less than 0, it will return a 0. If it is greater than or equal to 0, it will return a 1. So in this case, it will return a 0 because it is less than 0. So basically, the point is the output from this particular node is not going to be -25 with a binary step activation. This will basically return a 0 from here. So this is one function, one of the many functions that you could apply. Now, the question is, when should I choose binary step activation function? Now, there is no rule of thumb as to which one should be picked when.
Just a quick info, guys. Test your knowledge of AI by answering this question. Which of the following is not a stage of AI? A. Predictive analytics. B. Diagnostic analytics. C. Cognitive analytics. D. All of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
We are going to learn a few more functions. The decision of which one we should pick is based on the kind of problem that we're going to solve. If, for example, you're solving, um, in general, what people have observed is that while you have the option of picking so many different activation functions, in general, people have seen that for any kind of problem, ReLU or leaky ReLU in general really helps, right? Sigmoid and TANH and the others have a lot of issues. But for hidden layers, you can apply ReLU or leaky ReLU, and they seem to be actually performing really very well. We will learn about ReLU as we go along. But again, these are like different options that you have. You can pick whatever you want, and then you will have to try out seeing which functions work in which layers. There is no rule of thumb of saying, okay, this is the kind of data, so you should apply these activation functions or whatever. Different activation functions work well for different kinds of problems. Just like, for example, if you've learned a lot of machine learning models, right? You've learned linear regression, you've learned random forest, decision tree, bagging, boosting, whatnot. These are different techniques that you've learned. And for all kind of classification problems, you try out one or the other and see what works the best. Similarly, even here as well, you have these as options. And these are like hyperparameters. You will pick one or the other to see what works the best. In general, what people have seen, right, for most problems, ReLU or leaky ReLU sort of give you the best kind of outputs. You don't have to do a lot. You don't have to sort of think a lot. You can just pick ReLU or leaky ReLU, and then they are sort of the one of the best. We haven't looked at what ReLU is. We'll come to it ReLU in a minute. But we've done binary step activation. This is sigmoid activation. We all know sigmoid activation. We've been applying sigmoid activation in the last layer forever now. I mean, whenever since the day you've learned logistic regression, you've already been using sigmoid functions. So this is not nothing new to us. But you can also say that, hey, look, I want to apply a sigmoid activation even somewhere in my hidden layer as well. You can say that, hey, look, I want to apply a sigmoid activation in my hidden layer also. You can also do that. That is fine as well. Yeah. So you can, by default, we've been applying sigmoid activation in the last layer. When you're solving a binary class classification problem, we've been applying a sigmoid activation in the last layer. But you can also apply a sigmoid activation to hidden layers in between. What would a sigmoid activation do? If you apply a sigmoid function, what will it do? It will always return values between. What values will it return values between? Between 0 and 1. Absolutely correct. You see this? Irrespective of whatever the input value is, the output will always be between 0 and 1. That's basically a sigmoid activation. There is something called as a tanh activation. Right? There's something called as a tanh activation function. So the tanh activation function, basically it's called tan h, means tan hyperbolic x. This is a hyperbolic trigonometric function. Hyperbolic functions basically are they're very similar. This tanh activation is actually very similar to that of sigmoid activation. If you actually observe this curve and this curve, they're exactly the same. There you go, exactly the same. The only difference is your sigmoid returns values between 0 and 1. If you see this, the minimum most value is 0 and the maximum value is 1. While in the case of tan h, the minimum most value is -1 and the maximum value is +1. Yeah. So that's why tan h is a shifted version of a sigmoid function. It's very similar to that of sigmoid function. It's just a shifted version of a sigmoid function. While your tan h activate sigmoid returns values between 0 and 1, tan h returns values between -1 to +1. Yeah. So let me show you what I mean by that. So let's say, for example, in this particular case, cool. So for example, if you want to apply an h1, so the value of h1 in this case is -25. We all know it. So then when you apply a tan h activation, let's say for example you apply a tan h activation, look at what the tan h activation, tan h of -25 is going to be. So let's go back here. So you look at the formula, 2 by 1 plus e to the power of -2 power x -1. The way actually I think the right formula for this, we can come back to, we can actually look at this later. The actual formula is this: e to the power of x plus e to the power of -x by e to the power of x minus e to the power of -x. This is the actual formula of tan h activation. So if you apply if you apply -25 to it, so this is basically going to be e to the power of 25 plus e to the power of -25 by e to the power of 25 minus e to the power of -25. So compute what e to the power of 25 is. This will always return a value that will range between -1 to +1. Come what may, it will always return value between -1 to +1, whatever it is. You can compute what e to the power of 25 and e to the power of 25 is, and then you'll figure it out. Yeah. So the point that I'm essentially saying here is that irrespective of whatever may be the value, this tan h activation will always return a squashed value, a value that is between 0 and 1. See, I want you to sort of look at it this way. See what it is doing. See what these functions are doing. You are getting raw values as inputs. From x1 and x2, you are getting raw values. and then you're multiplying those raw values, and then you're getting another value over here at h1 and h2. You're basically getting another value. By applying these activation functions, what it is doing is that these activation functions are basically transforming these numbers into a much more handleable values, because x1 and x2 can be very, very large input values. But when the moment they come in, what you're doing is that you're applying these activation functions and you're actually squashing them. You're actually making these values much smaller. The moment they become much smaller, what happens is that they become more computationally more handleable throughout the complete process, because larger values make the computations more difficult. So by reducing those values and by making values more smaller, it is making the computations more easy. Secondly, by applying these non-linear functions, you're adding a lot of non-linearity as well. Okay, that's one of the reasons why these activation functions are really, really very helpful. This is the other activation function, guys, called as ReLU. Right? ReLU stands for rectified linear units. Right? Rectified linear unit. Right? That is what ReLU stands for. If you are if you're familiar with diodes, and how pulses are passed via diodes, you would kind of relate to this. This is some kind of a diode, rectifiers, right? So these are very similar to that. So the point simply being that what rectified linear units do is, if the value is less than 0, it'll return a 0. If the value is greater than 0, it'll return whatever the value is as is. So it basically kills negative values. That's what your ReLU does. The ReLU will always return values from 0 to infinity. What if the input into the ReLU activation is a negative value? It will kill the negative value. It will return a 0. If it'll only return a positive value. If the value is positive, it'll return the value as is. If it is negative, then it'll return a 0. That's essentially what this does. So if it says, if it is 0 for x less than 0, x for x greater than or equal to 0. That's essentially what your rectified linear units do. So what it basically does, this is this rectified linear units are primarily chosen they are the best choice for to be applied in the hidden layers. In most cases, what we see as ReLUs are probably the best. Uh, and there is one more variant of ReLU called as leaky ReLU. What people have observed is that at times, if you sort of apply uh, at times if you sort of apply the actual ReLU, it kills negative values. So to kind of not kill the negative values and to sort of um, keep the computations going, because imagine what may happen is, for example, h1 and h2 both return negative values, then the output of both of these is zeros. And if you applied a ReLU, then output of both of these is zeros. Then what happens there is that then there is no value that is going to go ahead. The y is also going to become 0 then in that case. So the complete network will become stale. So to kind of not do something like that and to kind of keep the network going, what you do is you kind of let a little negative value go through. You don't completely let the negative value go through. You just let a small negative value go through. Okay, let's go on. Then this is softmax activation. Softmax activation is basically like your sigmoid activation only, sigmoid function only. This softmax activation is actually used in the output layer, especially when you're solving a multi-class classification problem. Your softmax activation basically helps us always return values between 0 and 1. Like for example, imagine a network that looks like this. Think of a network. Yeah. Now you're basically returning 3 outputs. And again, the last one,
it's a super complex network, basically because there are too many hidden layers in between. But then you're essentially returning three outputs. Let's say this is y1, y2, and y3. You're returning three outputs. And let's say you're solving a three-class classification problem. So, but y1, y2, y3 are all going to be values which are going to range from minus infinity to plus infinity. They all will range from minus infinity to plus infinity, right? So because they're going to return from minus infinity to plus infinity, the problem is then going to be that because you're solving a classification problem, you want the outputs to be squashed between 0 and 1, and you want them to be like probabilities. So the best thing to do in that case is apply a softmax activation in the last layer. In this layer, apply a softmax activation. So when you apply a softmax activation, what it will do is it will return values. So for example, if this is 100, 50, and 50, let's say the outputs are in that particular fashion, your softmax activation, what it would return is it would return 0.5, 0.25, and 0.25. It'll basically do something like that. It'll do some kind of normalization of your final outcomes. Whatever are the values that are coming in from this particular layer, with the softmax activation, they become a little more. They all then sum up to one. They all will then sum up to 100 to a probability score of 1. They get normalized. That's the beauty about softmax activation. The only place where softmax activation is generally used is in the last layer. Just like how we applied a sigmoid transformation for binary class classification, when you're solving a multi-class classification, you apply a softmax activation function. That's it, right? Irrespective of 3 class, 4 class, n class, how many ever may be the classes, the last layer, if you apply a softmax activation, the outputs will always be between 0 and 1. And they will all sum up to, let's say, all the outputs will then sum up to 1. Yeah. So a multi-class classification problem can be like you're looking at an image and you're predicting if it is a cat, dog, a mouse, or let's say something else. So in this case, cat, dog, or mouse, you're essentially predicting is the image a cat, dog, or a mouse. So you're getting 3 probabilities, but then you want to squash all of them between 0 and 1. That's where you apply a softmax activation, and then it will give you values like 0.5, 0.25, 0.25. So 50% chance that it is a cat, 25% chance that it is a mouse, and 25% chance that it is something else. That's as far as our activation functions is concerned. So let's go back here. So if I were to sort of talk about how how we can actually learn a perceptron algorithm, we've already gone through this. I'm just running through the slide for now. So what the slide is, what we're saying is we start.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
We start with some kind of inputs and weights. That means your W1, W2, W3. We start with some form of weights, and then we calculate. We go through the whole thing. We basically run our data through it. We compute what the error is, and then based on the error, we come back and we change the weights so that we would want to make sure that we reduce the error. Same thing like your linear regression problem. So what we are going to do is we are going to initialize our weights with some random values, and then with those random values we run a forward pass. But when we run a forward pass, we get a prediction. But based on that prediction, we get an associated error with that particular prediction, because your model is either too good or too bad or whatever. You're essentially going to get some kind of an error. If the error is extremely high, then what you do is you go back and you update your weights. You run some kind of an update function. Let's not worry about this function right now. Some form of an update is what we run to our weights, to our W1, W2, W3, how many ever weights are there. We run an update. We change the weights a little. We don't know in which direction, we don't know what, but we essentially perform some kind of an update. And once the update is done, then you again go back. Hit and trial, Prashant, is one way of changing the weights, but of course hit and trial will take us forever. So there are different algorithms that we will learn that will make it easier. And what you do with once you start learning the weights, once you start changing the weights, you see that, let's say if the output is getting better, you end. If it is not getting better, then you again go back, and then you again change the activation, and then you again change, let's say, your weights. So you keep iterating through this process until you find the right kind of weight. Okay. So yeah, that's basically the typical process of your learning algorithm or your perceptron training algorithm. Guys, think of biases. So in your linear regression problem, what is the importance of an intercept? Why is intercept important in your linear regression algorithm? A bias is bias is the same thing here as well. Think of bias as the same as your intercept in your linear regression algorithm. So for example, you also train a so in the case of a linear regression problem, just to kind of throw some kind of an intuition, error, think of it as error, Rohin. But I think intuitively from a business standpoint, this is why intercept is super important, and training an intercept value is super important. So let's say I'm predicting sales, and I'm saying I'm going to predict sales as a function of money spent on ads, and also you're trying to predict sales based on the number of stores. We saw the same example the last time as well. So if you're going to say train a linear regression algorithm on this, so your linear regression could say sales is equal to 10 times ads plus 5 times number of stores. Okay. Now, for some reason, money spent on ads. This is basically when I say ads, that is money spent on ads or the number of ads. Think of it as number of ads. So on, let's say on any given day, if your number of ads are zero, and if your number of stores are also zero, then what your linear regression algorithm is saying is that your sales are going to be zero. Right? Which sort of doesn't make sense, because you're probably not just running your sales via your stores. Stores is probably one of the ways of running your business. You're probably running your business with, let's say, your stores, you have a web business, you have an e-commerce platform with which people can come and purchase products. So the number of stores that we talk about is not the only feature that could determine, or these two are not going to be the only features that will determine the sales. Exactly, there would be some minimum sales that would happen. Yeah, I mean, if there are no ads and no stores, the sales are going to drop, but that doesn't mean my sales are going to be zero. So to compensate for that some minimum sales, I want my model to have some amount of bias by default towards my sales. That's basically where I train a bias, or in the context of a linear regression, we call it as an intercept. That's as simple as it. Yeah, that's the same thing as your intercept. Okay. This was one of the questions that was asked to me in one of my interviews. Why do you need an intercept in a linear regression problem? So yeah, I mean, I think so basically constant is the same, right? Constant is the same as an intercept. When you say plus c, that is the intercept term, and that is the same as bias in this case as well. So when you say y is equal to mx plus c, the c is nothing but the intercept. C is nothing but the constant. It is interpreted differently at different places. So we may not account for some features, and for all of those additional features, you're essentially training one metric that kind of captures everything else. That's like a catch-all. Think of it like a catch-all. Yeah. So for features that you do not have as a part of your model, you're essentially training another intercept. Cool. That's basically where bias comes into the picture. Brilliant. So let's go back again. So that's what we're saying over here as well. So when you say bias, so when you say x1, x2, x3, x4, and when you say bias, that's essentially the same thing. So we're saying sales, ads, money via e-commerce platforms and all of that, plus a constant. Bias is nothing but a constant. Now, this is the process that we would ideally want to follow. That you start with some random values, you calculate, you go through the models, you try and make a prediction, and based on the prediction, you compute the error, and based on that error, you realize that, hey, look, there's a lot of errors, so I need to go back and change my model. Changing a model essentially means changing the weights. So if I have to change the weights, I don't know which direction to change. Let's say there's a known way to make that change and make the change in some fashion. And once that particular change is made, then we again come back and retrain the model using the updated weights. At times the weight may work in your favor, may not work in your favor. Again, you go through this process once again. So you iterate through this complete process, let's say 10, 15, 100, 1,000, 2,000 times based on the data that you have, based on the volume of data you have, based on how long it is taking for you to learn the new weights. You run through this complete process. If you're doing a hit and trial, you will just probably be going in circles, and it might take you infinite times. Theoretically speaking, it will take you infinite times to reach a good model. So you need a more robust approach towards updating weights. So one of the ways is called as gradient descent. We will learn about that later on. But technically, there is an approach towards updating the weights. Yeah. I mean, so broadly, this is like at a very, very high level. What we've been talking about until this particular point is like those fundamental components of AI and neural network. We haven't really dug into the depths of it. Right now, we're going to do it in the next few minutes. But to kind of give you that high level view, by now you must have understood that, hey, firstly, you can, with the components that we sort of spoke about, you can do a lot of nonlinear data processing. And Vishal, to your point, the reason why we would want to add the activation functions is to capture nonlinearity. Without activation function, you're essentially training a linear regression problem. So the activation functions give you that nonlinearity, the ability to capture nonlinearity. So organic learning, because the learning process is very, very similar to like how the to let's say how a human brain typically captures these patterns. And secondly, there's a very, very robust approach towards generating features internally. Remember we spoke about that. You can sort of generate features internally by adding multiple hidden layers and everything. So that kind of adds to the whole complexity of the model and helps us capture more complexity. Fault tolerance, the reason why we're saying it has sort of a fault tolerance is because there are certain techniques when we talk about, let's say, retraining, or rather when we say that we'll probably go back and update the weights. So this process of going back and updating the weights is actually pretty good, because we're simply not saying that, hey, we'll start with a set of weights and then we'll stop there. Rather, what we're saying is that we're going to run this multiple times until we get to a certain level of error, until we reduce the error to a certain extent. So that's the whole point of fault tolerance, because there is fault, but then I think the best part about that is you have an internal way of sort of repairing that particular approach as well, just like how a human brain works, so to say. So these are like broad brushstrokes of the benefits of neural networks. Of course, the benefits are like way too many. These are just a few ways of sort of representing the benefits. Cool. Now comes the actual part, right? Great. Now that we have these components, we've like at a 10,000 feet level, we've understood what is a neural network. We know what are the components that go into a neural network. By now, you guys must have understood that this is not some kind of a sorcery. We are not doing some kind of a magic here. It's not that deep learning models are any different from, let's say, your traditional ML models. Deep learning models are very, very similar to the traditional models. In fact, to train a deep learning model is actually more difficult because of the kind of complexity that you have. There's too many things that you have to manage. So don't expect the platforms to sort of take care of everything for you. At the end of the day, there is a lot of scope for a data scientist to pick the right choices from his or her side as well. Picking the right activation function, picking the right architecture of your deep learning network, and whatnot. So what that leaves us with is, okay, this is all great, but does it mean I'll have to write code for all of this every time? Does it mean I have to actually create a graph and everything? The answer is, well, you can, but then it's going to be extremely time taking. So there are a few pre-built libraries that we have, like what you see on the screen. These are few of the many libraries that are there outside today. For all you know, these are not the only libraries. These are the popular libraries, let me put it that way. These are like, I'll probably say the most popular libraries what you see today. And again, even within these, what we are currently observing is that there are sort of two libraries which have two deep learning frameworks which have become more popular over the last few years. One of them is called is TensorFlow, and the other is PyTorch. They've sort of become super popular over the last few years. And of course, TensorFlow has the advantage of a head start. TensorFlow was one of the first movers into this field. TensorFlow is from Google, and they are the ones who actually, for the first time, implemented deep learning frameworks, and they've open sourced it for the larger audience to use. On the other hand, PyTorch is from Facebook, and they've open sourced their deep learning framework that was built internally. So similarly, a lot of these other frameworks have come from different organizations. Keras is again an open source. These are all open source projects. Um, Interestingly, even NVIDIA has their own deep learning framework, um, and they're all super complex, super useful to use. Right now, TensorFlow and PyTorch are the ones which are really popular. So TensorFlow is, like, as I said, the open source software library for numerical computations. They're not only for deep learning. I mean, I think for any kind of numerical computations, TensorFlow has become like super popular. Yeah, I mean, these days you can do anything with every library. NL, natural language processing, classification, forecasting, object detection, computer vision, everything is possible using every library in some form or the other. There are two really cool functionalities from TensorFlow, and one of the reasons why TensorFlow has become so popular is because TensorFlow is built for enterprise grade solutions. It is not just built for research level solutions. It's actually an enterprise grade. It's not like R. Let's put it that way. R is not built for enterprise grade applications or solutioning. Python is slightly better at it. R was never built for it. On the other hand, TensorFlow is not like that. TensorFlow was built primarily with the outlook of not just TensorFlow. As a matter of fact, all the other libraries that we're talking about, they're all built with the outlook of making these models operationalizable. So, like, for example, you have like these two plugins from TensorFlow called TensorBoard and TensorFlow Survey. TensorBoard is like, imagine you have like a complex neural network and you want to understand what are the values inside a particular node, what are the values that are going from one node to another node, what are the weights, what is the error like. So you would want to, let's say, dig into more details of the neural network that you've built. You can use TensorBoard. If you have time, we'll probably try and explore TensorBoard in our session sometime. TensorFlow serving, on the other hand, is basically a web service, a web framework that is provided by TensorFlow to operationalize TensorFlow models. Majority of these libraries are all libraries for Python.
Just a quick info, guys. Test your knowledge of AI by answering this question. What are the main goals of AI? A. Create expert systems. B. Implement human intelligence in machines. C. Both A and B option. D. None of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Majority. That's essentially why I'm saying majority. Like, for example, DL4J is deep learning for Java, right? So that's what DL4J stands for. So majority of these libraries are based on Python. TensorFlow is based on Python. So TensorFlow is not another tool. TensorFlow is essentially a library in Python, just like how a scikit-learn is. Similarly, Keras as well. So the thing about Keras is Keras A is like a deep learning framework, and Keras is also a high-level API on top of TensorFlow. So, for example, what I mean by that is So you have, let's say, TensorFlow, and let's say you have Theano, CNTK. These are all different, libraries that are available, and Keras sort of sits on top of this. So Keras is like a high-level API on top of Theano, right? Ideally on top of Theano. Originally, it was built for Theano. Theano is another deep learning framework. These are all DL frameworks, DL libraries. So if you want to just work with plain vanilla Keras, then you're essentially building deep learning models using a framework called the underlying framework called as Theano. But then what these guys have done is the folks who've actually built Keras, they've become so smart. They said, okay, they've sort of separated this out very well. So they've seen that, okay, there is a lot of traction for TensorFlow, and there's other libraries coming through. Like for example, there's something called a CNTK by Microsoft. This was for Microsoft. So Keras sort of became that high-level API, wherein they said that, you know what, you can just write your code in, you can just write your code in Keras. So don't worry about what the underlying framework is. You just write your code using the Keras API. We will take care of which one. You can simply switch, saying, hey, look, I want to work with TensorFlow, or you can switch to Theano, or you can switch to CNTK just by changing one simple parameter. So your code will remain the same. If you simply say, I want to work on TensorFlow, or you're going to say, I can work on Theano, or you can work on CNTK. You can do whatever you want. So the moment Keras came up with that cool functionality, people realized that, hey man, this is really awesome. So people started using Keras because like Keras is like super easy to write deep learning code in. That means to build a network, it's like very, very easy using Keras. So suddenly what happened is TensorFlow was very popular and Keras became very, very easy to code. So people started to use this as a combination. So this combination of Keras plus TensorFlow became super popular. So right now, when somebody says I'm working on TensorFlow, most people are actually working on TensorFlow via Keras. So the combination of Keras and TensorFlow has become like super, super popular. Most folks today, they work on Keras using TensorFlow as the backend. And the good part is that what people have very, very often mentioned is that, working with TensorFlow is like super difficult. At least the version 1 of TensorFlow was like super difficult. The version 2 has become much more easier. But working with Keras and TensorFlow together has become like super, super easy right now. So we will realize it when we actually start writing code that it's not very complex. It's not all that complex. So what we are going to do in our session is we're going to do a lot of Keras plus TensorFlow combination. You'll see that a lot of implementations are basically a Keras plus TensorFlow combination, and it's not just in our session. In general, also Keras plus TensorFlow as a combination is like super popular, even in the market out. Okay, cool. So yeah, I mean, Keras has, as I said, recurrent neural networks and convolutional neural networks. Again, same stuff. Whatever TensorFlow can do, even Keras can do the same thing. The beauty about Keras is that the way you write code is that you kind of stack one layer on top of another. So you build like your first layer, the input layer, then you build your first hidden layer, then the second hidden layer, then the third hidden layer, then your output layer. So you define each of these layers separately, and then you sort of combine all of them together. As simple as that. That's basically how your Keras typically works. So that's essentially what they mean by stacking layers one on top of another. PyTorch, on the other hand, has started becoming very, very popular over the last 1.5 to 2 years. Let me be very honest. Today, PyTorch is giving a nice run for the money for TensorFlow as well. Today, there's a huge community for PyTorch as well, and apparently PyTorch also is pretty good, pretty easy for us to sort of learn and start going. Now with so many libraries coming in, the question is which one should I learn? Now I don't think the question should be which one you should learn. because there are so many frameworks, by now you must have understood that these are all just frameworks. This is code at the end of the day. If you understand the underlying math, and if you understand how you can implement with one of the frameworks, you can comfortably implement the same using uh, using other frameworks as well. So I don't think the question should be, should I learn PyTorch or should I learn TensorFlow? I think the question should be, how do I learn deep learning? Can I implement deep learning using PyTorch, or can I implement deep learning using TensorFlow? The answer to both the questions is yes, you can. Pick any one and learn it. And once you learn it, and then you can always switch between these frameworks as you go. So suddenly you might start working on a project where you're required to use PyTorch, or maybe the other team members are very proficient in PyTorch, so you might have to learn PyTorch. But it doesn't matter. At the end of the day, you have to start somewhere. And I think TensorFlow and the Keras combination is actually a tried and tested combination. PyTorch is very new in the market, new kid on the block, very, very promising kid, a very, very promising framework. So if you have some time later on, please feel free to pick that up as well. But yeah, I mean, if you honestly ask me, should you learn everything? The answer is no. There's no point in learning everything. Just pick one framework and just go through it. Go through one pass of it, you will understand how to implement. Once you're sort of confident of implementing it once, you can always switch between frameworks. It's not really that big of a deal. Oops. So the next is, of course, DL4J, deep learning for Java. This is surprisingly, this is a deep learning framework for Java, and this is quite popular in the Java world. I mean, for ones who coming from Java world, who want to sort of implement this, you can comfortably implement it using Java. It's quite popular as well. The other cool thing about the reason why this is sort of become like super popular is because when you're working with Spark and when you're working on Hadoop, because the underlying framework of Spark is all JVM based, it's all Java based, that's where DL4J took off. That's where deep learning for Java became very, very popular, because Spark under the hoods is all Java and Scala. It all runs on JVMs and runs on Scala. And DL4J is a deep learning framework that is built for Java. So it became super easy for them to adapt DL4J to work on a distributed computing framework. So you could sort of use it for Hadoop or use it for Spark. So DL4J runs really very well on any of these if you want. Prem Sundari, yeah, deep learning library and framework is the same. This is much more than just a library. I don't want to call it a simple library. This is a framework. The reason why we're calling it a framework is because it kind of gives you a structured approach towards building models. It's not a simple function. A library is a combination of a few functions. This is not just simply a function. Like, for example, in the case of a decision tree classifier, it's a simple function or a method. You just apply it and then you get going. But here, that's not the case. This is the reason why we call it a framework, is because it kind of gives you a combination of approaches towards solving a problem. Scikit-learn, you can call it a library, but essentially it's an ML framework as well. Scikit-learn also in some form or shape is a framework, because it kind of gives you the complete suite of solutions for machine learning in Python. Calling it a library is probably a very technical term from a Python way standpoint. The reason why we call it a framework is because it gives you much more than just functions. It gives you functions, but along with it, it also gives you an approach towards, okay, so when you're building a solution, along with this solution, also apply this particular method. So it's a combination of methods that you'll always have to apply to arrive at an outcome. Yeah, I mean, it's not a collection of packages or a libraries, Priyanka. It's one library. When you do an installation, you would see it, right? You would essentially have to do conda install TensorFlow. One library. It is one single library only. It's not like many libraries. A framework, because you're essentially doing much more than just applying a simple function. And I want you to just understand that, because deep learning is not just as simple as just calling a simple function. Cool. Yeah, and the other one is MXNet. Somebody asked me, how can I implement deep learning in R? So here you go. MXNet is one way of applying deep learning in R. But I'll be very honest with you. Somebody who's asked me, what should I do for R? I'll be very honest with you. I think applying deep learning in R is, I think, I think the ship has sailed for R. To be very honest, I think the ML ship has sailed for R. I don't think there's any point in focusing on R, to be very honest, because as a programming language, R has really fallen has fallen behind by a few, almost a decade now. So I don't really see R becoming like another tool where where you could start applying other complex approaches. You can try, but for experimental purposes. But I think the ship of R has sort of sailed. Right now, the focus is on Python and significantly on Scala as well. So yeah. I mean, again, as I said, MXNet also you can do the same things. You can apply do computer vision, that's imaging, natural language processing, forecasting, speech recognition, whatnot. You can essentially do everything. All these libraries in some form or the other give you the capabilities to do almost everything. If you sort of draw a Venn diagram, almost everything overlap on top of another to almost around 70-80%. There'll be probably some stuff which is very specific to a certain library, but net all libraries in some form or the other have the same approaches. So let's talk a little about TensorFlow, because that's going to be our primary tool of choice or primary. I think it's important to understand why do they call it TensorFlow, and firstly, what do you mean by tensor, right? We must have heard of a scalar and a vector. Tensor is something very similar. A scalar is a single number. Vector is an array of numbers. Tensor is basically, think of tensor as a slightly more complex, a generic representation of the same thing. Yeah, let's say a tensor can be a single number, a simple scalar, or a vector, or it can also be, let's say, a matrix of numbers, or it could also be, think of it as a cube, right? A three-dimensional array of numbers. That is also a tensor. So these are all different tensors. In the case of a tensor, you don't have direction, you just have magnitude. In the case of a vector is a two-dimensional array, rank 1. We call it as a rank 1 because it has only one single dimension. Values just move in one single dimension. In the case of a matrix is two-dimensional, or the rank is 2 because you have rows and you have columns. And in the case of a tree tensor, all these are tensors. They're all n-dimensional arrays. So popularly, the three-dimensional tensor is something that has, think of it as a three-dimensional. Think of it as a cube. Yeah, think of it as a cube. You have different values. So you have rows, columns, and you also have depth. Right? X, Y, Z, all three dimensions is what you have. So to represent a particular number, that's essentially a tensor. So in the case of neural networks, what you would observe.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
Is that tensors are like really popular ways of referring to values. We don't call it a vector or a matrix, because if you start referring to something as a vector, something as a matrix, then it could get too confusing. So tensor is like a generic word that people use to sort of represent any kind of an array in general. So a tensor with two dimensions is basically a matrix. A tensor with three dimensions is, let's say, a 3D array, or a three-dimensional array is a three tensor. A tensor with one dimension is, let's say, a vector. A tensor with no dimensions is a simple scalar. That's what a simple tensor is. Tensor is like a generic term for everything else. And the other point also is that these frameworks, all these deep learning frameworks, one of the things that is very, very common in all of them is they all work on computational graphs. And when we say computational graph, basically it's basically like representing a simple mathematical computation as a graph. So as you could see here, in this case, A and B are two values, and they sort of flow into a particular mathematical operation. And then that flows into another mathematical operation, and there's another input. And then the output is basically H. So if you see, if you kind of convert this whole mathematical operation into this whole thing into a into a mathematical equation, it sort of becomes AB, right? Because we're essentially multiplying these two. So AB, and you're adding C to it. So AB plus C is what is H. So anyone quickly, what's the outcome here? A into B is 200 plus 30, 230. That's the basic outcome in this particular case. In the case of your TensorFlow, we call each of these computations as a computational graph, and each computation or every computational graph is executed inside a particular session. So it's called basically like a session. So every computation, this is a computation, and this computation is happening inside this particular session. For jargon's sake, it's not something that we should really worry about. But what we are saying is that all computations, when they happen inside a particular session, they have how the values can be they can be used internally. Across sessions, variables are not shared. Inside a session, variables are shared, or variables are accessible to each other. Across sessions, variables are not accessible. That's basically what you mean by session. So yeah, a node is a mathematical operation. Like for example, this is a mathematical operation, this is a mathematical operation, and the values that basically get passed, they are all tensors. So this is a tensor. Like for example, this is a tensor, this is a tensor, this is a tensor. These are all tensors. Popular programming elements in TensorFlow are you have something called as constants, placeholders, and variables. Constants, as you wanna are constant values, something that doesn't change. Placeholder values are values which are typically going to get assigned during an execution. They are like arbitrary constants. They're placeholders, as in they are not really, you know that there's a value going to come in there, but it's just that you haven't assigned any value to it right now. So the value gets assigned during execution. And a variable is, again, you simply say X or a Y. These are simple variables that you have. So we'll look at how they are very different as we go along. Like for example, in this case, constants are program elements whose values do not change. So you simply say tf dot constant of 10. As simple as that. Placeholders, on the other hand, placeholder are, you simply say that, hey, look, there's a value that's going to come into it, but this value will come in at a later point. You're saying that there's a value that's going to come, but this value will come in at a later point. They are also actually a form of a variable only, but it's just that you're defining what type it is going to be. You're saying, hey, this is a placeholder, and expect a float 32 value coming through, or expect a string value coming through into this. Right? You're saying X and Y, and you're saying that expect a float or a string value to come through. So you're calling this as a placeholder value. So you're sort of booking that slot and saying this is what is going to come through. Then you have an actual variable, right? In this particular case, you have an actual variable. So right now what you're saying is that W in this particular case is a variable. So like for example, right now T is called tf dot variable of 3 and tf float 32. What you're saying is that right now the value is 3. I can change this value later on. I can change this value to something else. Currently, the value of this particular weight is, or this particular W is 3. It can become something else later on. These values can change as they go along. That's what a regular variable, just like how we all know what a variable is. Let's quickly do a small, I just wanted to kind of show you how the whole variable things work, and then we'll dig into more depths. It's not that I want to kind of start using them right now because we really don't know how to use a TensorFlow library, but I just wanted to introduce you to those constructs. Yeah, okay. So if you see, my TensorFlow is now up and running. So I've done an import TensorFlow as TF, and as you can see here, if you observe here, I'm essentially creating these as constants. Right, I'm just constant 1, tf dot constant of 3, 3.5 Sparta, and then false. So these are our different constants that I'm assigning. And as you could see here, when I print what these constants are, tf dot tensor, this is an int32, tf dot tensor 3.45. There is no shape. Observe that there is no shape because these are single values that you see over here right now. If, for example, you do something like this, right now, if you observe, the first one is tf of tensor 1, 3, because I have two values and the shape is 2. 2, comma, just like your Python tuples. So 2, comma essentially means it's one-dimensional array, right? And if, for example, if I pass this as a list of lists, then this will automatically be a tensor 1, 3, 3, 4. The shape is 2 by 2. Simple, pretty straightforward, nothing very complex, just like a NumPy array, two-dimensional NumPy array. This is also a tensor. It's just that this is again shape of 0. I mean no shape because it's a scalar in a way. Same is the case with the others as well. This is Boolean type. This is string type. Yeah, I mean. Just give me a second. Seems to be throwing some error. So basically, I've ended up installing a version 2 of TensorFlow, and that's essentially the reason why supported in the long term. TF. There you go. So yeah, right now what I've done is I've just created these 4 constants and I've just said session.run. But then I've essentially wrapped them inside a list, and I've asked it to simply do a run. So it has returned a list of all these values, nothing else. But look at this here. So I'm defining 2 methods over here, or 2 graphs. Think of these as 2 computational graphs that I'm sort of creating here. And I'm calling something called as addition, and I'm calling it as multiplication. And I'm doing a session.run, and addition and multiplication have simply been returned. So this is basically 50 plus 10 and 20 plus 20. 20 times 20, it has simply returned a value, as you can see over here right now. Now, the thing here, of course, is that when you talk about the same, similar stuff over here as well, as you can see, I'm just passing a couple of lists over here. These are 2 tensors with dimension 1, 2 constant tensors with dimension 1. And what I'm doing is I'm simply adding them, and I'm simply multiplying them. And as you can see here, the values are simply being returned as, as simply the multiplications of corresponding values. 1 into 5, 4 into 2, 3 into 3, 4 into 2, and 1 into 5 again. So it's simply corresponding value multiplication. Essentially, 2 vectors are being simply multiplied right now. That's all that we see in this particular case. Nothing really out of the world. Here is where the interesting part comes in. Now I'm defining, let's say, 2 string values, as constants, and I'm just running an addition on top of it. As you can see, a string addition, string concatenation typically takes place. Same stuff. Now here's where I'm defining a placeholder, right? Defining a placeholder right now. So when I define a placeholder over here, I'm saying A, expect an int 32 value to come through. And now I'm saying B is equal to A into 2. Right? B is, let's say, another outcome. B is now, let's say, the output of A, whatever this A into 2 is. I'm saying B is simply nothing but A into 2. Oh, so this B is just Unicode, guys. Yeah, okay. It's just saying it's a Unicode text. That's what it is. Again, so here if you see B is equal to A times 2, and I'm simply saying A session dot run. I'm saying run this particular thing, but along with it, what I'm also saying is that I'm saying assume the value of A as 10. Remember, A is a placeholder value. So I'm assigning the value of A during the execution. The value of A is, in this particular case, is being applied during execution. So when I run this, the value of A is assigned as 10, and the value of B is computed as 10 into 2, and the value is returned as 20 in this particular case. That's the beauty of the placeholder value. Again, if you ask me what is the value of A right now, the A value is still a placeholder. It is still an empty value. There is nothing inside it right now. It is still a placeholder value. It only assumes the value of A as 10 in the execution of this particular session. Yeah, when you run this, what essentially it is doing is it is simply executing B. B is simply nothing but a multiplication of A and 2. A value is 10, so it is simply running the value of B and returning the value of B. So in this particular session execution, the value of B is 20. That's all that it returns. I'm simply asking it to return B. Right. So when I say B plus B, it'll return it as 40. So it is executing this. I hope that makes sense. So it is simply executing this particular piece of code that you see. But when it has to execute this, it needs what the value of A is. So if, for example, if I don't pass this, it'll throw an error, invalid argument error. It says you must feed a value for a placeholder, tensor placeholder with type 32. Right. So I'm just going to pass that, and when I pass it, it just simply gets executed. Okay. Same thing here as well. Again, I've assigned this as a placeholder value. Same thing, I'm executing name1, and I'm saying for this particular execution, assume the value as Sam. Okay, that's it. So now look at this here. Again, I'm saying variable 1 is TensorFlow dot variable of 30. This is a variable now. Global variables initializer. This is basically simply initializing all the variables. This, what it does is whatever the variable I've assigned, it assumes, it basically initializes that particular variable. It runs the initializer first, and then the variable 1 is sort of available for me everywhere. Moving forward, the variable 1 is sort of available for me everywhere. You can ignore these two for now. Just don't worry about this as much, because in this particular case, I've assigned the variable and I'm trying to access this particular variable, but this particular variable doesn't exist because it is uninitialized, so to say. According to it, it is uninitialized. So one of the things that you need to do is you need to basically initialize your variables before you start using them. And the way you initialize them is by running those few lines over there that you need to initialize the global variables initializer, and then you need to run the session. Okay. Again, this is very fundamentals of very basics of TensorFlow. The default TensorFlow that is installed in my library, in my system, is TensorFlow 2. But then this notebook is available in your learning management system, LMS. Please visit your LMS, and then you will be able to access all of them there. Okay, great. Okay, now that we've sort of at a very very high level sort of got ourselves introduced to TensorFlow. Not that we know what TensorFlow is. It's just that we, at a very broad level, we sort of know what this TensorFlow is. What we are going to do moving forward is that we're going to start leveraging again these fundamentals, very very simple fundamentals that we just kind of that we just kind of learned right now, and then we're going to build on top of this. We're essentially going to start building neural networks. But of course, to start building neural networks, we need to know how to build a neural network in the first place. So right now, what we're going to do is we're going to go back to our fundamental concepts of neural networks, and we learn how to actually train a simple neural network, how to actually build a neural network. Forget about TensorFlow and everything. What we're going to do is we're going to first start to train a simple, very extremely simple neural network, like how you see on your screen right now. This is a very simple neural network, guys. Right? Simple perceptron. Right? It's a simple perceptron model, not multi-layer, a single layer perceptron model that we have currently. Okay. And essentially, this is basically like y is equal to w1 x1 plus w2 x2. That's basically what we're training over here. Something like this. So you have so what we're essentially training is you have 2 x1 x2 w1 w2 and this is y. That's it. There is just a summation over here, and there is basically an identity activation function. That means no activation function. So in this case, y is equal to w1 x1 plus w2 x2. That's all that we are training over here. Given a specific value of x1 and a specific value of x2 and a specific value of y, I'd want to find the corresponding values of w1 and w2 in such a way that my model gives me the lowest possible error. Right? Let's say the x1 value is 10 and the x2 value is 20, and the y value is, let's say, has to be 30. W1 and w2 should be 1 and 1 respectively.
Just a quick info, guys. Test your knowledge of AI by answering this question. Which of the following is not a stage of AI? A. Predictive analytics. B. Diagnostic analytics. C. Cognitive analytics. D. All of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
Nothing very complex, right? Similarly, if I want this to be, let's say, if I want this to be, this is 10, this is 20, and if I want this to be, let's say, 29.8385, then what should W1 and W2 be? God knows, we don't know what those need to be right now. Right? There can be any numbers. We can assume them to be something, and then we can basically you can assume some value of W1 and you can compute the corresponding value of W2 and all of that. But if you were to do it the actual neural network way, how do you go about solving this particular problem? So we're going to come back, and the aim is going to be for us to actually start to train this simple model. Yeah, this simple, very, very simple model that you see over here. So for example, x1 is 2, x2 is 5, and I want a y as 31. So in this particular case, I want to simply train a neural network model, and I want it to build until the error is 0. So if you see at this particular value of w1 and this particular value of w2, almost at this value of w1 and this value of w2, the error becomes 0. That's what I'm saying. Similarly, if I have a x1 is, let's say, 10 and x2 is, let's say, 20, and I want my output to be 30. This is different values that we've tried. We still haven't been able to completely come to a solution, but we have a framework to come to a particular solution in this particular case. So these are different approaches of coming to an outcome, guys. So like, for example, 1 and 1, you see, right at word go, you hit the 0 because you're initially starting your W1 and W2 with 1. So you don't really need to optimize any further. You started with 10 and 20 and your y is 30, and you're saying W1 and W2 is 1 by default. So the error starts at 0. But if, for example, instead of 1 and 1, let's say you started at 2 and -1, that's where things become a little tricky. So you have to keep trying until you basically come to a particular point where you see that the error becomes zero. So we keep running it. Let's say in this case, I've run it 50 times. I can run it 100 times probably, and I can hope that it kind of becomes, the error sort of becomes close to zero. Still, the error is -7. The error is actually extremely high right now in this particular case. Okay, let's take this simple use case, right? So it's basically as simple as saying, hey, look, right now I have like, I essentially I have an e-commerce firm. I have multiple ways of reaching out for my products, and right now I'd want to do that. I want to increase traffic. The end goal is to increase traffic. But then if I were to increase traffic, one of the challenges that I have is I want to do my marketing, but I want to do my marketing via multiple sources, right? Like for example, you can do it via email, direct, paid ads, referral program, social media, or organic search. You can essentially do this marketing via multiple ways. The problem here is that you can either use just one of the platforms for publicity or use a variety of them. You can basically use one of them or many of them. Basically, you can pick whatever. The point, of course, here is that you can right now, everything has its own advantages and disadvantages. Like for example, in the case of paid ads, there's money involved. In the case of referral programs, you have to reach out to existing people. For social media, you need to hire a digital marketing company. For emails, again, you need an email marketing team that can start doing it. So at the end of the day, you want to increase sales, but the thing is, you want to increase sales at the cost of there is some amount of money that you will have to invest into each of these different cases. So at the end of the day, if I were to sort of try and evaluate how much sales am I going to get based on the money that I spent on emails, or money that I spent on direct ads, paid ads, or referral programs, or social media, or organic search, what I need to do is, of course, upfront, I need to start projecting this. I need to make a projection. I need to make a prediction of saying, okay, if I invest X amount of money on email marketing, or if I invest X amount of marketing on paid ads, or if I invest X amount of money on, let's say, referral programs, how much sales am I going to get back? I need to make a prediction like that. I need to start making predictions of the sales that I'm actually going to get as an outcome, because I don't want to invest on everything. I mean, investing on everything is like basically burning money. So I want to invest in such a way that I can maximize my margins or maximize my sales in whichever form or shape. So to do that, one of the most important things that I have to see is I have to evaluate firstly which of these approaches gives me the most amount of benefit. Now, see, by the way, these are not the only ways, right? If each of these is, of course, again going to have its own subcategories. You will have multiple subcategories. You'll have multiple other ways of starting to market towards people. The point that I'm trying to drive here is when you're trying to solve a problem like this, right? If you think of it, it becomes like super difficult for us to sort of predict sales. And at the end of the day, I want to predict sales in this complete problem. I want to predict sales. So it becomes super complex because I have multiple parameters to look at. I have multiple inputs. I have money that is being spent on emails, referral programs, paid ads, direct social media, organic search. I essentially have multiple ways of targeting my customers and multiple ways of multiple ways of targeting my customers and of course driving sales. But at the end of the day, when I would want to solve, if it is, let's say, emails only, or if it is only referral programs only, then based on my historical data, I can tell you how much money to spend on referral program. Or if it is just direct media or direct marketing, or let's say if it is just social media, I can come up with some ways of based on historical information, I can make some kind of prediction using a simple linear regression or something. But when I have so many different parameters coming in and so much of interplay, like for example, your social media might also impact, let's say, your direct marketing, or your direct marketing may impact, let's say, your organic search, or social media may impact your organic search. So you don't know, and there's a lot of interactions that can happen between all of these as well. Like for example, somebody might get an email, but then they might some other time actually start visiting via some kind of an organic search. So there's a lot of interactions that happen between each of these features as well, or each of these inputs as well into predicting sales. So doing these predictions upfront on historical data with simple models is not possible, and that's exactly where we start requiring, the benefit of complex neural networks, or essentially your neural networks where you have multiple hidden layers in between, multi-layer perceptrons. That's essentially where your multi-layer perceptrons and your feed-forward neural networks are going to be coming very, very handy. Single-layer perceptrons are good enough for, let's say, a single, when I'm making a prediction of my sales just on the basis of one or two inputs. But when I have multiple inputs, that's where things get very, very challenging. And that's where you require more complex approaches to solve problems. That's where multi-layer perceptrons can become more useful. Yeah. So yeah, before actually, let's talk about your fundamental differences between your multi-layer, single-layer perceptrons and multi-layer perceptrons. We all know this. We don't have to sort of redo this thing time and time again. Single layer perceptron, of course, no hidden layers. Multi-layer perceptrons have more than one hidden layer. Except for one input layer and one output layer, there is at least one hidden layer. You have one input layer, one output layer, and you have at least one hidden layer in between. That's basically what is referred to as a multi-layer perceptron. Also, and if let's say this one hidden layer becomes, let's say, many hidden layers, 20, 30 hidden layers, that's when we start calling it deep learning models, because your network is like extremely deep. That's when we start calling it, instead of calling it multi-layer perceptrons, we start calling it deep learning models. And by the way, each of these nodes that you see here is a neuron. And when you talk about a neuron, you have multiple inputs coming into the neuron, because if you see, just take this particular circle that you see here, or this particular neuron that you see here, there are multiple inputs coming in. And when multiple inputs come in, what you do firstly an aggregation, and then you apply an activation function, and then you give an output. Same is the case here as well. You have multiple inputs coming in, you run an aggregation, you apply an activation function, then you return an output. So every neuron is doing this. Every neuron is simply nothing but one circle inside your neural network. So every neuron is performing an aggregation and applying an activation function and passing the value to the next layer. So there is some kind of computation that's happening at every neuron, some kind of information that is basically getting generated at every neuron. So think of these as signals. There are signals coming in, and based on multiple signals that are essentially coming in, what you're doing is you're passing a few signals, you're transforming a few signals, you're applying some kind of changes to a few signals, and then creating newer signals. And in combination, all these signals put together again will create another signal. So think of what simple input of signals can actually achieve for us at the end when you run them through a multi-layer perceptron. The point being that multi-layer perceptrons are actually pretty good. That's the point that I'm trying to drive here. Yeah, I mean, broadly speaking, this is like we've already spoken about this. For the sake of the slide, let's just go through this. You have an input layer, hidden layer, output layer, same thing. Yeah, this one point is that here, if you observe in this particular case, there's also a bias that's getting trained, just like your constant. If you observe, the bias term is 1, but the weight is W0. So I'm training W0 because there is no input coming through. The input is always 1. The input is constant. Just I'm training a W0. W0 is nothing but a constant. So W0 plus W1x1 plus W2x2. So W0 in this particular case becomes like your intercept. So the weight in itself becomes like your intercept or your bias or your constant value, so to say. 1 W0 plus W1x1 plus W2x2 becomes the value in here. Okay. Same here as well. Again, I'm training another bias term in this particular layer as well.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
Yeah, so this is all straightforward. Yeah, there's nothing really out of the world in here. We all understand this pretty straightforward. So going back to that solution, what is going to happen is that at the end of the day, I want to predict if somebody is going to make a purchase or not. Or I can also predict, I mean, in this case, there are two outputs. You can also predict, let's say, sales. You're predicting if somebody is going to make a sale or not, or make a purchase or not. Or you can also predict, let's say, one single neuron, the amount of sales. So all these go in as inputs, and these inputs essentially will then make one single prediction for you, which is, let's say, you're predicting the sales or predicting if somebody is going to make a sale or solve it as a regression problem or a classification problem based on the scenario. Here, let's take this another example. Suppose you have the following data set, right? Let's say you want to predict somebody's final results of, if somebody's going to fail or pass. 0 is essentially fail and 1 is basically pass. And I have this information, the amount of hours that somebody has studied and the amount of midterm marks that somebody has achieved. So I want, based on this information, I want to predict if somebody is going to make it through their final term or not. So in this particular case, if you observe, again, based on the input that we have, I have two inputs, are studied and midterm marks, and based on this I want to predict if somebody is going to actually make it through their final term or not, based on this information. Now, of course, I want to first learn that I want to learn the patterns that basically go through this. Firstly, this is what has happened historically. This is historical information that I see. I've captured this historical data set. But based on this historical information, what I would want to do is, if let's say there's a new kid who's studied for 25 hours and who has scored 70 marks in their midterm, I want to predict if the person is going to. I want to predict what is going to happen to this particular person. Pretty simple. This is a binary class classification problem where I'm trying to train my model on the historical data, and I'm trying to predict on this particular simple data set. That's all that I'm trying to do. Like for example, in this particular case, take this simple example. So what I have is, this is R studied and this is midterm marks. And let's say for whatever maybe the reason, I've decided that I'm going to go with a multi-layer perceptron that looks like this. And I have multiple weights, W1, W2, W3, right? 3 different weights flowing in from different directions. And of course, based on the weights that I have over here, it's not just W1, W2, W3. This is, of course, this is my bias. This is X1 and X2, two inputs bias. I'm going to have 1, 2, 3, 4, 5, 6. Essentially, I'm going to have 6 weights in here because I have 2 inputs over here, 3 inputs from here, and then 2 inputs in here. So I essentially will have 6 inputs, 6 weights. And what I'm going to do with these 6 weights is, based on some random values of weights, I'm going to make a prediction to start with. I'm going to start with some random values of weights and I'm going to make a prediction. Let's say the target value is 1 and 0. Let's say I end up making a prediction saying the value is, let's say, the probability of passing is, let's say I make a prediction of 0.4, and let's say I make a prediction of 0.6. The value that somebody would pass, the value that somebody would fail. Probability of somebody would pass is, let's say, 0.4. The probability that somebody would fail is 0.6. So whatever may be the reason for that particular student, 35 marks and 67. So if you go back to the historical data, 35 and 67 is the first kid. This person has actually cleared the exam. This person has actually cleared the exam. But we made a prediction that, from our model, we said that there is a 60% chance that he would clear the exam, and 40% or rather 40% chance that he would clear the exam, and 60% chance that he would fail the exam. So if you now look at it, there's a collective error that is associated to this particular model. I initially made a prediction. My prediction says that the person is only 40% likely to clear the exam. But if you compute the error, there's an error of around 0.6 error on this node and 0.4 error on this particular node. There's a significant amount of error in my model with my first record in itself. It's just simply this particular data point in itself. So now what do I do? My challenge right now here is that I made a prediction, but that particular prediction is incorrect. So now what I need to do is I need to sort of perform some kind of a correction to my weights. in such a way that my prediction gets corrected. So I can apply some kind of a change to my prediction. So that's change to my weights. So how do I change my weights? I'm going to perform these weight changes based on how much error is being contributed by each of these nodes. Based on how much error each of these nodes is basically contributing, that is the amount of correction that I'm going to make on those weights. Okay. So what does that mean? What do I mean by that? So when I say I want to make a correction, like for example, in this particular case, if I'm making a negative, if I'm basically getting a value of 0.4 over here, and if I'm getting a value of 0.6 in this particular node, the reason I have a 0.6 in here could be driven because of one of these three weights. Because I'm getting values from these three places, but one of the weights is significantly high, hence the value in this particular node is extremely high. So I have to reduce this and I have to increase this. For me to do that, I need to basically target that particular weight over here that is causing this value in this node to be very, very high. So I have to perform some kind of a magic over here, such a way that I propagate this error backwards into my network, especially in the direction where in that particular direction which is causing the model to make errors. Yeah, I have to pass that error back in such a way that I pass it back in such a direction which is actually causing that particular error. So that process of propagating the error backwards into the network in the direction of the error causing weight is what is referred to as back propagation. Right? So the back propagation essentially is there is an error that is at the last layer of my network. What I would want to do is I want to capture that particular error and then propagate that error backwards into my network and see which nodes are causing in that particular order, whichever nodes are causing the higher amount of error, I would want to pass the error backwards into my model. When I pass the error backwards into the model, firstly, I will know which nodes are causing higher amount of errors. Once I know which nodes are causing the higher amount of errors, then accordingly, I will change those weights to basically make sure that the contribution of those particular nodes or those particular weights is minimized in my final outcome. Yeah. So that process is what is referred to as back propagation and weight updates. Okay. So once I, let's say, perform that particular step, once I, let's say, perform the back propagation and once I do my weight updates, what is going to happen is, there is some math that goes on. We'll come to that math in a minute. But there is some amount of mathematics that goes in the background. And what that math basically causes is my errors now start to minimize because I have made some changes to my weights. The weights that were originally W1, W2, W3 or whatever have now become W4, W5, W6 because these are updated weights now. They are not the same weights. So these new weights, now if you observe, they are basically making a prediction that the person is now 80% likely to pass an exam and the person is 20% likely to fail the exam, which is much closer to what it was previously. Previously, we were making a prediction of 0.4% and 40% and 60%. Now we're saying 80% and 20%, which is much closer to reality because in reality, the person has actually cleared the exam. So now if you compute the error, which is 1 minus 0.8 and 0 minus 0.2, so the error is actually much lower than what it was earlier. Earlier it was 60% and minus 40. Now it is 20 and minus 20. So relatively the error has now gone down. But to again still perform the same step, to still make this model more better, what I would do is that I'll again perform the same step. Now I still have the error. I'll again identify which nodes are causing the higher error. So I'll propagate the error backwards and identify which nodes are causing the higher error. Now, until where am I going to propagate this error? Am I just going to propagate the error until the previous layer? No, I'm going to propagate the error all the way until backwards, all the way until the first layer. And then based on which nodes are causing the high error, accordingly, I will change those corresponding weights. Because when I change the weight, automatically the contribution of that particular node becomes smaller. The moment the contribution of that node becomes smaller, automatically automatically what will happen is that it will directly impact my outcome, and that way my outcome will become more closer to reality, more closer to the actual prediction. But what we did to the exactly, so the Prashant, that's exactly where I'm going to come to. What we did to the final to actually update the weights is what we're going to talk about in a minute. I'm just kind of telling you the life cycle of this particular problem, right? So we'll talk about the back propagation right now, right? So I make a prediction, the prediction is incorrect. I want to basically pass this error backwards all the way until the beginning. But how do I do it? Right. So let's take a simple example. Let's not worry about all of this as much. Let's actually talk about, let's take this simple network. Let's start working with the actual data in itself. Okay. So right now what you're seeing in this particular case is you are seeing two inputs. Actually, let me actually copy this. So yeah, this is our network, right? These are my trainings. Training data is, let's say, 0.5, and my 0.5, 0.1. 0.5, 0.1 basically meaning the input 1 and input 2 are 0.5 and 0.1. The weights are like how you see here right now, the 0.15, 0.2, 0.25, 0.3. So these are the weights like how you see the way they are right now. And what you also see in this particular case, you also basically see is that the biases are 0.35. That means bias contribution of weights is both 0.35 and 0.35 in both cases. Similarly, 0.6 and 0.6 in both cases. So you have the weights and everything. You have the network. H1, H2 is the hidden layer. O1, O2 is your output. And what you're saying is for an input of 0.05 here and 0.1 here, the actual output should be 0.01 and 0.99. That is what the actual output should be. For 0.05 and 0.1, we want the neural network output to be 0.01 and 0.99. Now, of course, two steps, forward pass and the backward pass. Forward pass is where you actually go through and compute the error and see how bad the model is or how close it is to the actual predictions, the actual values, and then compute the error and pass that error backwards into the network. So what's going to happen right now? By the way, the other point that I forgotten to mention over here is that the hidden layer has a sigmoid. Let's say we're applying, let's say, a sigmoid activation in the hidden layer. Let's say we're applying some kind of a sigmoid activation in the hidden layer. Okay. So the first one is the forward pass, right? So if you look at the H1, this is why I kind of copied this here. Yeah. So right now what you observe is here is that you want to compute H1. H1 is nothing but this value. H1 is nothing but, if you observe, it is I1 into W1 because you have a line going from I1 to H1. So I1 W1 plus I2 W2 plus B1. So it's I1 W1, I2 W2 plus B1. That's exactly what we're saying. So I1 W1, I2 W2 plus B1. That's what we're seeing. So I1 W1 plus I2 W2, I1 is 0.15.
Just a quick info, guys. Test your knowledge of AI by answering this question. What are the main goals of AI? A. Create expert systems. B. Implement human intelligence in machines. C. Both A and B option. D. None of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
And W1 is 0.05, I2 is 0.2. Sorry, W2 is 0.2 because W2, this line is 0.2. And then the value is 0.1. And then we have B1, which is 0.35. So the value is 0.3775. That's essentially what we get here as H1 output. So the H1 output is 3775 in this particular case. So W1, W2, W3, W4 So these are the values that you see over here. Okay, brilliant. Similarly, this is the value at h1, but mind you, that's not the output at h1. That is the value which is computed. The half of h1 is that, but the output from h1 is going to be a sigmoid transformation. Remember, I'm applying a sigmoid transform. So all that I'm going to do is whatever is the net h1, which is 0.3775, I'm simply going to apply a sigmoid transform. The moment I've applied a sigmoid transform over here, the value simply become 0.59, because 1 by 1 plus e to the power of minus 0.3775, it is 0.59. So the output to H2 carrying out the same process for H2. Similarly, even if you compute the same for H2, if you want to simply do the same for H2, you can actually do it for H2. H2 is going to be same one. So W3 H2 plus, sorry, similarly for H2 you have values coming in from here and here. So it is going to be I1 W3 and I2 W4. It's going to be I1 W3 and I2 W4 and plus B1. Or rather in this case plus b1. It's simply b1 because it's the same value that's going to come through in this case. So if you do the same computation and then you apply the sigmoid transformation, the output of H2 is going to be 0.5968. 0.5932 and 0.5968 are the values from output of H1 and H2. So the values that are going to come out from H1 and H2 are 0.5932 and 0.5968. Now comes the next step. The next step is another pass. Is another forward pass. The forward pass is where I'm going to pass the value of H1 and H2 and then compute O1 and O2. Great, let's go ahead, let's do the same. So if you do this here, net O1, again, so net O1 and out O1, same process. So W5 into O1, W5 into H1 that you see here, and W6 into H2, W6 into out H2, same values. So 0.5932 into 0.4 and 0.45 into 0.59. 0.45 into 0.59 plus B2. This line, you also see this line going through it. So this is B2. B2 is 0.6, 0.6 into 1 because the value is by default 1 here. So you have 1.1 and then you again apply a sigmoid transformation because again, even the outside layer is also a sigmoid transform. This is a classification problem. So the outer layer also is applied and we are also applying a sigmoid transformation here. So when you perform a sigmoid transformation, again you get a 0.75 at the end. Same for out 2, it is 0.7729. Yeah. So right now, forget about everything else. We're not applying any kind of softmax or anything. We just applied a sigmoid transformation. Forget about doing softmax or anything, just for simplicity purposes. Ideally, what should have happened is we should have applied some kind of a softmax. If it is a classification problem, we should have done some kind of softmax at the end to sum up the values to 1. But that's okay. In this case, we're not doing anything. We're solving it something like a regression problem, so it's okay. Let's not worry too much about it. So you have output 1 and output 2. They are supposed to be 0.01 and 0.99. We've got output 1 as we've got output 1 as 0.75 and output 2 as 0.77. Nowhere close to what they're supposed to be. Yeah, nowhere close to what they're ideally supposed to be. So now what do I do next? I made a prediction with the current weights, and mind you, these weights that you see are randomly initialized. They are not initialized with any rocket science. They're randomly initialized. Okay, so now there is an error. Then the error that we are seeing, if you were to compute the error, is, if you observe the error, the way that we are computing this particular error is we are not simply computing a actual minus predicted value. We are doing a mean squared error. Look at this. Mean of the squared error, actual minus predicted whole square divided by 2. Right? So 1 by 2 into actual value minus predicted value. So error at O1 is going to be whatever was predicted at O1. O1 was 0.75. So 0.75 minus 0.01, the whole square divided by 2. We don't care even if there is a 2 or not. There's no 2, it doesn't matter because this is just a constant anyways. So 1 by 2 into 0.01 minus 0.75, the whole square. Similarly, at error at O2 is going to be 0.99 minus I think that was also 0.7513, 0.77. 0.99 minus 0.77 the whole square divided by 2. Same error. And this is 0.27. This is 0.023. This is relatively smaller. The error in this particular case is much smaller because this is for O2 the value is actually much closer than O1. The O2 value was supposed to be 0.99 and we made a prediction of 0.75. So the O2 value is much closer than O1, hence the error contribution via O2 is much smaller than O1. So the overall error is a summation of these two, which is 0.29. Right? The overall error in this particular case is 0.2983. Great. Wonderful. Now what do I do from here? Now what we do from here is I need to pass this error backwards into my model. So when I say back propagation, I'm not going to literally pass the error back, but what I'm going to do is I'm going to pass this error back in such a way that I'm going to pass it more towards the nodes that are contributing to the error most. Now comes the tricky part. So now what I'm going to do is I'm essentially going to find a way to pass this error backwards into my model. Now you tell me, we've been doing all this computation, right? You tell me, between O1 and O2, which is contributing to the error more? Is O1 contributing to the error more or O2 contributing to the error more? Yeah, O1 is contributing to the error more because O1 is much far away from the prediction. O2 is much closer to the prediction. Clearly, see, O2 is 0.023, O1 is 0.27. So O1 is contributing more to the error than O2. So what that means is whatever correction that I have to make, the correction will have to be primarily in the O1 direction because O2 is okay. O2 also I will have to make a correction, but the correction that I have to make on O2 side is going to be much smaller than the correction that I'm going to make on O1 side. O1 I'll have to make a drastic or rather larger change on the O1 side than on the O2 side. That's the exact mindset that we're going to carry from here. Right now you're able to say that O1 is contributing more error than O2 because the numbers are pretty straightforward for us to understand. The moment I say, okay, now we've decided that O1 is contributing more to the error. So now between H1 and H2, that is contributing values to O1, which of these two is contributing more? Is W5 contributing more error or W6 contributing more error? W6 has a higher weight, but is W6 actually contributing more error? That depends on what are the values of H1 and H2. Because we need to go back and check what are the values of H1 and H2. Because net output of H1 is 0.3775 and net output of H2 is 0.59. Also, the H2 weight is also very, very high. So between W6 and W5, the error contribution by H2 is actually much higher than H1 towards O1. Does that make sense, everyone? So what I will have to do is between W5 and W6, W6 will have to be reduced significantly than W5. For us to individually track each of these weights all the way until the back, imagine how complex it could get. I mean, if you were to manually do it and individually do it, it will be super complex. So, and you're like spot on. So right now it is like just one hidden layer, so I'm able to do it manually. But what if I have, let's say, like 20 hidden layers or 10 hidden layers, and in each hidden layer, if let's say I have like 40 nodes and 20 nodes, then life's going to be like super difficult because I cannot manually track them down. That's exactly where we need to take the help of math, right? That's where we need advanced mathematical concepts. That's exactly where derivatives come into picture. What derivatives and derivatives give you is partial derivatives basically give you the gradient or rather the contribution of the impact. So when I take the gradient at O1, gradient of error at O1, it will show that the contribution of W6 is much higher than W5. Similarly, when I take the contribution of H1, it will say that W2 contribution is much higher than W1. So the point simply being that when I start taking more and more when I start bringing in concepts of derivatives, and when I start bringing in concepts of computational graphs, things can become much more easier to handle. We can start representing all of this as mathematical equations, and that way things become more easier. Computationally, they become easier, not from an understanding standpoint. Understanding standpoint, things becomes a little more complex for us. But computationally, things become easier. Let's actually look at it. Let's actually look at what we are doing here. Cool. So I just hope before we get into the actual math, I just want your intuition to be at the right place. Intuitively speaking, we are going to go back and correct those weights which are contributing higher. That's the sole purpose of this exercise. Now we've computed the complete error. Now comes the actual part. So let's take this O1. Let's take O1, right? There is an overall error. This is basically an enlarged diagram. So the diagram that you see in this slide is essentially an enlarged diagram of the O1 neuron that you see here. So if you see, there is a total amount of error, and that error is contributed by firstly O1, and O1 is basically contributed by net O1, because net O1 is simply nothing but, again, which is contributed by W5, W6 and B2. So if you think of it, what is causing what? Even if E is high because O1 is high. O1 is high because net 1 is high. Net 1 is high because net of O1 is high because either W5 or W6 or B2, one of these is high. So I have to start tracking back what is causing this error, and that's essentially what backward pass is going to be all about. So the way that I'm going to look at it is, at the end what I want is, I basically want how much is E, what is the rate of change of error with respect to first W5, what is the rate of change of error with respect to W6, and what is the rate of change of error with respect to B2. Yeah. So what I want to understand is, between W5, W6 and B2, I want to understand what is the rate of change of error. When I say rate of change of error, that means which of these weights is actually contributing the highest. Okay. So when I say rate of change of error, it's typically represented by a derivative. So what I'm saying is that I want, in a lot of ways, what I am essentially asking for is, I'm basically saying, so we've computed an error over here, right? So this error term, I want to compute. So DE, D or dou doesn't matter. Dou is basically a partial derivative because there are multiple things that are coming through. I cannot make a complete derivative. So I'm going to simply say dou E by dou W5 is what I want to compute. Similarly, dou E by dou W6 and dou E by dou B2. So the error contributed by W5, error contributed by W6. Let's for the moment, let's not worry about this too much. The computation of this is very similar to the other one. I want to compute dou E by dou W5 and dou E by dou W6. But you have to remember something, that if you look at that diagram previously in the previous slide, dou E by dou W5, if I have to compute dou E by dou W5, I cannot compute it directly. So the way I'm going to compute it is, A is first directly dependent on O1. So what I'm going to do is, I'm going to make use of a concept called as chain rule in differentiation. Simply put, what I'm saying is that dou E by dou W5, or the rate of change of error with respect to the W5 weight, is nothing but rate of change of error firstly with respect to output of O1. So I'm going to say simply out O1 multiplied by rate of change of error at output O1, rate of change of output O1 with respect to net O1, because this is changing as a dependent of net O1. Okay.
Okay, guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
So then this is going to be dou output O1 divided by dou net O1, similarly multiplied by dou net O1, or rather dou net O1 by dou phi, dou net O1 divided by dou W phi. That's essentially how I represented the whole thing. This is basically from a concept called as chain rule in mathematics, in differentiation, partial differentiation. If you're not fully aware, it's okay. All that I'm simply saying is that, hey, look, I want to compute how badly the error is being contributed by W5. Similarly, I want to compute how error is being contributed by W6. But how do I do that? The best way of doing it is I compute dou E by dou output O1, dou output O1 by dou net O1. So I want to identify how output is getting contributed by net O1. Then again, similarly, how net O1 is being contributed by W5, or how net O1 is being impacted by W5. And when I multiply all of that, I'm going to get how dou E is getting, or rather how my total error is getting impacted by W5. That is what this is simply going to be. Similarly, I'm going to do the same thing for dou E by dou W6 as well. Yeah. So if I were to put it into actual math, this is how it's going to look like. So don't get terrorized by it. It's not very difficult. It's the same thing. So dou E total by dou out O1, dou out O1 by dou net O1, dou net O1 by dou W5. Same exact thing that we just did. This is the same exact equation that we kind of put together over here. Nothing very complex. So we are simply calculating the rate of change of error with respect to change in W5. So when W5 changes, how much does the error change is what I'm trying to compute. Because if I know that if W5 is contributing heavily, then I will change W5 more. If I see that W6 change in W6 is contributing heavily to the outcome, then I will change W6 heavily. So to make that decision, which one has to be changed with how much, I first have to identify which one is contributing how much, and that's what I'm currently doing right now. I'm just trying to firstly compute how much is the error being implemented. So now here is where I'm going to start computing each of these terms. So firstly, dou E total by dou output O1. So for that, what we need to start doing is I'm going to start computing each of them separately. So firstly, how do I compute my error? How do I compute my error? It is 1 by 2 into the actual values, whatever my actual values were in the previous case, which is nothing but, target O1, let's call it target O1, minus the whatever my predicted O1 was. Predicted O1 is simply nothing but output O1, the whole square, plus 1 by 2 into target O2 minus output of O2, the whole square. Guys, this is exactly the same as, computing the error here and computing the error. I just put the equation together. Earlier, this is how we computed the error. So now what I'm saying is I'm going to compute dou E by dou output O1. I just have to partial differentiate this whole thing with respect to this. That means everything else will remain constant. So basically this term will simply vanish, because target O2 and output O2 are, I'm assuming these are constant. So this whole thing will vanish. This whole thing will become 0. And I have to simply do a partial derivative over here. So 1 by 2, so 2 by 2 is what it is going to become, into target O1 minus output of O1, and this will simply get cancelled, and I have to differentiate this one, and that will be minus 1. So simply put, -1 of target O1 minus output O1 is what is going to simply be. So that's as simple as that. Minus of target O1 minus output O1. That's what this is, as simple as that. Okay. And I simply substitute the values and I can't compute what that one is. Target O1, I know what the value is, and output O1, I know what the value is. I can simply compute what that is. That way I've completed dou E total by dou output O1. So I've computed this one. This one is complete. Okay, brilliant. So let's move forward. So the second one is dou output O1 by dou net O1. So for me to firstly compute this differentiation, the first thing that I have to do is I have to first understand how output O1 is being computed. If you go back and see, firstly, the output O1 equation is simply nothing but a sigmoid transform. See, you know, if you go back and check this one, see, output O1 is a sigmoid transformation of net O1. It's exactly a sigmoid transformation of net O1. So let's go back. This is going to be simply 1 by 1 plus e to the power of minus net O1. That's essentially what output O1 is. So now I have to differentiate output O1. So dou output O1 by dou net O1 is going to be a partial differentiation of this whole thing. So when you do a partial differentiation of this thing, especially your sigmoid transforms, there is a pretty straightforward way of doing a sigmoid transform. So sigmoid, sigmoid into 1 minus sigmoid. Basically, that is what your sigmoid differentiation of sigmoid transformation. Let's say you have a sigmoid of x, and you want to compute a differentiation of this. It's as simple as sigmoid of x into 1 minus sigmoid of x. That's essentially what the output is typically going to be. Where partial differentiation is going to be. And I think to compute something like that, as you observe here, it's the same thing. So output O1 into 1 minus output O1. You simply do a output O1 into 1 minus output O1, which is basically a sigmoid into 1 minus sigmoid. And then when you compute, you're going to get basically a value for your net O1, your dou output O1 by dou net O1. That will be basically a second term. So this term is also done. This is going to be output O1 into 1 minus output O1. When you do the actual partial differentiation, you're going to get output O1 into 1 minus output O1. So two terms are done. The last term is net output O1 with respect to W5. So if you see how net output O1 is getting computed, which is nothing but, W5 into H5 plus W6 into, I think, W5 H5. Oh, sorry. When I say H5, what I mean is H2. Let's go back one step. So W5 into H2 plus W6 or output H2 plus W6 into output H1. W5 into, this is going to be output H2, W6 into output H1 plus B2. That's what your net output O1 is. So net dou output O1 by dou W5. Again, when you see a dou W5, this is going to get cancelled. This will all get cancelled. What you will simply be left with in this particular case is going to be simply output of H2. That is all that you're going to be left with in this particular case, because everything else simply gets cancelled because you're doing a partial differentiation with respect to W5. And that value is as simple as this one. Output H1, which is 0.5932. So that's basically a third term. Once you have all these three terms, then you can simply do a multiplication of these three terms and you'll get a simple value out of this. This, my dear friends, is just dou E total by dou W5. Dou E total by simply dou W5. Similarly, you'll have to do dou E total by dou W6, dou W7, dou W8. For all the errors, basically W6, W5, W6, W7, W8. You'll have to basically do an error correction for all these four weights to start with. Okay, but yeah, basically just like how we've kind of updated 5, 6, 7, 8. Similarly, we will have to do something very similar with W1 and W2 as well. Similarly, dou E total by dou W1, just like how I've computed dou E total by dou W5, I will do dou E total by dou W1 and dou E total by, similarly, it's the same thing, but multiple components in here, right? That way, what will happen is right now, all my values will simply get updated. All my weights, not the I1, I2 value, they will remain constant, but my weights will now get updated. With the new value of weights, ignore all of this. So this is W1, W2, W3, W4. They are also now updated. With the new value of weights now, I'm going to go back and rebuild my model. So basically, these are my new weights. W1 is now 0.14. W1 is instead of 0.15, it is now 0.14. Similarly, W2 is 0.19. W2 is 0.19. W3 is 0.24, and this is 0.29. W4 is 0.29. So all the weights have reduced a little. Okay. So last but not the least, of course, now that the errors have now all these values have now been updated. So now what would you expect? You computed an error, and based on the error, you updated the weights now. So now you're going to run through the model. You're going to run the forward pass again. So when you run the forward pass again, what would you expect? Would you expect the error to be high or low? Error to be reduced? Absolutely right. So with the updated weights, when you run the error, when you run your forward pass again, previously the forward pass gave us an error of around 0.2983, but with the updated, after the first round of back propagation, the total error now has become 0.2910. It has become 0.2983 to 2910. Now you may ask me, dude, this is not a significant reduction. Absolutely, yes, this is not at all a significant reduction. But if I run this 100 times, but if let's say I run this 1,000 times, do you think the error will then significantly reduce? Absolutely, yes. If you run the same process 100 times or 1,000 times, the error will then significantly reduce. So point being, when you run multiple back propagation, forward pass and back propagation steps, that means your model is basically learning continuously, learning and updating weights, learning and updating weights, learning and updating weights. When this continuously happens, what happens is that almost after around 10,000 times, the error almost drops to around 0.40354 or 50, I don't know, 4 zeros almost 0.4035. It's almost as close as to zero, right? So when you run this like 1,000 times, 10,000 times, that's where things become much closer. Things get much closer to your actual predictions. Great question, Deepak. How much time will it take to run 1,000 predictions, 1,000 more times? If you implement it with simple Python with simple data, like this example, this small example will probably take a few milliseconds, probably a few seconds, maybe 3-4 seconds maybe, to run it 1,000 times or 10,000 times. But imagine you had, let's say, instead of one data point, imagine you had, let's say, 1,000 data points or 100,000 data points, and your network had like 20 layers, and your each layer had like, let's say, 30 neurons. Then in that case, training that could take anywhere between a few hours to probably even a day at times, depending on the infrastructure that you have, depending upon the data that you have, depending upon the size of the algorithm. Training a deep learning algorithm can take anywhere between a few hours to a couple of days. And if you have, let's say, the compute you have, let's say, for example, instead of using a CPU, if you have a GPU compute, that means if you have a graphic card on your system, and if you instead of using regular TensorFlow, if you start using.
Just a quick info, guys. Test your knowledge of AI by answering this question. Which of the following is not a stage of AI? A. Predictive analytics. B. Diagnostic analytics. C. Cognitive analytics. D. All of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
TensorFlow GPU version, then things can be much faster. you can accelerate things a little more. So that triggers us into a different line of conversation altogether. But the point being that deep learning is a time-taking affair. It's not something that's going to happen in like a jiffy, like a decision tree classifier.
So, suppose you are a computer vision engineer and a client has approached you with a problem statement in which you have to detect the faces from a set of images that they will be providing, and you have taken up this project, and these are the following steps that you have to follow while building up this project. So, these are the images that they have provided to you. These are some of the images that have taken from their dataset, and here we'll be working on Python with OpenCV. In this project, we will be using the Har cascade classifier for detecting the faces from multiple images. So, firstly, you have to perform the downloading part for the Har cascade system. So, here I have written download Har cascade frontal face default.xml and this raw GitHub code. These are the raw datas for the Har cascade. You have to just simply save as, and you can save it as desktop, and you have the Har cascade classifier. So now next we will be just importing the CV2 and glob. So now we will be practicing it in the Jupyter notebook. So firstly you have to import the CV2 library and glob. So I want to tell you that glob is the function which returns us the array of those file name which we will write in the next line. Like we just have to perform face detection on those images which have .jpg extension. So for that I will be writing gimage equals to glob .glob. So here I am calling the object glob and with the function glob, and here inside the function I will be writing the star.jpg. So it will take up all the images that have extension .jpg. So after that we will detect, after getting the glob images, now we will create cascade classifier so that we can, so as it helps us in getting the face detection. It contains all the features of the images like nose, ears, face, object. These are some of the features of the image. So here we will be writing detect equals to cv2 dot cascade classifier. Then inside the braces we will be writing which classifier. We have downloaded the Har cascade frontal face default classifier, so we will be mentioning the same name, Har cascade. Okay, Har cascade frontal face default.xml. So now after creating the Har cascade frontal face default XML file, then what we will do, we will now traverse the glob images so that we can detect the faces. So for traversing we will be creating a for loop for traverse, or you can also write t image for traversing the image, t image in g image, the glob image. Okay, so now it will take one image at a time. Now in the for loop we will read the image, a particular image. So for just reading the image we will write like I have taken image equals to cv2 dot im read, and what is this reading? The t image. Okay, so after reading the particular image from the G image, now we will convert the images. These are the colored images. The image that it has read, it is the colored images. So in this phase detection, we will first have to convert the colored image into the grayscale image. So it is easier for the classifier to handle the image and detect the faces from it. So for converting the image from converting the colored image to grayscale image, we will write gray image. I have written this gray image equals to cv2 dot cvt color, and In the braces, it will have this image that you have to convert it into grayscale. This image, comma, we will write cv2 dot color and underscore bgr to gray gray. Okay, so after converting it into grayscale, now we will detect the faces from the images. So for detecting the faces, I will be writing the face equals to detect. I am calling this object here and with the function detect multi-scale, and it has 3 parameters. So the first one is in which image you want to detect the face. So we will be writing this gray image here, and the next parameter is the scale factor. So we have to see the value of the scale factor, as the scale factor is that value which decreases the volume of the whole grayscale image by 5% until the face is detected. So it basically what does, it decreases the value of the image so that it can find the face from the image. So I am writing 1.25. The smaller the value is, the greater will be the accuracy. So I am writing 1.25, and the next parameter is the minimum neighbor. So we don't have to bother this value. Now after that, after detecting the face, now we will be describing the rectangle shape for the face. So for that, create a for loop for. Now in this braces, we will be writing all the dimensions for the rectangle like x, y, w, h, length, breadth, height and width. Okay, so after the parameter, now in face, we are actually we have detected the face, but now we have to define that face with a rectangle shape. So for that, we will be using the dot rectangle function. So here I am writing cv2 dot rectangle. Okay, rectangle. Now in this we have 4 parameters. The first one is the image that you have to detect the face image, this image that we have read it here. Okay, the second parameter is the RGB value. RGB value means the colored value. So here I am writing the x, y, and then the other parameters for the rectangle. We are basically defining the parameters of the rectangle, how it will look on the image. So we will be writing x plus w, y plus h. Okay, so after defining the parameters of the rectangle, now we will be look at the color of the rectangle. So here I am just taking the green color. So this is the code for green color. Okay, 0, 255, 0. Okay, so now after that the last parameter is the thickness of the rectangle. So I am giving 2. So now after defining the rectangle, now we will just show the image. So for displaying the image, cv2 dot imshow, in the parenthesis we will be writing detect. Any message you can write like detect images. Okay, and comma, which image? This image. So image. Okay, so after displaying the images, now we will be defining the wait key function. What does wait key does is we will define some intervals between the images. It's just a time period that what will be the intervals between the images. So cv2 dot wait key, and how many? I am taking 200 milliseconds, sorry, 2000 milliseconds, and we will be writing cv2 dot destroy all windows. So destroy all windows will closes all the windows based on the wait for key parameter. So here I am writing the 2000 milliseconds, so it will destroy it for that. So here, okay, so I am running this code. So here you can see that all the faces have been detected.
The problem statement. So the problem statement is here. Your client is a large MNC and they have 9 broad verticals across the organization. So one of the problems your client is facing is around identifying the right people for promotion and prepare them in time. So it is only for manager position and below. So currently the process that they are following is, first one, they first identify a set of employees based on recommendations and past performance. Then the selected employees go through the separate training and evaluation program for each vertical. These programs are based on the required skill of each vertical. Then at the end of the program, based on various factors such as training performance, KPI completion, employees gets promotion. So talking about the KPI completion, so only employees with KPIs completed greater than 60% are considered. Now this is the actual problem statement. Now let us look at the scenario that is provided by the company. So the final promotions are only announced after the evaluation, and this leads to delay in transition to their new roles. Hence, the company needs your help in identifying the eligible candidates at a particular checkpoint so that they can expedite the entire promotion cycle and they can speed up the process actually. So the first thing is they have provided multiple attributes around employees' past and current performance along with demographics. Then they have provided multiple attributes around employees' past and current performance. Now the next and the second point is the task that we have is to predict whether a potential promote at checkpoint in the task set will be promoted or not after the evaluation process. Now this is what we have to do, and moving ahead, let's understand the data set and the parameters. So let me go to the training and the testing data set. Now this is our training set and this is our test set. So now let me go to the training set, and this is the employee ID. So we are not much concerned about the employee ID, so it will not actually help us in the prediction. This is the department section, including sales and marketing, operations, then technology, analytics, operations, sales and technology, again technology, then research and development, then there is finance, procurement, and so on. There is also a department called HR, and the next one is region. So this is region 7, region 22, region 19, and there are many regions. So region will actually not help us to predict the outcome of the model that we have to build. Then comes education. So education can be the factor for predicting the promotion. So the list of education that is provided over here is masters and above and bachelors. So also here the empty data is there, which means that there is no data provided over here. So we will deal with the missing values also. And then comes the gender. So the gender is male and female. After that comes the recruitment channel, that is sourcing and other. Then comes the number of trainings. So that is 1, 2, and we'll scroll down. It includes 3, the number of training that are provided to the individuals or the employee. Then the next thing is the age. So this is the age of the employee. Then comes the previous year rating. So this can be one of the most important factor in the promotion. So the previous year rating is 5, 3, 1, 3, and so on. And this position or this, so this is 3-star, 4-star, and this is empty. So it denotes that the employee is not at all having a rating. So it can be because the employee may be a fresher. So let's check out the length of service. So here the length of service is 1. So that is why the previous year rating is not shown over here. So we'll sort out this thing also for making the model more accurate. Then comes KPI metrics, that is key performance indicator. So it denotes and it indicates the metrics for the performance of the employee. So 0 over here denotes that the performance is not at all good for giving them promotion, and 1 indicates that the performance is decent enough to give the promotion. Then comes awards 1. So this is 0, 0, 0, and here it is 1. So award 1 is 1 over here for a particular employee whose ID is 77981. And now average training score. So this is the training score of an employee while pursuing a training for the company. Here it is 85, 73, starting from 49, 60, 50, and so on. So it can be a major factor for predicting the promotion for the employees, that is how well they perform in the training and what is their score in the training. Then comes is promoted. So 0 means that they are not promoted and 1 means that they are promoted.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
So in this data where the promoted thing is 1, so this is the average training score, and here this shows the KPI metrics, that is also 1. Then the next one is the length of service, that is 6 years, and so on. So these are the parameters and the data set on which we'll be working on for making an AI model to resolve the business problem. Now let me go to the training set. So this is the training set and it consists of, let me go to this part. Okay, so this also consists of employee ID, then department, region, education, gender, recruitment, number of trainings, age, previous year rating. Then comes length of service, KPI metrics, awards won, and then average training score. So these are the parameters over here. So we have divided the data set into train and test set so that we can train the model using the train set and we can test the model using a separate data set, that is HR_test. Now the reason for using the test and the train data for the model is that we do not want our model to overfit the data. So in future it may get different sets of data and it may face issues in giving accurate results because the model is overfitting the data set that it is having. That is why we are using a separate data for training the model and a separate test data for testing the model. Now we have understood the data, that is trained data and the test data. Now let us move on to the steps that we'll see further. So the next step that we'll be going through is pre-processing and feature engineering. So in this we'll pre-process the data with using the different types of pre-processing. That is, we will manipulate the data, we will remove the null values and the missing values from the data set, and before that we'll use various and we will import various types of packages that are required for the implementation, and we'll see the info of the train and the test data set as well as the description such as the standard deviation, the mean and the average of the values. Then we'll perform feature engineering for the model and for the dataset values. Then we'll build the model using various algorithms that are used to build AI based applications, and we'll apply feature scaling so that all the values comes in the common slot and the prediction becomes more. And finally we'll evaluate the model that is created using various parameters and metrics of model evaluation, and then we'll visualize it using models visualization. So further, let's go to Google Colab for the implementation part. Now this is our Google Colab. So first thing you have to do is just go to this folder option, click on this upload session storage button and upload the training and the testing dataset. So I have already uploaded it, so I'll just show you. So I'll scroll down and here is the data, that is train and test data that I'll be using. So whenever you open Google Colab, so the first thing you have to do is you have to load the dataset. Otherwise you cannot work with Google Colab and create algorithms and AI based applications. So also one thing more, if you load the dataset now, so it is for this instance on which you are working. If you will close the tab, then the dataset will be deleted. So again and again you have to load the dataset. Now I have written the code over here, the entire code. So I'll implement and I'll explain every code what it is actually built for and how it is working. So first I'll import warnings and use this warnings.filter warnings ignore. So this is used to ignore the warnings that are displayed by the interface or by the Python library while implementing the program. So I'll run this, and now you can see it has been successfully executed. Now the next thing is the scientific and data manipulation libraries. So I have imported pandas, I have imported numpy, then import math, gc, os, and the sklearn package. So we use pandas basically for data analysis and data manipulation, and it provides various features for the analysis of data. Then comes numpy, so we can work with multi-dimensional data and matrix arrays using the numpy library. Then comes importing of maths that help us to implement various mathematical operations. After that, import gc for the garbage collection, and then importing os so that the packages and libraries are imported so that the application which we are building using the various modules and libraries of Python, so it gets added according to the operating system. Then importing scikit-learn, that is sklearn. So scikit-learn basically help us to implement classification, regression, dimensionality reduction, and many other machine learning algorithms we can implement using the sklearn or scikit-learn library. So I'll run this, and now the installation of the scikit-learn is done. So I have already done. It may take a while for you to get this. So I'll run this pip install scikit-learn to install the scikit-learn library. So it will take a while and it will get loaded. So these are the basic steps that you need to implement before data pre-processing. So these libraries and packages are the first thing that you have to load and install or download for working further with the data pre-processing task or creating algorithms. Then comes more libraries. So in sklearn we have pre-processing, model selection, tree, ensemble, and metrics. So from sklearn library we import the packages for pre-processing and model selection, tree, ensemble, and metrics. So why we do that? Because we have to use label encoder, one hot encoder. We want to use min max scaler, normalizer, robust scaler. Then comes max absolute scaler, and then we used model selection thing for using k-fold, stratified k-fold, train test split, then cross validation score. After that comes the tree package, for which we have to use decision tree classifier, random forest classifier, and then voting classifier using the ensemble package of sklearn library. Then comes the metrics package of the scikit-learn library, using which we'll evaluate, or first we'll load F1 score, then confusion matrix and classification reports that help us to implement the functions for F1 score, calculating confusion matrix for accuracy, and the classification report. So we'll use this from sklearn.preprocessing, import standard scaler, min-max scaler, normalizer, robust scaler, and for loading all these modules from the library, we'll use these commands. So let me run this. So it shows that it is successfully executed. So before moving ahead, let me explain you the standard scaler, min max scaler, so all these, why we are actually using it. So starting with standard scaler, it actually removes the mean and scales each feature or variable to unit variance, and this operation is performed feature wise in an independent way. So standard scaler can be influenced by outliers, so the values lying beyond the common slot of area where the actual values are lying, so it can be influenced by the outliers, and it involves the estimation of the empirical mean and the standard deviation of each feature. So it scales it, so it helps the model to predict in a better way. Then comes min max scaler. So min max scaler rescales the data set such that all the feature values are in the same range from 0 to 1. So actually there are too many values and it can have different values from 1 to any of the value. So we need to rescale the value in a common slot such that we can create a plot out of it and gets a better visualization. So min max scaler helps in this way. After that comes the normalizer. So the normalizer rescales the vector for each samples to have unit norm independently of the distribution of the samples. Now then comes the robust scaler. So unlike all the other scalars, the centering and scaling statistics of this scalar are based on percentiles, and therefore they are not influenced by a few number of very large marginal outliers. Then consequently the resulting range of the transformed feature values is larger than for the previous scalars, and one of the most important thing to note is that they are approximately similar, and for both features and for most of the transformed values they actually lie in a range of -2 to 3. Now coming to max ABS scalar, so it differs from other scalars and such that the absolute values that are mapped, they are in the range of 0 to 1. So they are the absolute values, and on the positive data the scalar behaves similar to min max scalar, and therefore it can suffer from the presence of large outliers. Then comes the voting classifier. So the logic behind the voting classifier is creating a separate dedicated model and finding the accuracy for each one of them. So we actually create a single model that is trained by the other models and predicts the output based on their combined majority of voting for each output class. So that is the logic behind the voting classifier, and we'll use this voting classifier for our project. So I hope the importing of the libraries and packages is clear. Now we'll move ahead and we'll import class and we'll install the cat boost. So I'll click on it. So you have to use this command pip3 install cat boost, as we'll be using the boosting algorithms such as xgboost, lightgbm and cat boost for preparing our model. So it will just take a while to load, and I have already loaded this and I have downloaded the packages related to cat boost. That is why it is showing requirement already satisfied. Then I'll import the xgboost and use an attribute that is xgb for it. Then lightgbm and then cat boost. So I'll click on it and it is successfully executed. So why do we actually use XGBoost, LightGBM and CatBoost? So XGBoost is a scalable and accurate implementation of gradient boosting machines, and it has proven to push the limits of computing power for boosted trees that are used for implementing the algorithms for the sole purpose of checking the model's performance and improving the model's performance and the computational speed. So that is why we use XGBoost. So also XGBoost is used for supervised learning problems where we use the training data to predict a target variable. So that is why XGBoost is used for building the AI models. Then coming to LightGBM, that is a gradient boosting framework that uses tree-based algorithms, and it is designed to be distributed and efficient with the following advantages, that is faster training speed and higher efficiency. Also, it has support of parallel and GPU learning capable of handling large-scale data. So that is why LightGBM is used as a classifier. Then coming to cat boost algorithm, so it is an algorithm for gradient boosting on decision trees. So it is basically used for search, recommendation systems, personal assistant, self-driving cars, weather prediction, and many other search tasks. So one of the major benefit of using cat boost is it can handle missing values internally. Also, by default, cat boost uses one hot encoding for categorical features with a small amount of different values in most.
Just a quick info, guys. Test your knowledge of AI by answering this question. What are the main goals of AI? A. Create expert systems. B. Implement human intelligence in machines. C. Both A and B option. D. None of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
of the modes that we use. And so coming to one hot encoding, we use it for all the categorical features with a number of different values less than or equal to the given parameter value in a specific range. So we'll use all these algorithms for our AI project, for building our model, and I hope you are clear with the algorithms that we are using. So let me run this, and you can see it is being successfully executed. Now I'll run this. That is, from XGBoost we are importing XGBoost classifier. So it is also successfully loaded. Now comes the data visualization libraries. So we will use matplotlib, seaborn and plotly package for the data visualization. So I'll run this. Okay. Now comes the randomness of the data that is being selected. So we'll use np.random.seed. So it is actually used to save the state of a random function so that it can generate same random numbers on multiple execution of the code on the same machine, or it can be on different machine. So the seed value is the previous value number generated by the generator. So that is why we'll use this np.random.seed. After that, we have to set the location path from where we'll use the dataset. So we have already loaded the dataset, and you have to do it again and again for the Google Colab if you are using Google Colab. So now I have already imported OS. So it is just written over here from Google Colab, import files, then train pd.read.csv is used to load the dataset. I'll run this and let us see. Okay, so it is being successfully executed. Now we'll display the dataset of train and test. So we use this display function to display the values. So I'll run this and it will display the training values and the testing values. So let me scroll down. So the first one is training value and the second one is the test values. The second one are the test values. So this shows the index. Now employee ID, department, region, education, gender, recruitment channel, then number of trainings, age, previous year training, length of service, KPI metrics that is greater than 80, and awards 1, average training score, and is promoted. So as we have already discussed the training dataset, and the KPI metrics should be greater than 80% to get the promotion. So here it is. Now let us check out the test dataset. So again, these are the index, employee ID, department, region, education, and it will not have the is promoted column because this is the testing dataset. That is, these are the independent variables using which we have to predict whether the person has to be promoted or not. That is the variable is promoted. Now further, let me go to the exploratory data analysis that we have to perform. So for this, first we have to look into the information of the training set. So for this, we'll use train.info to display the information of the trained data. So let me implement this. And now we get the training data. Along with it includes the non-null count and the data type. Also the count of the types of data type, that is float 64 is 1 time for the corresponding column, and it is previous year rating, and integer is 8 times and the object is 5 times. Also it shows the memory usage, that is over here it is 5.9 plus MB. So this shows the information related to train set, and then let me display the information related to the test data. So here it shows that there are 23,490 entries starting from 0 to 23489, and data columns total there are 13 columns, and non-null count along with data type and the count of data type over here, and the memory usage is 2.3 plus MB. So this is the information regarding the test and the training data. Then comes displaying the descriptive statistics of train data. So just talking about exploratory data analysis, so it is a part of the data pre-processing. where we actually gather the information related to the data. So we check the info, we check the description of the data, such as the average, the maximum and the minimum values, along with the mean or the standard deviation, the type of data, memory usage, and the non-null count, and many other factors. So we look into that in this data pre-processing step, or you can say the EDA, that is exploratory data analysis. So let me run this train.describe. So it shows more information related to the training dataset. So it shows the count, it shows the mean for all of these columns, then comes the minimum value, maximum value, and the interquartile range. Now let me check the description about the test data. So I'll run this, that is test.describe. Again, it shows the count, the mean, the standard deviation, minimum and the maximum value, and the IQR, that is interquartile range. So this shows us the description of the train and the test data. Now further we'll display the number of unique values and the actual values. So we have to first define a function, def for defining the function, that is display unique, and it will take the argument as data. So here we have passed the argument of train data. So display unique, we have called the function. Now what does this function do? So for column in data dot column, that access the columns present in the data set. So we have to print the number of unique values in the column, that is the column corresponding to the trained data set that we are accessing to. Then the columns are then using the str function data, then column dot n unique. It will fetch the unique values from the data set or from the column. Then the actual unique values in column. So again, now further to get the actual values, so here we use again the str function and then the sort values function that sorts the data in the ascending order, because the ascending is set true over here. So for getting the actual values, we have to use this sort underscore values function, and this na underscore position takes two strings, input last or first, to set the position of null values, and accessing this unique function gives the unique values from the data set. So it shows the number of unique values simply, and using the sort values function we can access the actual values in the column. So let me execute this, and now here we get the output. So number of unique values in employee ID are 54,808. So starting from 1 and it goes the list index. So these are the actual values, and then comes the number of values or unique values in department column, that are 9. But the actual unique values in the department column are analytics, finance, HR, legal, operation, procurement, R&D, sales and marketing, and technology. So the actual values are shown over here. So these are the actual values. So this is how we actually access the actual values using the sort underscore values, and we can keep descending also over here, but we have kept ascending order. So these are the actual and the unique values for all of the columns of the train data set. So we can check it for test, but we'll leave it for now. And now we'll move on to displaying how each feature is related to the target variable in a flow. So for this we will use a plot using the parallel categories diagram. So the parallel categories diagram actually it is also known as parallel sets, and it is a diagram, or you can say a visualization of multidimensional categorical data sets, and each variable in the dataset is represented by the column of rectangles, where each rectangle corresponds to discrete value taken by that variable. So here we pass in the columns. So the columns are department, education, gender, previous year rating, KPI, metrics, then recruitment channel, and is promoted, and color is based on the is promoted column. Then we use the continuous color scale. So using this sequential.agrenil. So we plot the figure using multiple colors. So this figure dot show help us to show the figure. Now let me implement this and let us have a glance at the figure that we get. So it will just take a while to load. Till then you can just wait. Okay, this is the figure that we had. So this figure is very descriptive and it shows you the data. So let me show you how you can actually read this figure and how actually you can understand the various dependent or independent variables from this figure. So there are columns named department, then education, gender, previous year rating, KPI metrics, recruitment channel, is promoted. So is promoted is shown over here. So it consists of the value as 0 to 1. So hence its scale is from 0 to 1. And then comes the individual categories of the columns. So in department, there are multiple departments such as sales and marketing, operations. So this section is the operations one. So you can see when I have kept my pointer over here, so it shows the relation, actually the data relation from other columns such as education, gender, previous year rating, KPI metrics, recruitment channel, and is promoted. So the count it shows is 11,348. That is, there are 11,348 employees for the operations department. When I kept my mouse pointer for sales and marketing, it shows the count as 16,840. And then comes the count of this sales and marketing, and then technology. So the count is, let me click on this. So the count is, you can see over here. So this shows the count as 7138. Then comes analytics, that is 5352, R&D, which is the least, and then procurement, finance, HR, and legal. Now coming to education. So when I kept the pointer over here, so it shows the count for the masters and above degree as 14,925. So here the category is written over here. Then when I came to this bachelor's, it shows the count as 36,669. Then coming to below secondary, it is 2,409. And then the final one is the below secondary one, and this, so this last one is the below secondary one, that is 805. Now coming to gender, then the count is 16,312, and the count for the male employees is 38,496. Now previous year rating starting from 5. So the employee who are having the rating as 5 are 11,741. Then 3, rating of 3 is 18,618 employees are having a rating of 3. Then 1, it is 6,223. Then rating of 4 is of 9,877 employees. After that, the rating of 2 is 4,225. Now the KPI metrics greater than 80. So for 1, that is the metric, KPI metrics is greater than 80, the count is 19,291. And for the employees for whom the KPI metric is less than 80% are 35,517. Now again, the recruitment channel is sourcing, other, and referred. So for sourcing, it is, the count is 23,220. Then for others, the count is 30,446. Then for the referred one, it is 1142, that is the least. Now I'll come to the is underscore promoted column. So the count it gives is 50,140 people are not promoted, that is the value is 0. And the promoted people's count is 4,668. So you can see over here the structure of the figure. Now for the next one, we will have a heat map. So we will display the correlation between the features through heat map, and lighter color, higher correlation, and if close to 1. So lighter color shows the high correlation. So for this we use sns.heatmap, and as we are making the heat map for the train dataset, so we'll use this train.corr for correlation, and this annotation or anot is true. So I'll run this and we'll get the heat map. So here are the employee ID. So these are the columns: employee ID, number of training, age, previous year rating, length of service, KPI metrics greater than 80%, awards won, and then average training score is promoted. And this scale shows the is promoted thing.
Okay guys, a quick info: if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
Starting from 0 and 1, so the values are only 0 and 1. Now the x-axis of the figure, so it is not actually x-axis, but it is the other side of this figure. So it has again employee ID, number of trainings, age, and previous year rating, length of service, KPI metrics, then awards won, and average training score, and is promoted. So a heat map is a two-dimensional graphical representation of data where the individual values that are contained in a matrix are represented as colors. And the Seaborn library, we have imported it for this purpose, and the Seaborn Python package allows the creation of annotated heat maps, and which can be tweaked using the matplotlib tool as per the creator's requirement. So we are creating this for the correlation, finding the correlation. So this color shows us the correlation between all these parameters that we are evaluating. So this is the heat map that shows the people who are promoted, or not the people who are promoted, but the correlation between these columns. Now let me go to the next part, which is finding the duplicate rows from the trained data if it is present. So we have to check for duplicate rows to remove them. So we will create a method that is remove duplicates that will have an argument of data. So in this we'll print before moving or before removing duplicates the number of rows, comma data dot shape. We'll give the argument as data dot shape. Then we have to implement the logic or the action, that is data dot drop duplicates. To drop the duplicates, keep equal to first in place equal to true, and then again we have to print after removing duplicates the number of rows. So again the argument is data dot shape. So actually this data dot shape returns the data in the form of array, and then we'll return the check duplicates. And now I'll just implement this, run this, and now I'll call the remove underscore duplicate and give the data or the argument as train. And now I'll click on this. Further, after the successful execution of the code, we'll get this: before removing duplicates the number of rows are 54,808, and after removing the duplicates the number of rows are again 54,808. Now it will return the checked duplicates. After that we'll handle the missing values. So remember that still we are in the data pre-processing or the manipulation part, so we have to deal with the missing values. So missing values are present in the previous year rating and education columns in both train and the test data. So here I have just written for the reference why is data missing in column previous year rating. So data was not entered because those employees were fresher. So as I have already told you when we were discussing and when I explained you about the data set, So data was not entered because those employees were freshers, that is length of service is 1 is equal to 1, and they did not have the previous year rating. So the no data would have been there in the data source itself for these employees. So logically we are imputing with 0 as freshers with 1 year experience and may not have previous year rating at all. So filling the missing values in train and test data. So what we'll do is we'll use this train data set and the test data set, and in this bracket we'll give the column name, that is previous year rating. And what we'll do is, again, to access the previous year rating, so we are actually accessing the previous year rating, and then we'll use this dot fill na with 0, so it will fill those values with the 0. So the next thing is we'll access the column of fresher for the train data set, and then we'll use this previous year rating and apply function, and then we'll use this lambda. So here we'll put the condition, so if x is equal to 0 is equal to 0, then the employee will be a fresher, otherwise the employee is an experienced professional. After that we'll display the fresher column with the value counts, and again the previous year rating, length of service, and this fresher tag that we have used using the condition that is applied over here for marking the tag as a fresher. Again we'll use this display function to display this previous year rating, length of service, then fresher for the first 25 values and for this we'll use this head function. Now I'll run this, and here we get the output. So these are the columns and they are replaced by the values as 0, 1, fresher. So this is the fresher column and this is the fresher tag that we have displayed using the display function and putting the condition over here. So the experienced professionals are 50,684 and the freshers are 4,124, and the data type is integer again. So we have used the previous year rating, length of service, and the fresher column for displaying the data. Now again we have displayed the data for previous year rating, length of service, and this tag I should have changed it to experienced. So okay, so I have put a condition over here, so let me go to that one. Okay, so here if x is equal to 0 then it will be a fresher, otherwise experienced. So that is why it is showing data over here for experienced as well as for fresher, and the length of service, previous year rating. So this is actually about the removal of the missing values and sorting out the missing values that were there in the data set. So we actually saw some empty blocks in the data set, so we filled in with the values as 0. So for that we used fill na and filled with 0. So this is done. Now next what we'll do is we'll display the missing values in the train and test data. So to display that we'll use this display function, and this will give the text as train corresponding to the missing values in train set. So we'll use this train dot isNull dot sum. So isNull for counting the for getting the null values, and sum function to sum all those, and to display it we'll use this display function. Same for the test. So I'll run this. So for training set, so this is employee ID, department, region, education, gender, recruitment channel. So for all other columns the null values, so there are no null values, there are 0 null values, but for education there are 2409 null values present. And for the test column, the employee ID, department, region, and all other columns are not having any null values. The count is, or the sum of those null values is 0, the count is 0. And for the education, it is 1034. So as the test dataset is less than the training dataset, so it is showing less. So we have counted the null values over here. So now after executing this, let us handle the null values. So for this we'll use ffill bfill. So I have written this for reference, so you can read this. So talking about ffill, so this is forward fill, that fills the missing values with previous row value, and if previous row value is null, then it moves to the next element without filling. That is why we use ffill and bfill both. So what does bfill do is, so it is backward fill that fills the missing values with next row value, and if the next row value is null, so it moves to the next element without filling. So what actually happens is, for example, for just explaining you, if the system goes to 4th and 5th row and the 4th one is empty, then it iterates to the 5th row and fills the data of the 5th row into the 4th row. So this is actually the backward fill. And in forward fill, what happens is it fills the missing value with the previous row value. For example, if 4th row is having a data and 5th row is empty, the data is not present, then the value present in the 4th row will be added for the 5th row data. So we use both forward fill and the backward fill to fill in the data. Also, filling with mode and new category called others are most commonly used technique which didn't work here, so we are not using that. So we can assume that while collecting data relevant members, data were collected close to one another, so it is not too fluctuating, that means. So talking about the training, now we'll fill in the values for the education column. So here we have used this train, inside it we have given the argument inside the square brackets as education. Then we'll use this dot ffill for forward fill, and we give the argument in this way, that is access is equal to 0 for all of the train and the test data. And finally we display the data and we try to actually calculate the sum of all the null values that are present in the training data set and the test data set using the isNull and sum function. So I'll run this and let us see the output. So it will just take a while to load. So here we get the output for the train and the test data set. So employee ID, department, region, education, gender. So you can see over here, so we have implemented it on the education column by using the forward fill and backward fill. So the count has come down to 0 for the education column. Now after this we'll work on feature engineering. So based on the age distribution, most of the employees are in the range 20 to 40 who will be also waiting for a promotion, and so we have created 2 bins, 20 to 29, 29 to 39, and remaining 1 bin for 39 to 49. So we have used dist plot, so plot a univariate distribution for the observations. So I have written this for the reference so that you can refer it in future if you have any doubt and all. So you can see the description of this. Okay, so moving ahead, we'll use this sns.dist plot and we'll give the train as the data and this age column, and after that we'll use this train, and inside this square brackets we'll give the age. We'll use this pd.cut and give in the argument as train.
Just a quick info, guys. Test your knowledge of AI by answering this question. Which of the following is not a stage of AI? A. Predictive analytics. B. Diagnostic analytics. C. Cognitive analytics. D. All of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
And the age column, so the trained data set along with the age column, or for the age column, and bins will be 20, 29, 39, 49, and labels that would be given to these bins are 20, 30, 40. Same for the test one. For each column, pd.cut, bins will be 20, 29, 39, 49, and the labels will be given as 20, 30, and 40. So let me run this, and now we'll get the plot like this. So feature engineering is nothing but extracting the feature or the properties from the dataset and the expertise and the knowledge that we have. So this is the plot that we have after plotting the age column. Now after this, we'll split the train data into predictors and the target, that is independent and dependent variables. So this is the step that we have to do before creating our model. So here we'll split train into x underscore train, that is features, and y underscore train, that is target. So in x train, we'll select all of the columns, that is department, region, education, gender, recruitment channel, number of trainings, age, previous year rating, length of service, KPIs, metric that is greater than 80%, awards won, and average training score. And in this Y train, we'll select the is promoted column, that is the separate column that we have to predict using the test dataset. So we will add this in the Y train section, and then we'll convert the Y train into a frame using 2 underscore frame, because it is a single parameter and the output is expected to be in data frame. So we'll use this to convert it to a frame. Now comes the X test. So we'll use this X underscore test, and inside it we'll give the argument or the number of columns, that is department, region, education, gender, till average training score. So now we have successfully splitted the train and the test data. So after running it, so it has no error, that is it has been successfully executed. Now as we have splitted our data set into train and test, now we'll perform the data encoding using the label encoding and the one hot encoding. So what does it actually mean to perform these operations? So actually label encoding refers to the converting of the labels into numeric form, so that to convert it into the machine readable form, and the machine learning algorithms or the AI algorithms that we are using for building our AI based application can then decide in a better way on how those labels must be operated. And using one hot encoding allows the representation of categorical data to be more expressive, and many or the various machine learning algorithms cannot work with categorical data directly. So the categories must be converted into numbers. So this is required for both input and output variables that are categorical. So we use one hot encoding for that. So we'll define a function that is data encoding, and given the parameters or the arguments, that is encoding strategy, encoding data, and encoding columns. So let me go down and check where I have called this. Okay, encoding data encoding. So I'll check where I have called this function. So this is data encoding I've called over here, then encoding strategy, and then the data, then the columns that we have to give. Now I'll go back over here. Now what does this function do? So if encoding strategy is label encoding, then we have to print if label encoding, and the encoder we have to put in the label encoder because we are using label encoder. And then we will put a for loop over here. So for column in the encoding columns, we have to print column, then encoding data, and in this encoding data the column will be inserted, and then this function has to be executed. So encoder.fit transform, and then the argument must be given. So tuple encoding data, again we'll use the column as the argument. After that, if this is not true, then we put in elif condition where encoding strategy is equal to one hot encoding. So if this is the scenario, then we have to print elif one hot encoding, and then encoding data we'll use pd.getDummies for encoding data. So this PD is the instance of the pandas library, and this getDummies will give us the categorical values, the dummy categorical values. And after that comes the dtype list that we have to define for float 64, float 32, int 64, int 32 for the data type. So this is the data types list. Then encoding data as type we'll use, and then data types list, and then we'll access the data types. So after implementing if elif, these two lines of code will be implemented which shows the data type, and then return encoding data. So using these condition we'll implement the data encoding technique. So here for description I have added this quote and many points related to it. So let me read it for you. So applied one hot encoding, it will be applied to object categorical columns only, and it's most common to one hot encode these objects columns since they can't be plugged directly into most models. Then pandas offers a convenient function called getDummies to get one hot encodings. So using this getDummies we get a dummy variable or a dummy value for the categorical or for the encoded values. So get this using getDummies, and many machine learning algorithms cannot operate on labeled data directly, and they require all the input variables and output variables to be numeric. This means that categorical data must be converted to a numerical form, and a one hot encoding can be applied to the integer representation. Finally, this is where the integer encoded variable is removed and a new binary variable is added for each unique integer value. So you can go through this description for the reference. So I'll run this. So it has been successfully executed, and you will get the result in the next code when we'll implement it. So just for reference or example, I have added the data encoding for this color, that is red, blue, green, red, blue, green. And I have created this df as the data frame, and then pd.data frame. I have given the data over here columns as color. Then I'll print before one hot encoding and call the function as display df, and then I'll print after one hot encoding and display pd.getDummies. So for the first one, so we get the result as before one hot encoding, it is displaying the data frame, and in the second one we get the result after one hot encoding. So I'll run this in one go. So let me explain this one also. So encoding columns, encoding strategy. So I'll go in this code. So we have created a function data encoding, and the parameters are encoding strategy, encoding data, encoding columns. So over here are encoding columns, encoding strategy. So encoding strategy is label encoding, one hot encoding, and the encoding columns are region, age, department, education, gender, and recruitment channel that we have to encode. So while implementing this, we have to just give in the index. So here I have called the data encoding function that we have defined earlier. So xtrain encode, xtest encode, and we have called data encoding and data encoding strategy. So index is 1 and the data is xtrain and encoding columns. So it will take the entire column, so all of the columns, and then the second one is encoding strategy xtest on xtest and encoding columns, so it will take all the columns. Then for displaying the encoded train and test features, we'll use the display function and we'll display the first few values using the head function. So xtrain encode, xtest encode. So let me run this, and the first one gives the color data frame, that is red, blue, green, red, blue, blue. So these are encoded in 0, 1, 2, 3, 4, 5. So we have performed one hot encoding, and after performing one hot encoding we get the following results, that is color blue, color green, color red. So these three are the colors, red, blue, green, and these are the indexes, and the encoding that is done is, so this is the data frame. So we have converted it into a data frame, that is why it is showing a data frame over here. So color blue, color green, color red. So this is these are the encoded values for it. Now let me go up and let me check. So this was the color part, and then we defined the encoding strategy. Then we have called data encoding 2 times for train and test, and it is showing one hot encoding, one hot encoding. So it has performed one hot encoding. So why it has performed? Because the index that we have given over here is 1. So here it is 0, label encoding is 0, having an index of 0, and one hot encoding is at the index position 1. So one hot encoding will be performed. So for performing one hot encoding, first it will print elif one hot encoding, that shows that it is performing this type of encoding, and then it has performed the one hot encoding using the pd.getDummies. So it is displayed over here. So these are the result for the encoded rows, the columns that are over here. So you can check it out, the encoded values. So we have encoded it for region, and then it shows various region and the values, then for gender, recruitment channel, and so on. After that, after the encoding has been performed, so our data is encoded, and now we have to perform scaling. So we have already discussed about the scaling types, that is robust scaler, standard scaler, min-max scaler, and max ABS scaler. So I have told you about these type of scalars. So we will directly create a function, so using this data underscore scaling, and we'll give the argument name as scaling strategy, scaling data, scaling columns, and we'll give in the condition as if scaling strategy is robust scalar, then the scaling data will be, and inside this square brackets we'll give the scaling columns that we need to scale, and then we'll use the robust scalar dot fit transform to scale the values using the robust scalar, and then the scaling data which we have used and we have passed in the argument, and the scaling columns that we need to scale. Same with the standard scalar. So we'll give in the condition as elif, so scaling strategy, if scaling strategy is equal to standard scalar, then we have to use this standard scalar dot fit transform, and again the scaling data along with the scaling columns, or you can say the corresponding scaling columns that we have to put in over here. After that, again elif scaling strategy is equal to min-max scalar. Now same with the min-max scalar and max ABS scalar. So scaling data, then scaling columns, then again using the fit underscore transform method and given in the parameter as scaling data with the corresponding scaling columns that we need to scale. And final else condition consists of the robust scalar. So if any other scaling sent by mistake, it still performs the robust scalar. So we'll use the same line of code that we used for robust scalar, that is scaling data, corresponding columns, and then robust scalar function dot fit underscore transform, and finally we'll return the scaling data. So I'll run this and let's check. Okay, so it has been successfully executed. Now the next one is where we will call the data scaling function or the method. So this is the data scaling method that we have created over here. So this is the description that I have given for reference. So let me read for you. So robust scalar is better in handling outliers. So standardization of a dataset is a common requirement for many machine learning estimators, and typically this is done by removing the mean and the scaling to unit variance, and the outliers can often influence the sample mean variance in a negative way. So in such cases, robust scaler, which uses the median and the interquartile range, often give better results. So here we have defined the scaling strategy. So that is robust scaler, standard scaler, min-max scaler, and max ABS scaler. Now we'll use this X train scale and X test scale as the variable or the instance, and we'll store the values after calling this method, that is data scaling. We'll pass the argument as scaling strategy, that will be 0 in the first one and 0 in the second one. So 0 indicates that it is calling the robust scaler. So we have created the scaling strategy and we can call any one of this. So we have called the robust scaler. Then here we have given the X train encode and then X train encode columns. So what it actually shows is we are scaling the encoded values of train and the test dataset that we have encoded in the previous steps. Okay, then we'll display this X train scaled value and first few values of it for the train and for the test. So it should be test over here. Now let me run this and let us see what we get as the output.
Okay guys, a quick info, if you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
So this is the number of training, previous year, length of service, KPI, metrics, award won, average training, department. So now we have successfully scaled the values using the robust scaler. So what actually is robust scaler doing over here? So you already know. So it is handling the outliers and it is making the model more accurate and helping us to create such a model to give more precise results. So this is done. Now comes the most important step, that is creating baseline ML model for binary classification problem. So we will use some machine learning algorithms, and you can also say that AI algorithms. So we have already looked around it earlier, that is XGB classifier, then cat boost, light GBM. So here we will create a dictionary, that is key value pairs for ML model name, and then ML model functions with hyperparameters. So these are the hyperparameters. So we'll given the name as classifier, and at the 0th index we'll give the XG boost. First will be cat boost, second will be light GBM. So using this XGB classifier, we'll define the hyperparameters, that is learning rate, N estimators, max depth, subsample, verbosity, scale, position weight, updater, base score. So the learning rate over here is 0.1. The number of estimators are 494. Maximum depth is 5. Subsample is 0.7, that is 70%. Then verbosity is 0. So what actually verbosity is? So verbosity in keyword, it arguments, and it usually means that showing more wordy information for the task. So actually giving the more description. Then the scale position weight, that is 2.5. Updater is grow hist maker, then base score is 0.2. So we'll see the plot which will be plotted. Then it will be same for the cat boost classifier, learning rate, number of estimators, subsample, max depth. Then for light GBM, the importance type come in for extra. Then verbosity is -1. So you can see over here the verbosity is -1. Here it is 1 or 0. Sorry. So here it is 0. Here it is 1. So the more is the verbosity, the more wordy or the descriptive is the model, or you can see it is more adaptive and it shows the more information. So here it is -1, so it is low. Then maximum number of bin is 60, number of leaves 300, boosting type is Dart, learning rate is 0.15, number of estimators are again 494, max depth and other things are same as the cat boost and xg boost. Now after creating a dictionary of an ML model for the binary classification, we'll print. So we have to use this list, then classifiers dot keys and classifiers dot values for it. So after implementing it, let us see what we get as the result. So XGBoost, CatBoost, Light GBM, and this is what we get. Now our model is created and there are so many parameters to evaluate it. So base score, booster, column sample by level and so many others, but we need to improve our model as no model is perfect in AI or machine learning. So what we'll do is we have to improve the machine learning or the AI model. So as we have used this machine learning algorithms, so it is same for AI also. So I have written over here the ML model. So to improve the ML model with voting classifier, with model evaluation metric, we'll use this F1 and predict target for is promoted. So we'll evaluate the F1 score. So actually what voting classifier is, we have already discussed in the previous section while importing the libraries, modules and packages for the voting classifier. So we'll use the instance or the variable as voting model, and then we'll use the keyword that is reserved by the library or the package, that is voting classifier, and the estimators will given as the xg boost, and then the second argument will be then list classifiers dot value to fetch the values, and for 0th index is the 1 for xg boost, and the 1 or the first index is for cat boost, then light gbm. Then we have given over here as soft voting, and the weights are given over here 5, 5.2, 5, 5 and 5.2. So actually in soft voting the output class is the prediction based on the average of the probability given to that class. And you can consider an example. Suppose you are given with some input for the 3 models and the prediction probability for class 1 and class 2. So if the probabilities are 0.1, 0.2, 0.3, and for the next one it is 0.2, 0.3, 0.4. So obviously the average of the second class is greater. So the winner is the second one. So this is the soft voting that we call in machine learning. So it is given over here. So then we'll use this voting model that we have created and use this fit method, and inside it we'll give the parameters as xtrain scale for the scaled values that we have created in the data engineering process, and we'll give in the y train for training the model. Then we'll evaluate the predictions of the voting using the voting model that we have just now created dot predict probability, and we'll give the x test scale for checking the performance of the model on the basis of test dataset. So we'll take the entire test dataset. So let me run this, and it will just take a while to get executed. So now get the output. So you can see over here, so the learning rate and the total time, remaining time. So you can see it is still executed. Now again it will take time, so let me tell you the next part that we'll implement. So next we'll work on the result, we'll see the result and try to improve the F1 score. So for this okay, it is completely executed. We see the values. So it took a total of 10.4 seconds to predict the outcome or to learn the features of it. Then the next part that I was talking about is the result and the improving of F1 score. So for this we have to round off the probability results, and for this we'll simply use an instance as prediction, and we'll give in the round function, and before it we'll use the integer that converts it to the integer, and then we'll have a for loop. So for value in predictions of voting that we have just now implemented for the voting model or the voting classifier, so predictions of voting will be counted over here, and then we'll create a data frame table for this result, and we'll store it in the result promoted section. So we'll use this pd.dataframe, and we'll give in the employee ID and is promoted, and it will have the predictions and the test set of the employee ID. Then this thing you need not to take care of. These are again the classifiers, and then you have to print list classifiers keys over here. So this will be same as previously we have used the classifiers over here. So this is the same thing. Now let me implement it and let us see the results. So list of classifiers, so XGBoost, CatBoost and Light GBM. Now next we'll print result promoted. So I'll type in print, then result, and now I'll run this, and you can see employee ID and is promoted. So these are all the IDs of the employees who are being promoted. So here you can see that the ID number 5973, so employee corresponding to this ID has been promoted. So this is how we implement it and get the result using the round of probability. Now next we have used the classifiers, that is classifier 1, classifier 2, classifier 3 for XGBoost, then Light GBM and CatBoost. So we are fetching the values and the index as same. We have used 0, 1, 2, and then we have used the array from the NumPy library and given the index over here, and then finally use the voting classifiers, and we have given the estimators as XGBoost, CatBoost and then LGBM for classifier 1, classifier 2 and classifier 3 represented by CLF 1, 2 and 3. Then voting again is soft. Then we will predict the class probabilities for all the classifiers using the predict underscore prob function and giving in the argument as x, and using the classifiers for the XGBoost, CatBoost and Light GBM along with the voting classifier that we have built over here. So all this we are using for predicting the probability. Now to get the class probabilities for the first sample in the dataset, we'll create two classes and then we'll create a 2D array and put a for loop where we'll use the probus instance that we have used for predicting the probability for the model using various classifiers. So these two has been created, and now we'll plot what we have created or what model we have created. So we'll plot. So we'll use n equal to 4, that is number of groups, then ind instance for np.arrange, so arranging these groups, and these are the group positions, and width will be 0.35, that is bar width. Then we'll use figure and ax as the instance for the subplots. So we'll use the plotly package. So plt.subplots is the function that we have to use, and then bars for classifiers 1 to 3 and bars for voting classifiers. So for classifiers 1 to 3 we'll use the instance of p1 and p2 and use this ax.bar function where ax is the instance, and bar is the function taking the parameter as ind, that is the group's position, in np.hstag that takes the class probabilities that we have created, and the index -1 shows that it is taking all the values. Then the width is 0.35, then color, h color, and same for the second one, that is p2, where we'll use the second class that we have created. And for the bars, for voting classifier, we'll use the p3 p4 instance, we'll create it, and ax.bar, where bar is the function that we are using and ax is again the instance. And here the parameters are quite different, that is ind is same, but here we are giving 0 0 0. So instead of hstacks, that is np.hstack, we just given the values as 000 because it is a voting classifier and we cannot use hstag in it for this scenario. So the color is quite different. And now we'll set the plot annotations using the axv line. So it takes the argument as the value 2.8, color equal to k, line style equal to dashed, and then ax dot set underscore x ticks with ind plus width. So it is a matplotlib function that ticks when the values are true and a minor tick when the values are false. Then set the x tick labels for xgboost, catboost, light gbm voting classifier, and the rotation will be 40. And now we'll give the y limit, that is 0 to 1, plot title, that is class probabilities for sample 1 by different classifiers, then plt.legend, that creates a legend for any plot, so for p1 and p2, and the values given over here is promoted no and is promoted yes. Then location is upper right, then plt.tight layout, that helps to automatically adjust the subplot parameters according to the padding. Then finally we'll use this plt.show to show the plot. Now let me run this. So this is the final step of building our AI model and optimizing it using various feature engineering processes, classifiers and encoders. So this is the class probabilities for sample 1 by different classifiers. So here the dark green color shows the people who are not promoted and the light green color shows the people who are being promoted. And this is the voting classifier and its average probabilities. So this is the visualization of the probabilities for the employees who are being promoted and who are not promoted, but the actual values we already saw using these classifiers over here. So there are 23,490 records of 2 columns consisting of employee ID as it is unique. So it shows the corresponding ID and the promotion status of the employees. So I'll just go up. So here we have created the model and we saw that the model took 10.4 seconds, and this is the learning of the model we have created. The model using the voting classifiers and XGBoost, CATBoost, Light GBM, gradient boosting or extreme gradient boosting instead of that. And after that we have the results and we worked on improving it. Then we get the result of promoted, and finally we have visualized using the plot our results. So this visualization of the data is just for our understanding, but how actually is the code implemented using the algorithms in real time is by integrating it using other softwares. So company will not use this code directly. So what they will do is they will create the model using the code that we have built, and then what they'll do is they might have another application that shows the information of the employees and their various parameters such as age and other things that we saw. Let me go to that section where we have looked around the data. So employee ID, number of training, age, previous year rating. So they might have an application that show the data. So there they can add a feature that predicting the promotion, and whenever they click on that, so this code is added in the backend. So before it shows the prediction of the employees or before it shows the list of the employees, this code is being implemented and the results are shown on the interface. So this is how artificial intelligence or machine learning algorithms helps the company to resolve the issue for their various business problems. So here it is the status of the promotion, whether the employee has to be promoted or not. So it is not about this problem. There are many real life business problems that can be resolved using artificial intelligence and machine learning. So these algorithms and these methods are added in the pipeline of a static software or an application, and it gives the output and the result that is the best prediction according to the analysis using the algorithm along with using the data set that is being provided by the organization, and it makes that software or the application as AI based application. So this is how we implement various scenarios using artificial intelligence.
And then coming to the comparison between artificial intelligence and machine learning, let's break it down into a couple of simple points. The first thing has to be definition. We've already looked at this, so let's quickly glance over it again. Well, basically, in the world of artificial intelligence, the intelligence part of it is actually defined when we talk about, the machines gaining knowledge and, the ability to actually learn something and pretty much apply what it has learned. This particular stored knowledge, that is where the word intelligence comes in. Coming to machine learning, again, machine learning basically involves the process very similar to artificial intelligence, where it's acquiring information, but then it's doing it in a very different way. There's something called repeated learning, where it actually learns on one particular concept again and again to master it and then understand what the concept actually is. Then coming to the second point, which is the technological aim of artificial intelligence and machine learning. Again, when it comes to AI, pretty much AI is concerned about, increasing chances of success in actually mimicking human intelligence. So it at a couple of stages, artificial intelligence is not concerned with how accurate it is, but it's a very different story when you come to machine learning, because when it comes to machine learning strives to increase the accuracy, and it would actually sideline the amount of success that it sees, because achieving accuracy in a mathematical model in terms of machine learning is actually a very good priority, and it is actually built for what it's supposed to do, and it does it very well. Coming to the third point, it is basically the goal of artificial intelligence and machine learning. When we talk about the goal of AI, it is to, again, as I've already told you, to simulate natural intelligence, to prove to humans that machines can be as good as humans, and this is done by solving complex problems and whatnot. Coming to machine learning, again, machine learning, the primary goal of machine learning is to actually learn from the data that it actually sees, understand what the data is, then perform certain tasks using the data. Since it does it repetitively, it understands it better and better every time it does it, and this increases the performance of that particular machine. And then the fourth point is how simpleton it actually is. Well, artificial intelligence, put in very simple terms, is basically that it is decision making on steroids, because to a computer what feels like a very complex convoluted entity, it is actually a very simple dumb machine which has been coded by the humankind, right? So artificial super intelligence claims to, if it has ever been founded, or if a machine chooses to start coding another machine, the decision making skills of an artificial intelligence entity will be equal to that of human intelligence or better than that as well. Coming to machine learning, again, machine learning basically allows a system or a computer to learn things from the data it sees, does it repetitively as you already know it. And coming to decision making, again, as we already talked about it, artificial intelligence is actually concerned with finding the optimal solution to an existing problem, but machine learning is used to see if the problem is actually pretty much optimal to work on or not. So it'll actually try to see if the solution, whatever it's obtained, is actually optimal, it's not optimal, it'll work, it'll not work, and much more. So here's a very subtle difference that you can see on your screen right now when it comes to artificial intelligence and machine learning. And then number 6 on this list is the outcome. So artificial intelligence, again, leads to developing system which basically will mimic human activities in certain circumstances. But then at this point of time, it can mimic everything apart from emotions and much more. In fact, it can detect emotions. That is how good it is. But for it to mimic human level emotion is impossible at this point of time. But then let's not say it's impossible in the future as well, because we do not know what the future holds. And then coming to machine learning involves this entire procedure where you will be creating algorithms which learn on their own. And here's the best part about the comparison: machine learning will help achieve artificial intelligence at the end of the day. So the outcome of artificial intelligence is to equal human intelligence, guys. So this brings us to the 7th point again, which is a very important point for all of you guys as learners. Because here's the average developer salary of an artificial intelligence developer and a machine learning engineer. An AI developer gets somewhere over 120,000 USD per year. And then an average salary of a machine learning engineer is over $100,000 per year as well. Well, this number is an average number for an associate to a junior or a middle intermediate level programmer. But do know that there are companies out there in the world which will actually pay 3 times, 4 times the number you see on your screen right now throughout the world. So they don't mind where you are, they don't mind what amount they're paying out if you're actually good with the skills and you have the right certification when it comes to especially artificial intelligence, machine learning, and concepts of data science, guys. And then coming to my final thoughts about this particular comparison, well, if it has to be put into one sentence, then know this: artificial intelligence will lead to intelligence at the end of the day, or some sort of wisdom. But if you're talking about machine learning again, it's all about acquiring knowledge, and this knowledge again is put into use when we talk about artificial intelligence in general. So to summarize the entire thing, guys, artificial intelligence will actually use all of the experience to acquire knowledge, to acquire skills, to learn it and understand how it has to apply all that knowledge. And machine learning will basically use all the experience it has from learning again and again and again to basically look for some pattern, understand what's going on there, to amplify the amount of knowledge it has gained, to see where it's like picking a needle in a haystack. So machine learning is where it's the process of picking the needle in a haystack. Where we're talking about artificial intelligence, it finds the fastest way, it finds the most important way where a human is not required to pick out that needle from the haystack, guys. So coming to when you have to use artificial intelligence, when to use machine learning, here is when you'll be using artificial intelligence. Artificial intelligence is required in situations where there is a requirement of precision, where there is a higher degree of precision is a very important requirement. And then you will use AI when you have faster decision making, logical decision handling, which does not require any human interference, guys. Because at the end of the day, emotions do come into place at a place of work, which might affect at the end of the day the work that the person is doing. But then if a machine does this, again, it cannot understand emotions. So your work will again remain very efficient because of the fact that it cannot have any emotional interference. And then coming to handling repetitive tasks, humans might get bored of doing the same thing again and again, but the machine does not. And then the next point is the reason why AI replaced a lot of jobs in the last year. It is that it can work 24/7, 365 days of the year without taking any single break, unless there's, of course, a breakdown in whatever it's doing. But then without a break, because humans again are very, very limited when it comes to working when you directly compare it to a machine, because machines can go years and years without a single break, but a human cannot, obviously, right? And then coming to risk analysis and risk taking, the machines can actually take a very good calculated decision based on so many things, so much mathematics, so much programming, and much more. Coming to machine learning is actually used where it can see the data and see a trend or a pattern that it can find. And another important reason is that there should be no human intervention here as well. The basic idea is to make the model self-sufficient enough so that it can understand the patterns and trends. And then, if there is a requirement for machine learning, then there'll definitely be some sort of requirement for continuous improvements, continuous learning, and hunting for more knowledge. So this brings us to the point which says that, improvement needed is actually linear. It does not have to be, learn, wait, forget, and no, it has to be learn, and keep going like that. That's what the point basically means. And then coming to the next point, it does not require any human intervention when it comes to adaptation as well. So humans take a lot of time to adapt, so let's say to a new climate, to a new technology they're learning on, everything in general, right? So humans need some time to go about doing that. Machines, well, if there is a requirement where you have to change certain programming language to something else, and nowadays there are tools which can do it automatically for you as well. And then industrial requirement are there, guys. So basically what we're trying to do is we're trying to perform predictive analytics in the world of manufacturing as well, like what product is doing good in what part of the world, why is this car selling so much more. So you have machines which can tell you all of this. You don't need any more humans to look at the numbers, plot graphs, and go about taking a judgment call, which might be a little inaccurate at the same time as well. So this brings us to the last section of this particular comparison: what companies use artificial intelligence and what companies use machine learning. Here's the list for artificial intelligence, guys. Everyone at Walmart Labs, we have KPMG, we have Microsoft, Genpact, Ericsson, Accenture, and millions of other companies, guys. So everyone in the top Fortune 500 company makes use of artificial intelligence in one or the other way. And then coming to machine learning, there's a lot of companies. Here again, there are thousands and thousands of companies which goes on to making use of machine learning on a daily basis. We have everyone from NetApp, we have General Electric, we have Google, Amazon. You can think about a lot, guys. Twitter, Facebook, again, Apple, Capgemini, IBM, and there are so many companies. I cannot fit all these guys in one particular slide, or in fact a couple of slides as well. So what do you guys think about this comparison? Do head to the comment section and do let me know. And then we need to understand why we require artificial intelligence, guys. Again, head to the comment section and let me know your top reasons of why you think we require artificial intelligence around us. I mean, human beings are the most intelligent species out there as of now. I mean, sure, that's debatable, but as of now, that's how it stands. Well, so why do we need artificial intelligence then? Well, let me tell you, humans are the most intelligent beings, but then there is only so much that we can do. For example, consider handling a huge amount of data, right? So in this world we live in, basically we live in a world which is a big data problem. So we have terabytes, we have hexabytes, we have petabytes worth of data coming in from each and every Fortune 500 firm, pretty much every single day, every single hour of every single day, in fact. So this data is growing exponentially, and then when the data is growing at this rate, you cannot expect a human being to be on the other side all the time to handle it. So this exponential growth of data is handled by machines very easily. And then when we talk about the variety of data as well, let's say you need to go on to merge some data, split some data, basically bifurcate some data. There are varieties of data. There's unstructured data, semi-structured data, structured data. So it might not be possible for one human or a team of human beings to basically go on to do this with the amount of data I just told you, right? So when you think about it practically, the variety of sources through which the data comes in is again unlimited almost. So having a machine on the other end of it to take the brutality of the variety of sources, the types of data, the amount of data is going to make life more efficient for the employer as well as the employee. And then we come to processing speed. Yes, again, I'm going to restate the same thing. Human beings might be the most intelligent beings out there, but then we do have machines which can be exponentially faster than humans when it comes to certain basic things, let it be mathematical calculations or anything as such. So this will provide unparalleled performance when we have to compare a human being's work directly to an artificial intelligent being's work. If we have to go on to directly juxtapose them. So this brings us to artificial intelligence developers. Who are these guys and what do they do? Well, you need to know this. Again, AI developers are basically computer science based people, and these people have to do a lot with coding, programming languages such as Python, languages such as R, and many other programming concepts. So why do they need all this programming? Well, this is basically to ensure that they can design, maintain, test, evaluate all the artificial intelligence solutions that certain organizations need. So let's say again, the AI technology which has gone into building Siri at Apple might be extremely different, is definitely very different than the technology which went into Tesla's autopilot, right? So these developers need to understand what the problem is, make sure they can formulate the problem and then formulate a solution for that problem as well, right? So designing a solution for an artificial intelligence requirement, and in fact maintaining that product after it's been designed, and evaluating to make sure that it is performing right where it should, is again very important aspects of an artificial intelligence developer. And I have a quick question for you guys on that note. So I'm pretty sure most of you guys use social media, right? It might be Facebook, it might be Instagram, it might be Twitter, and it might be all the other fancy social media apps out there. Coming to Facebook, let's see how AI developers pretty much work out here, right? So AI developers are pretty much responsible again to handle about 350 million photos a day which has been uploaded to Facebook, and they do a lot with face detection and image recognition as well. So let's say you and your friends decided to go on a vacation. Let's say there were 10 people of you and you clicked about 300 pictures. Now imagine tagging 10 of these people in all the 60 pictures, right? So again, 600 tags you have to do manually, and this is going to take many hours if you have to do this. But then Facebook already would understand who the person that is in the picture, where the picture was clicked, and much more. That is what geotagging means, and location options too. So this is told to you very subtle. It says, hey, was the picture clicked here? Is this person that? I mean, it'll show you the name of the person and it'll show you the location as well, and you might be like, yes. So at that point of time, you might not recognize and realize the power that's working behind it to get you all the details, right? Again, and another important thing is automatic friend suggestions, right? So let's say you added someone on any of their other applications. Now Facebook owns WhatsApp and Instagram. So let's say you're in touch with someone on WhatsApp where you've saved their number or something. Facebook will tell you, it'll give you a friend recommendation saying, hey, why don't you add that person on Facebook as well? So imagine all the processing that goes behind this particular thing. I mean, it's so subtle, as I mentioned on the first slide, that we don't even know it's there anymore. And then when you talk about Instagram, see, there are 95 million photos which get uploaded to Instagram, and handling that is definitely a task, right? And the best thing that Instagram is known for these days is customized advertisement. So you go to Amazon, you're searching for the latest mobile phone, or you're searching for a mobile cover, tempered glass, whatever it is. As soon as you come back to Instagram, it's going to show you one advertisement which is beautifully put together. You'll feel like clicking on the advertisement. Basically, that's how customized these advertisements are. And again, face detection and object recognition as well. So that plays a very important role in Instagram. Location recommendation systems, again, it will just tell you where the photo was clicked, what time the photo was clicked, and much more. Friend recommendation again. So let's say again you added someone on Facebook, or you guys just let's say there are two people who use Instagram. You guys have talked on another social media, but then you guys decided to meet for breakfast or dinner or whatever. And as soon as you come back to Instagram, it's going to give you a friend recommendation saying, why don't you add this person on Instagram? Again, how does this work? Artificial intelligence is at play, my dear viewers. And then coming to Twitter handles pretty much 6,000 tweets per second. Again, there has to be some form of pretty much a pipeline, a channel for the data to flow through in and out of the Twitter's storage area, where pretty much they need to understand, they need to work with this data, because it's not all about storing the data when it comes to Twitter, right? Because they perform sentiment analysis of every single tweet. They check if the tweet has a positive sentiment, a neutral sentiment, a negative sentiment, and what pretty much they can check to the depths of what person in which area liked or disliked this tweet on the face of the globe, basically. So this will add power to their organization. This will make sure that marketing can be done using Twitter, and in fact at the end of the day you're bringing more sessions to Twitter and they're happy. Coming to outreach analytics and customized marketing, again pretty much it'll tell you who your audience is, when they're watching your tweets, when they're reading it, and why as well, right? So coming to data analytics, again, you can pull out any number of statistics you want with respect to sentiment analysis of any tweet that's present on Twitter, guys. So think about it. We never knew a simple tweet can have this much of a complex circumstance in the back end when we talk about data and artificial intelligence, right? So this brings us to the most important aspect of this video, guys, which is the skills needed to become an AI developer. And let me tell you about three important skills that I think you should have. And the first one is all about mathematics and all about algorithms, guys. Because at the end of the day, you need to understand how numbers can, in fact, be used to achieve artificial intelligence. There is so much that you might not know, and to the intermediate level viewers, pretty much you will know how much of importance mathematics and statistics play a role. And then coming to algorithms, all the machine learning algorithms are again one step closer to making the machines intelligent. All concepts such as machine learning, deep learning, neural networks, all these are work under the same umbrella of artificial intelligence. All of these terms that I told you, all of their goals is to achieve artificial intelligence at the end of the day. So having very good mathematical skills and being well versed with the top algorithms which works with, again, based on statistics, is very vital. And second of the three most important skills is probability and statistics, guys. Why did I mention statistics again? Well, it is that important. You need to understand all the concepts, everything from the basics of correlation, all the way till how you can basically churn through data and make sure the data will give you insights that the naked eye might not tell you at all. So that is one of the reasons why statistics is extremely important. Coming to the world of probability, again, we need to sometimes understand that the values can be continuous, the values can be discrete. We need to find out what a possibility of occurrence of something is, right? So that, again, pretty much an artificial intelligence algorithm of today will not give you 100% accuracy all the time. It will give you an accuracy of 80, 90, 95, 98%. Again, this 98% is 9 on 10 probability. So it says that there are chances that it might fail 2 times out of 100 times. Again, probability, right? So this is a very important second skill to have. Coming to the third most important skill is having the knowledge of a programming language, guys, because again, there are languages like Python and R which form a very strong requirement when you have to learn about artificial intelligence and to help you become an AI developer. And you can either go on to learn Python, you can go on to learn R, but then beginners do prefer Python because R actually has a steep learning curve which some of the beginners might find difficult. But then do not worry, you can pick up either Python or R and you can be on your way to become an AI developer. And then coming to what R is majorly used for, well, R is actually used to do a lot of data plotting, a lot of statistics, and it involves a lot of bringing mathematics and programming together, is what I want to tell you guys. And then in a just again, most of the companies which basically has open positions for AI developers has these roles always present. So you need R and or Python, you're going to need statistics, you're going to need to work with algorithms, machine learning, and so much more. And on that note, here is a step-by-step guide on how you can become an artificial intelligence developer. Let us begin with step 1. Step 1 is pretty much, again, you understanding data structures in detail. You might be wondering why you need data structures, right? Again, if you understand how your data is stored, how your data is talking to the other entity that is present next to it, then you will understand how you can increase the performance of an algorithm by making it improve itself by drastically changing its understanding of its neighboring data. So understanding the right data structure, understanding when to use what data structure is extremely important. And this is step number 1. Guys, I urge you guys to pretty much whip out your pen and paper or make notes of these, as this will help you a lot in case if you guys are considering to becoming an AI developer. Coming to step number 2, again, as I mentioned, programming. So Python and R are the biggest names when it comes to a programming language to help achieve artificial intelligence. And programming knowledge is vital, guys. It is necessary. There is no work around this, and in fact, it is so much fun to work with, and I've been working on this for a couple of years and I absolutely love it. So, working on Python, working in R, there are libraries for machine learning, there is TensorFlow, there's Scikit-learn, there's PyTorch for neural networks, there's CNTK, that's the Microsoft's cognitive toolkit, and there are much more. There is Staffy, pretty much, guys. if I have to go on to naming the frameworks, I can keep on going. So when you think about this, there are so many things out there that you need to know, and this already forms the step number 2. So what comes after this? Well, step 3 is understanding a little bit of mathematics, guys. You need to understand, you need to have some sort of clarity on how numbers can actually be used to drive a data driven entity into making it self-sustain, because at the end of the day, statistics will play an extremely vital role in making sure your machine understands what's going on in it and derive some sort of continuous or differential inferences based on that. And then this brings us to step number 4. Step number 4 is the most important part, ladies and gentlemen, because here again you will be finding a problem. This is how you have to go by with step number 4. Find a problem which needs a solution. Let's say it might be a new startup that your friend is starting, or you just spotted a common problem across your daily life.
Just a quick info, guys. Test your knowledge of AI by answering this question. Which of the following is not a stage of AI? A. Predictive analytics. B. Diagnostic analytics. C. Cognitive analytics. D. All of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session.
So find that problem and make sure that you can formulate the problem and understand what the actual problem is. Now find a solution to that problem, and after you found the solution to that problem in a general human way, try to see if you can get the machine to do it. If you can implement artificial intelligence to do it almost as good as you, if not better, then your job is done. But then you need to understand that at the end of it, you becoming an artificial intelligence developer. So telling the world about it is again very important as well. So there is this website called as Kaggle, where pretty much it's an amazing community where people pretty much come together, give out their problems, give out solutions. There are challenges that you can take place in, and basically it's like a GitHub for programmers. Again, GitHub is the same thing, but when we talk about it, Kaggle is a little different, and I'm sure you guys will know how when you go on to explore Kaggle, which is your step number 4. So coming to step number 5. Step number 5 involves you to understand a little bit of cloud computing, because again, in today's world, half of the organizations we see around us are already scaled to the clouds. So everything from Amazon Web Services, we have GCP, which is Google Cloud Platform, we have Microsoft Azure, and much more. So taking artificial intelligence and scaling it right up in the sky through the clouds is now booming. And as my dear viewers, I have to tell you that having a good certification which will train you on all of these concepts is extremely vital. Working on AWS, working on GCP or Azure or any of these, so having cloud computing knowledge and bringing it together with artificial intelligence are very vital. And coming to step number 6. Step number 6 is again an important aspect for an AI developer, because not only you'll have to work with one single computer at point of time, you'll have to work with multiple entities, multiple computers, because at the end of the day, you're going to use this to exponentially increase your computing power. And this is basically done to understand how you can gain some sort of systematic knowledge onto scaling this artificial intelligence entity that you're developing onto a modern infrastructure. This is very vital, guys. So to revisit all the steps, here's a recap. Your step 1 will begin by understanding data structures. Step 2 with a programming language and some libraries. Step 3 is mathematics and statistics. Step 4 is finding a problem, analyzing it, and solving it. Again, the next step involves scaling artificial intelligence to the clouds, and the last step is to understand how you can make use of artificial intelligence on multiple machines at the same time, which is basically distributed computing. And to basically strengthen everything that I've said, here are some of the sample job descriptions that we can check out. So here's a job description for an artificial intelligence developer from the Penn State University in the United States of America. Their requirement is this. They say proficiency in Python is needed, experience with machine learning library TensorFlow, Infinite Cafe is needed, and pretty much they say proficiency in mathematics is needed, as we discussed, linear algebra, multivariate calculus, and much more. Skill is required in JavaScript, JavaScript or R, as we discussed, data structures, and ability to communicate technical topics to the people who might be non-technical audiences. And then cloud computing, AWS, as I told you, right? So we discussed all the 6-7 points, and again, you can see just in one job description, we can see all those 6 points reflecting onto us, right? And then in fact, coming to a researcher's jobs, we just checked out the artificial intelligence developer role. Let's check out the artificial intelligence researcher's role. Again, this comes from the Massachusetts Institute of Technology. It's called the Lincoln Laboratory. These guys as well, they require you to have experience in machine learning software, PyTorch, TensorFlow, MixNet, Scikit-learn, and much more. They would appreciate if you guys had experiences in working with large computer vision data sets, experience with big data, Hadoop, Spark, Elasticsearch, Cassandra. You'll be able to work in a multidisciplinary team environment. You have to have very good communication skills, oral skills, and sometimes you might have to travel as well. So guys, when we think about these two job descriptions of an AI developer and an AI researcher, again, when you come to think about it, we have validated all the points that we pretty much just discussed, right? And this brings us to the most important part of our live session, which is pretty much to tell you what the average salary is. So here is the average salary, guys. So pretty much, again, when you think about it, the average salary of a junior AI developer is somewhere around $80,000 in the USA, 7 lakhs per annum in India, 45,000 pounds in the UK, and then a senior AI developer has somewhere around $115,000 in the US, 15 lakhs per annum in India, and 60,000 pounds in the UK, guys. So these are some of the very big numbers that you can see when we talk about AI developers, AI researchers, and then, as I told you, this is a very lucrative career that you can pretty much jump onto, guys. Coming to the first question on these top deep learning interview questions set, the first question is, what are the differences between machine learning and deep learning? This is a very common question that's asked, and it is very important that you know the basic differences that lie between machine learning and deep learning. One very good commonality is that both of these are actually subsets of artificial intelligence, and deep learning itself is actually a part of machine learning. So when we talk about machine learning, we're making sure that we find a way where we're training machines with a lot of data. We give it some data and we hide some data from it, in fact, and we use the hidden data later, which we also call as the testing data, to make sure that the machine learns something, and to verify if it has actually learned from its experience. When it comes to deep learning, we try to find methodologies and ways where we can sort of trick the machine into making it think like a human being, making it use the human brain structure in terms of working. In the concepts of neural networks, the entire concept is named after neurons and the use of neurons as well, just because how very similar to how it works in the human brain. So this forms to be the basic difference between machine learning and deep learning. Moving on to the second question, it says, what is perceptron? Perceptron is a very important concept in deep learning because it actually matches what we see in an actual neuron in a human brain. So coming to how it works in deep learning, a perceptron actually receives inputs from a variety of entities, and then later it takes these entities, applies some transformations on it, what we call as functions. It applies functions on this, and then it becomes the output. So input, perceptron, applying function, output. That is how the order goes. So if you have to talk about when perceptron is mainly used, it is actually used when we go on to perform binary classification, where we use an input, we try to see if we can classify something based on the output. There's so many factors when we talk about the functions as well. There is weights, there is biases, and there's a lot of things in a neural network in deep learning that has a lot of impact. And in this system itself, perceptrons play a very important role to take an input and transform it and work on it to give you a valid output in the case of classifiers as well. Now, coming to question number 3, it states, how is deep learning better than machine learning? Both deep learning and machine learning are very powerful in their own ways. To solve most of the complex problem in a very simple way, machine learning has got it covered. But then when you talk about deep learning will overpower machine learning, especially when it comes to working with data that has huge number of dimensions. Think about an Excel sheet which has about, let's say, 100 columns with 35,000 entries each, something like that. So when there's a lot of data in your data set, and the dimensions are very large, deep learning will be exponentially efficient at working with things than compared to machine learning. So if your data is large, then a deep learning model will work very efficiently to actually solve it, handle it, and it'll make it easier for you to program and work with it at the same time as well. So this is how deep learning is having the upper hand over machine learning in a very simple and a concise way. Now, moving on to the fourth question, it states, what are some of the most used applications of deep learning? Again, this is a very common question that can be asked in your deep learning interviews. So at least make sure you mention at least 3 or 4 fields, and in fact I've put up around 6 fields on the screen right now. Everything from sentiment analysis, mostly Twitter, and all of that. Then we have computer vision to analyze graphics. Then we have automatic text generation, we have object detection, we have NLP, natural language processing, and image recognition. There are more fields. You can name about 10 to 12 offhand if you have worked a little bit on deep learning, but then it doesn't it doesn't really add a lot of value if you just list 10 to 12. So rather just tell 5 or 6 and just explain 1 or 2 lines about what each of them mean. That way the interviewer has an idea that you are concrete with respect to all the concepts there as well. Now with this we can come to question number 5 that states, what is the meaning of overfitting? Overfitting and underfitting are actually 2 very common issues that have to be dealt with whenever you're working with data sets and whenever you're working with deep learning. Overfitting, as the name suggests, is a scenario where you have a deep learning algorithm, and your deep learning algorithm is looking very hard into your data, and it is trying to hunt for meaning. It is trying to find some meaningful correlations in between the data in the data set. Now in a way, what happens in overfitting is that it'll start vigorously hunting for the data, and this makes it pick up noise, what we call as noise, rather than any sort of useful data. So with this noise, it hurts the efficiency, it hurts the detection capacity of the model. So rather than picking up any useful valid information, your model will start picking up noise, and that is not a good thing. So what happens is, at the end of the day, you'll have a very high variance in your data and a very low bias. This way, of course, you would already know that your model will be very, very inaccurate in terms of detection, and very inefficient at detecting new things, even if it has a good level of accuracy as well. So when you think about it, overfitting needs to be fixed, and underfitting is just the reverse of this. Anyway, coming on to the 6th question, it says, what are activation functions? Activation functions are very important entities in deep learning, because these are the actual functions that will take your input and make sure that you have something usable on it. So the transformations that happen, right, it is all because of the activation function. So what an activation function is basically is that it has the capability to decide if a neuron actually needs activation or not in that particular array, in that particular set of neurons, to see if there has to be anything modeled from that particular neuron in the chain in the neural network, or if it adds a value to the next set of neurons as well. So this is actually done by calculating the weighted sum of it and then taking the bias as well. So at the end of the day, whenever you're making use of an activation function, the model output will be non-linear. And if you have to talk about the types of activation functions as well, so there's rectified linear unit, or ReLU for short. You have softmax, sigmoid, linear, tanh, and many others as well. So it adds value that you answer it in a way where you tell what activation functions are, how they're calculated, what the output will look like, and what are the types of activation functions as well. With this, we come to the 7th question that states, what is Fourier transforms that is used in deep learning? Fourier transform is very, very vital to deep learning, because it is one of these packages that is used to manage and work with a lot of data when we work with deep learning. As you already know, in deep learning, we will be working with huge data sets. So we need methods and tools and techniques where we can process these in real time, and we can make sure that we can handle it and work with it easily and quickly as well. So Fourier transforms is one of these packages that will make sure that you have high efficiency whenever you're working with data. And with Fourier transforms, your model is now open to a lot of signals where you can have the data processed from multiple entities, and just make sure that you're opening up a dimension when you're working with the data as well. So Fourier transforms are a very, very vital part of deep learning. Now, with this, we can come to question number 8 that states, what are the steps involved in training a perceptron in deep learning? There are about 5 to 6 steps whenever we have to talk about the perceptron learning or training a perceptron, as it's also called as. And these are the 5 steps. Firstly, the first step is always to initialize all the thresholds and the weights of the network. Then, of course, we'll be providing the actual inputs. The outputs are calculated based on a lot of things. Then we have back propagation, all the algorithms that run in the back end. And after which we'll have the steps where we'll be upgrading the weights in every single step. So after the weights are upgraded, then we'll again provide another set of inputs. We'll be calculating the weights again, and this goes on from the starting initial node all the way till the last node of the output neural network. And this is how simple it is to actually train a perceptron in deep learning. Now with this, we can move on to the 9th question that states, what is the use of the loss function? Whenever we talk about neural networks and deep learning, we need a methodology, we need a number, we need a numeric where we have the ability to see if the model is working towards its goal or not, right? So the loss function is a measure of accuracy here as well, because we're trying to see if the neural network actually learned something useful from the data or not. And a loss function is a negative metric where if the loss function's value is less, then it's good for the model. If the loss function value is high, it means that the model is not performing well. So at all times, it is very vital that you mention that the loss function has to be kept to a minimal extent. Now with this, we can come to the 10th question that states, what are some of the deep learning frameworks or tools that you have used in the past? Now this is a very common question that's asked in the interviews, because they want to find out, the interviewers want to find out about the experience that you have with all of these tools. So just make sure to mention of all the frameworks, tools and techniques that you might have used in your projects or your certification programs, or whatever it is that you have used, the methodologies that you have used to learn. Of course, there are many top deep learning frameworks out there. We have an entire video on that on the channel as well, so make sure to check that out after this video. Among the top deep learning frameworks, we have TensorFlow, we have Keras, we have PyTorch, we have Cafe2, we have CNTK, that's Microsoft's cognitive toolkit. Then we have MXNet, we have Theanon, we have many others. In fact, you can list about 12 to 15 very good top deep learning frameworks out there. But then just make sure to mention 3 or 4. But then if you of course used more than that, then do make sure you mention that as well. But then make sure that you are very honest about it, and do not I would suggest that you do not state a deep learning framework that you might have not used, as that might lead to you being asked questions on that, and you not being able to answer as well. So make sure to take care about that. Now with this, we can come to the 11th question that states, what is the use of the swish function? So the swish function is nothing but an activation function, as we discussed a while ago. So it's something called as a self-gated activation function, and it is developed by the people at Google. So one thing to note about the swish function is that it is extremely popular because Google has put up a very good claim that it outperforms all of the other activation functions that exists today in terms of efficiency. So we discussed the different types of activation functions as well, right? Tanich, Relu, and all of these. So then Google came about, they devised an algorithm, the activation function algorithm, and they put up saying that this will outperform everything else that already exists. So that is one of the reasons why this particular activation function has seen so much limelight as well.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
Now with this, we can come to the 12th question that states, what are autoencoders? Autoencoders itself are artificial neural networks, and this is something which is very important that you know. And of course, they do not have any supervision, as they have the ability to automatically try and map inputs and to find out outputs and work with it on their own. So it's a very interesting concept to work with autoencoders, and these are very efficient as well. But then when we talk about autoencoders, it is very vital that we talk about two important things. One is the encoder and one is the decoder. These two are the very important important entities that we have to discuss about. An encoder will make sure that the input is taken and it is converted into a format which is understood by the neural network, into an internal computation state, of course. And then we have the decoder, which does the exact opposite of this. It will take the computational state data and it will make sure to convert it back into the output. So encoders, even though the name only has encoders, there are two operations that's going on. One is the encoder operation and the other one is the decoder operation. Now with this, we can check out the 13th question that states, what are the steps that have to be taken whenever you make use of a gradient descent algorithm. There are actually 5 to 6 steps that have to be discussed whenever we talk about initializing and making use of the gradient descent algorithm. The first step is always, you have to initialize all the biases and weights for the network as well. And after you have initialized all the biases, you have to send the input data throughout the network, which forms to be, of course, the input layer, the first layer of your neural network. And then we'll actually calculate the loss function, right? So you'll have an expected value that you're expecting at that point of time, and there will be a value which is predicted by the model as well. So calculating the difference between this will give you the error of how far away the neural network is from the actual goal. Now, after that, you will actually change all the values in the neurons to make sure or to find ways where you can minimize this loss function, this difference that we just found out in step 3. And after which, of course, this entire process is an iterative process. You'll be looping it and doing across multiple iterations to find out what biases, what weights, and how best you can do to keep the loss function at its minimum. So these are some of the steps that have to be followed whenever you're working with gradient descent algorithm as well. So with this, we can come to the 14th question that states, differentiate between a single layer perceptron and a multi-layer perceptron. We already discussed that, if we're talking about a perceptron, in case if it's a single layer perceptron, it will not have the ability to classify nonlinear data for us, but then a multi-layer perceptron completely can, classify nonlinear data. And a single layer perceptron is a bit limited in one aspect where, the number of parameter that it takes in is very less when you compare to a multi-layer perceptron. And this in big deep learning models can have a very, very, disastrous effect as well for efficiency, for effective working and whatnot. So again, for the second point, I think multi-layer perceptron wins. And when you talk about the third difference, of course, a single layer perceptron has many things that it can do well. But if we are talking about efficiency when making use of large data, again, a multi-layer perceptron of course takes the higher end because it is extremely efficient to work with in the case of large data sets. Now with this, we can come to the next question that states, what is data normalization in deep learning? So data normalization is a very, very important step. It is actually a pre-processing step where we try to make sure, we can move around the data, rearrange the data, and we can make sure to refit and pack this data into one particular range. This is the entire process of normalization. Why we do this is to make sure that, if your data is in one particular range, it means that your network has the ability to learn very effectively and be very efficient as well. So, when you're performing steps like backpropagation, having a data in a very structured range, a specific range, will make sure that your network can learn that much faster as well. So these are one or two reasons why this pre-processing step that we take called as data normalization is very important. Now with this, we can come to the 16th question that states, what is forward propagation? So backward propagation is the scenario where, we work from the output layer to the input layer, and here in forward propagation, it is the exact reverse. We follow in the order of the neural network. So, we go from the input layers to the hidden layers and then the output layer. So, when you're talking about a complex neural network, there'll be more than one hidden layer. So for every hidden layer, the output of the activation function is actually calculated, and this is done until the next layer can actually be processed. The reason they call it forward propagation, as I just mentioned, is to make sure we work from the input and towards the output. And this is the exact opposite of the backward propagation algorithm as well. So to make sure that we use the output of the activation function and to calculate it for the next layers, forward propagation is very, very important. Now, with this, we can check out the 17th question. Again, coming back to the very main important question, your interview could start with this question itself. What is backpropagation? So, backpropagation, instead of talking about what, the first thing you have to always discuss is why backpropagation is even important, right? So, it is to make sure that we keep the loss function or the cost function less, and to see how the values changes whenever we, work with a variety of biases, a variety of weights. Whenever we change all of these, even a slight change can have a very big impact on your model. To understand how these work, we require the backpropagation. It's called backpropagation, of course, because it starts from the output layer, works backwards towards the input layer direction. So how is backpropagation calculated? Well, it is very easily calculated whenever you work by understanding the gradient that is calculated at every single hidden layer itself. So it's as easy and straightforward as that. Now, with this, we can check out the 18th question that states, what are hyperparameters in deep learning? So when you talk about hyperparameters, even though the term is very complex, they're nothing but variables that are actually used in deep learning to actually determine the structure of a neural network. So these variables are put into place to make sure that we have an easy way of understanding so many different factors and parameters in the deep learning model, be it the number of hidden layers that are present, or the learning rate of the model, and much more. So hyperparameters are very important variables that will give us a lot of insight into how the model or the neural network is functioning as well. So moving on to the next question, it states, how can hyperparameters be trained in neural networks? So training a hyperparameter is very important, and understanding how you can convey this to the interviewer is also very important, because these are long procedures and your ability to concisely answer it is very important. So, to train a hyperparameter will require 4 very important components. It's the batch size, the number of epochs, and there's something called as the momentum, and there's a metric called as the learning rate. So what happens in batch size is that we'll take the input, we'll split it into batches. Batch size can be varied depending on however it is required based on the efficiency and a lot of other things. These batches can be cut into further sub batches as well, if that is the requirement. So instead of pushing all the input into a concurrent pipeline, we just make sure to dig it up into batches and then vary it across. Now, when you talk about epoch, an epoch is basically a denotion of how many times the training data is run through the neural networks where it can train. So the number of epochs is the number of iterations at which the model, the neural network trains as well. So it's an iterative process. The number will depend on so many different factors. Doesn't mean that if you have a large number of epochs that your model will be very, very accurate with every single iteration. It will go up to a point, and then of course your model will work, in fact, in the opposite direction. Now, when you talk about momentum is actually put into place where we have an idea to check out what happens in the next consecutive steps. Whenever data is being moved around in a neural network, it is vital to understand what happens next, right? So, there is no point if your model is very inefficient where it's passing around data and not driving any momentum from it. So momentum is this particular track where we make sure we understand what's happening next as well. Now, coming to the last component, it's a very important component. It's the learning rate. Learning rate is what we're all after when you work with deep learning, because this is used as a very important parameter where we're trying to denote what is the time that's required to actually update all the parameters when your model learns and when your neural network is ready to take in certain inputs and give you meaningful outputs as well. So these, 4 form to be very, very vital, very important components in the world of deep learning whenever we go on to train hyperparameters. Now, with this, we can come to the 20th question that states, what is the meaning of a dropout in deep learning? Now, dropout might seem like a very common term, but it is actually a technique in the world of deep learning. Dropouts are a very important technique, in fact, because these are used to avoid overfitting. Overfitting and underfitting are common problems, as we discussed a couple of questions ago. So to avoid overfitting, to make sure that your model doesn't hunt for noise, what we actually do is, we purposefully remove a bit of data which might not be useful for the model to learn as well. So if you have a dropout value to be very low, it will have a minimal effect on learning because you're not removing enough data and your model can still go towards overfitting. But then if you remove a lot of data, then what will happen is the model will not have enough data to learn. So it will underlearn and then cause inefficiency as well. So this value, right, this drop off value should be very, very vital, because if you have it too low, it will not have an impact. If you have it too high, then your model will not learn effectively anymore. So understanding this is a key concept. Now, coming on to the 21st question, it states, what are tensors? Tensors, you might have heard of these. These are another name of arrays, guys. So tensors are actually multi-dimensional arrays that are mostly used in deep learning, where we have to represent data across either one dimension or in fact multiple dimensions as well. So why can't we just call them arrays and not tensors, right? So tensors have the specialty of a name because they have been very famous. They have been very vital whenever we work with data of higher dimensions. So one very big advantage when we talk about tensors is that whenever we make use of it in any of the programming languages, right, the syntax is very readable. It's a very high level syntax. So what that does is it gives us a clear picture of tensors, even though if we do not have very high amount of training in terms of making use of tensors or its terminology. As soon as we look at the programs, we'll have a keen idea about what tensors are and what they might be doing in the program as well. So this is one very good advantage when it comes to working with these multidimensional arrays called as tensors. Now we can move on to the 22nd question that states, what is the meaning of model capacity in deep learning? Model capacity is again a very important metric that we have to discuss about, because model capacity deals with the capacity of the model to actually take in a variety of mapping functions. So how many mapping functions can your model handle? How many can it concurrently work with as well? One thing we drive out of this metric is that higher the model capacity, it literally means that there is a large amount of information that can be stored and worked with in the network. If the model capacity is low, as the name suggests, it means it cannot handle and effectively a large amount of information at a time as well. So model capacity is something which is very straightforward, but yet it forms to be a very important concept in deep learning. Now with this, we can come to the 23rd question that states, what is the Boltzmann machine? Boltzmann machine sounds very complex, but it is actually a type of a neural network, that we call as an RNN, or a recurrent neural network.
Just a quick info, guys. Test your knowledge of AI by answering this question. What are the main goals of AI? A. Create expert systems. B. Implement human intelligence in machines. C. Both A and B option. D. None of the above. Comment your answer in the comment section below. Subscribe to Intellipaat to know the right answer. Now, let's continue with the session,
where we make use of binary decisions, biases, and to do a lot of functioning and working for us as well. So Boltzmann machines are, like as I mentioned, RNNs. They are hooked together to create something that we call as DBNs, or deep belief networks. So these deep belief networks are extremely sophisticated. They have multiple number of hidden layers, and they're put into place because we have complex problems that require effective solving. So the entire goal of deep learning, in fact, is that we have extremely complicated problems, and we need to find ways to make use of the power of computing to simplify that to a good extent for us. And a Boltzmann machine will do exactly that. Now, after understanding this, we need to check out what are the advantages of making use of one of the top deep learning frameworks out there called TensorFlow. So, of course, this could be a very important question in case if you work with TensorFlow, because understanding the advantages of it is very vital. So TensorFlow has many advantages, and to me the most important advantage is where it will give you a lot of flexibility and platform independence whenever you're working with it. The platform independence is very vital because we all have multiple operating systems, multiple platforms that we work on, and of course, so it has the ability to power through and train on both CPU and your graphical processing unit as well. And with new technologies with GPUs, it just makes it very efficient to work with tensors too. And then when we talk about auto differentiation and the features it brings with it, is again a huge impact. When we talk about threads and its ability to handle asynchronous computation, this is where TensorFlow wins over many other deep learning frameworks as well. The second most important advantage to me is that it's open source. It has a beautifully large community, so you don't have to pay for it, but then at the end of the day, there are so many things that are being added in terms of features, technologies, fixes, and so much more. And this entire community of open source is just a beautiful thing, and I'm sure you can relate to this if you work with TensorFlow as well. So with this, we come to the 25th question that states, what is a computational graph in deep learning? So a computational graph, as the name suggests, is a scenario, or is a graph itself, where we try to take inputs, arrange them into meaningful entities called as nodes, and later create a graph structure out of it. So these are done to simplify certain mathematical calculations as to visualize them better. So, in terms of deep learning and in terms of backend functionality, it helps a lot whenever we're working with parallel processing, as it provides a huge performance boost over a single threaded performance in terms of making use of actual computational graphs. As your processing power is now 2, 3, 4, 5, or 10 times, 10 folds better than how it was before as well. So, computational graphs are very, very important units when it comes to working with deep learning. Now, we can come to the 26th question that states, what are CNNs? CNNs and RNNs are very different types of neural networks. CNN stands for convolution neural network, while an RNN stands for recurrent neural networks. Now, coming to the talk of CNNs, CNNs are mostly used to perform visual analysis or working with a lot of images and classification as well. You can have multiple images of many channels as well. So when we talk about images and channels, mostly we talk about colored images and black and white images. Colored images will have like 3 channels: red, green, and blue, RGB structure, and so much more as well, right? So a CNN has the ability to easily work with, classify, and give you meaningful outputs on all of these images and visual data. Now, if we talk about a little bit more about CNNs, the next question can be saying, what are the various layers that are present in a convolutional neural network? So when the talk is of this, understand that there are 4 important layers in a convolutional neural network. One is the convolution layer, we have the ReLU layer, or the activation function layer as it's also called. Then we have the pooling layer and the connectedness layer. So when we talk about the convolutional layer, this is where we apply things and entities called as filters across the main data to have them as parameters to teach and train the network. So after the convolution step is done, we'll use the activation function to squish it and bring it into a range which is workable and understandable by the neural network. After the activation function is done, then there's something called as pooling. Pooling is where again we shrink the data to make sure we are not losing any of the existing data, and what happens after convolution is we lose certain data as well. So we do stuffing in the pooling layer as well to make sure that we add certain bits, dummy bits, to make sure that the size of the image is actually maintained after every single iteration. So with every iteration the image shrinks a little, and with padding we make sure that we are not letting it shrink out of context as well. And then when we're talking about the 4th important layer of the convolutional neural network, it's connectedness. Here we're just making sure that all of the activation functions are applied correctly by making use of the bias and generally checking that the entire neural network is connected thoroughly and it's working as expected as well. So as the name suggests, this is a very important layer to verify the understanding of the neural network. So these are the 4 very, very important layers that you have to know about in this particular order itself. Whenever you're mentioning the working of it, the questions can be like, what is the working of a CNN, or what are the layers that are present as well. So this will develop as both of those questions. Now, when you talk about RNN, as I just mentioned, next question can be, what is an RNN in deep learning? So RNN, as I discussed, it stands for recurrent neural networks, and unlike CNNs, the working here is very different. The use of it is very different because RNNs, or recurrent neural networks, are very, very efficient at working with a lot of string data, textual data, genome data, handwriting data, and much more. So if you have already worked with any basic use cases where you're performing, let's say, handwriting prediction or detection of handwritten letters or whatnot, then there's a good chance that you've made use of an RNN. RNN uses the technique called as backpropagation that we've already discussed for all its training requirements, and it is very, very effective at doing this as well. Just like how CNN is very effective for working with images, it shows similar girth whenever you're working with textual data as well. So this is again a very important aspect in deep learning. Now with this we can come to the 29th question that says, what is a vanishing gradient whenever you make use of recurrent neural networks? A vanishing gradient, to be honest, can be considered as a scenario, because we already saw in the last answer that RNNs make use of backpropagation, right? So if there is backpropagation, then there's the calculation of the gradients at every single step. And whenever we work with backpropagation, whenever we calculate gradients, they tend to get smaller and smaller as the data works backwards from the output layer to the input layer. So since the value becomes extremely smaller towards the end as we approach the input layer, it causes a problem. So this basically means that your model will learn very slowly and it cannot be efficient. It will underlearn sometimes and it will cause a lot of problems. So this is a scenario of occurrence where your gradient values are becoming very low, and that scenario is what we call as the vanishing gradient. Now, I hope this is clear. So with this, we can move on to the 30th question, which states, what is exploding gradient descent in deep learning? Just like vanishing gradient, exploding gradients are another issue which work in a very different way, because here is a scenario where we're clumping up all of the gradients. Means what it does is it will create a large number of updates for all of the weights in the model whenever it's training. So your model weights are being updated constantly more than required, and and we already know the working of gradient descent, right? So it's based on the condition to keep all of these updates small to make sure that your upgrades are controlled, and only then can your gradient descent have some meaningful impact on your deep learning model. So with this, we have to understand that whenever you control these updates that happen to the weights of the model, right, this will have a huge impact, in fact direct impact on the efficiency of the model as well. So this is another scenario, what we call as the exploding gradient descent, where we have large number of updates that happen to the weights, which make it very, very inefficient at the end of the day too. Now with this, we can move on to the 31st question. So the 31st question states, what is the use of LSTM? LSTM is again a very important type of recurring neural network that we use to perform a variety of operations whenever we work with textual data and string data, as I just mentioned a couple of slides ago. So it stands for long short-term memory, and the working of it is slightly different because it makes use of something called as feedback chains, where it gives the network the ability to perform like another general purpose computing entity as well. So when it comes to that, it is very efficient at working working with a lot of data, especially when we're talking about genome data and genomic sciences. LSTMs are very efficient at working with that as well. So again, just being a type of another RNN, it sort of trickles down to having all of the features and the general working of RNNs too. Now with this, we can come to the 32nd question that states, where are autoencoders used? So we checked out autoencoders before, but then there might be a follow-up question to that stating where they are actually used, right? So you have to understand that autoencoders again have a lot of usage in the real world. So whenever we talk about it, you can have about 10 to 15 uses that of course that you might know already, but then it is vital that you at least mention 3 or 4 very popular applications of it as well. So let's say in the real world, if you have a black and white image and you want to have it colored out to what it actually was in its real life, then adding color to black and white images are very important use cases. And if you have any other old images where you have to remove noise, autoencoders are used here too. And then when you talk about dimensionality reduction and feature removal or feature variation as well, autoencoders seem to be very popular. And in fact, more than popular, they're popular for a reason, that is because they're efficient at handling all of these tasks. So make sure you mention all of these real life applications which are very popularly used as well. So with this, we can come to the 33rd question that states, what are the type of autoencoders? So, there's actually 4 types of autoencoders that you have to mention. One is the deep autoencoders, we have convolutional autoencoders, we have sparse autoencoders, and of course we have the contractive autoencoders as well. So you really don't have to explain when you're asked for the types, but then it might add value if you can just state 1 or 2 sentences about each. But then it is very important that you mention all the 4 types that exist for autoencoders as well. So moving on, we come to the 34th question that states, what is a restricted Boltzmann machine, or an RBM for short? An RBM is actually a graph, if you have to talk about it in general. It's a graphical based model that we make use of in deep learning today, and it does a lot of things and can do a lot of things efficiently as well. So when you have to talk about performing operations such as classifications, or let's say regression, dimensionality reduction, be it collaborative filtering, topic modeling, or all of these operations that need to be performed that require an algorithm to do it, an RBM can do it very effectively in today's world of deep learning, where it can make use of the computation power of today and work with it effectively as well. So an RBM, a very, very, again, I know there's a lot of efficient being used in the case of deep learning, but then of course an RBM is very tricky to work with at the same time, but then the output that it provides is worth the effort. Coming to the 35th question, it states, what are some of the limitations of deep learning? We've been talking about advantages for 34 questions now. So it is very vital that you know what some of the limitations or the disadvantages are. There are not many disadvantages, but then there are a few disadvantages as well. The first one is, whenever you expect very good, very accurate output, you need large amounts of data, and your network has to have the capability to work with large amounts of data effectively as well. So that is one disadvantage. To gathering all the data might not be the case in all the factors. And then when we talk about how complex it is to implement, for example, an RBM is pretty complex for a beginner to work with and to get it working efficiently as well. So in a couple of cases, not just RBMs, RBMs might be easy to you, but then there are many concepts where it can be a little convolutional, it can be a little confusing, and it can be a bit complex to work with as well. So that is one of the disadvantages. And just like any other deep learning concept, your main focus always will be to make sure that your models are very efficient. So you'll be hunting on keeping that loss function down, you'll be hunting on making sure that your goal parameter is being met, and it is being met in a way where your model is very accurate, it is not overfitting a lot, it is not underfitting a lot, and it is performing as it should at its best. So hunting for these can take a lot of time, and it is not as simple as it's put out as well. So in case if you have had first-hand experiences working with deep learning, you will know what I mean with this. Now, we can come to the 26th question that states, what are the varieties of gradient descent that are available, or what are the variants of gradient descent? There are actually three very important distinctions whenever we talk about gradient descent. One is the SGD, or the stochastic gradient descent, then we have the BGD, or the batch gradient descent, and then we have the mini batch gradient descent. And whenever the talk is about stochastic gradient descent, the first important thing is that we only make use of one training example, and we calculate gradients based upon that. We update all the parameters based upon this single entity, this single example that we have. But then this is not the case when we talk about batch gradient descent, because once we calculate a gradient for batch descent, as the name suggests, we'll take the entire data set and calculate the gradient for all of the entities that are present in that data set, and then of course we update all the parameters one after the other in every iteration as well. And mini batch is again very similar to batch gradient descent, but then the batches itself are broken down into digestible pieces or small sized chunks, or small sized batches as it's also called, and then work with it just like how if it was a stochastic gradient descent, where we again take a simple training example and we make sure that we calculate gradient, update all the parameters, and perform the same operations for different values across a variety of iteration as well. So these are some of the three important gradient descent, stochastic gradient descent, batch gradient descent, and mini batch gradient descent that you have to mention when you ask this question. So with this, we can check out the next question that states, why is mini batch gradient descent so popular? So why is mini batch so popular, right? So this is again a question that's asked a lot. In fact, it's a very frequent question if you talk about the previous question or a follow-up to that as well. So one reason why it is popular is, of course, because it is very efficient when you directly compare it against stochastic gradient descent. And when we talk about avoiding the concept of local minima, mini batch gradient descent will help, because we'll be approximating all of the gradient values for the entire data set, and this is done because we use a concept called as generalization rather than hunting for specific values every single time by doing this concept where we're finding the flat minima and working with it. So what this does is it will make sure that we can avoid the local minima, we can approximate the gradient for the entire data set by the process of generalization.
These are available in the description box below.
Punch without having much effort into it. So that's one advantage of mini batch gradient descent. Now with this, we can check out the 38th question that states, what are deep autoencoders, right? So we checked out regular autoencoders. So what are deep autoencoders? Deep autoencoders are actually an extension of the regular autoencoders that we just checked out before. So here the difference lies where, the first layer is actually responsible for what we call as the first order function of the input. And if you have a second layer, then the second layer will take care of what we call as second ordered functions. Third layer will have a third order function. Fourth layer will have fourth ordered functions, and so on. So it goes on like that. So when we talk about a deep autoencoder, it is basically a combination of making use of two or more symmetrical DBNs that we discussed, right? So DBN is a deep belief network. So here in an autoencoder, we'll combine two or more of these deep belief networks, where let's say the first 5 layers is kind of considered as the shallow layers, which will take care of the encoding aspect of it, and the last 5 layers, or in fact all of the other layers, can handle the decoding part as well. We checked out that encoding and decoding are two very vital aspects of autoencoders, and this is where deep autoencoders shine, and how they are complementary to the regular autoencoder as well. So with this, we can come to the 39th question that states, why is the leaky ReLU function used in deep learning? So ReLU stands for rectified linear unit. So leaky ReLU is also called as LREL. In case if you asked about LREL, make sure to understand that it is the same as leaky ReLU. So, we use leaky ReLU in a concept, let's say, where we have the input values, and if they, if the input values are all less than 0, right? So what we try to do is we allow the passage of, small sized negative values to the function, where we use it to actually manage the function, work with it, and then, to drive the activation based upon that as well. So whatever neurons require activation, if the values are less than 0, leaky ReLU is very popular there, which will allow the usage of small negative values and drive meaning out of that at the end of the day. So after understanding leaky ReLU, it becomes very vital that you check out some of the examples of supervised learning algorithms. So, this is a machine learning question, but then we've seen this has been asked a lot in deep learning interviews as well. So what are some of the examples of supervised learning algorithms in deep learning is the question. You have to understand that there are three main supervised learning algorithms in deep learning. One is ANN's artificial neural networks, then you have CNN and RNN, convolutional neural networks, and recurrent neural networks respectively. So you have to mention the three types or the three main supervised learning algorithms usages in the field of deep learning as well, and these will cover all of the subfields that come under them. CNN has a lot under it as well. RNN has a lot of types, as we just checked out in the previous set of questions, but then mentioning these three should be more than sufficient. Now, there can be a follow-up question to this stating, okay, what about unsupervised learning algorithms? Can you state examples of that in deep learning? Well, yes, there are three very main important unsupervised learning algorithms in deep learning. We've checked all of these out. One is the autoencoders, then we have the Boltzmann machine, and of course, we have something called as self-organizing maps as well. So these three form to be very, very important unsupervised learning algorithms that find a lot of usage in the real world when we make use of deep learning and its concept too. Coming to the 42nd question, it states, can we initialize the weights of a network to start from 0? Can the weight be 0? The answer is very tricky. You might be, leaning to say no, but then understand that the answer is yes. It is actually possible to start with 0 initialization. But then, of course, it is not recommended to use, because setting it up to 0 will make sure that your neurons will be giving the same output and the same descent and the same gradients whenever we go on to make use of back propagation. So the learning is almost next to 0 or next to nothing here. What this means is that your network cannot learn at all if we start with 0, because there is no asymmetry, right? So each of the neurons have to be unique from each other, and they have to do a unique task that is assigned to them. So if everything is set to 0, then when we work with back propagation, there is no way to tell apart from one neuron to the other. So the learning rate is 0, as I just mentioned, and it really doesn't work. But then yes, it is of course possible where you can have 0 initialization done to the weights before working with the network as well. So after understanding this, it becomes very vital that you understand something called as same padding and valid padding in CNN. So you remember CNN is used for image classification as well, and padding is done as a part of working with images. So whenever we perform iterations, with every iteration the images are being shrunken in size. To make sure that they're not shrunken beyond usage, we do padding, where we apply more dimension to the existing matrix, right? So there are two types of it. One is valid padding, and we have same padding. Valid padding is where it is used where it is where there is no requirement for padding actually. So the output matrix will have the dimension n minus f plus 1 multiplied with n minus f plus 1, which happens after the convolutional state. And with case of same padding, padding elements are common padding elements, in fact, are added across all of the output matrix as well. So same padding is a situation where we try to match the dimension of the input matrix as well, but then valid padding might not be matched because it can have its dimension on its own, which is calculated by the formula given there as well. So same padding will try to match all of the elements after padding to make sure that your output matrix will have the same dimension as the input matrix. So that is the basic difference that lies between valid padding and same padding. Now, it is very important that you might be asked this question, so make sure to concentrate on this as well. So what are some of the applications of transfer learning in the case of deep learning? Transfer learning is a very popular scenario where we take a large model, we train it with a huge data set, yes, of course, and then we make sure to use this model, which has learnt on very complex data, large amounts of data, to work on simpler data set. So what this does is its efficiency is boosted to a very high extent because it has actually trained on complex data, but it is now working on simple data. So this way it is very efficient, it is very accurate, and in fact transfer learning is being implemented in our daily lives very well as well. But then if you have to talk about the complex use cases of it, we have BERT, we have ResNet, we have GPT-2, we have VGG16, and many other popular examples of where transfer learning are made use of and how efficient and effective they are as well. But then understand the basic working of it. So you train your model on something very complex, but then you actually show simpler data to it at the end of the day where it can work with it effectively and be more efficient to it. It's as simple as that. Now with this we can check out the 45th question that states how is the transformer architecture better than recurrent neural networks in deep learning? So, whenever we make use of something called as sequential programming, there are two important things you have to be concerned with. One is how much of processing power you're making use of at every single point of time. And so what is the difficulty that you're facing whenever you have to work with parallel execution, right? So sequential processing will raise these two red flags. And what this does is this actually gave away these two concerns with the primary reasons why we have something called as a transformer architecture now. So in a transformer architecture, we have something called as the attention mechanism. The attention mechanism will take all of the dependencies that are available and it will map in between each of the sentences whenever things have to be processed as well. So when we talk about concepts such as NLP, right, natural language processing, here since the data is mostly sequential, it'll of course bring up the two concerns as mentioned above. But then by making use of these attention mechanism, by mapping all of the dependencies, by making sure your model can recognize these entities faster and map it across to a dictionary faster, let's say, then transformer architecture is very effective, as you can think about it. So with this we can check out the 46th question that says what are the steps that are involved in working with an LSTM network, long short-term networks, as we discussed in a couple of questions before. So whenever you're working with LSTM, there is three important steps that you have to think about. The first step is concerned with the network actually picking up all of the information where it has to remember certain things, it has to identify what it has to not remember and what it has to process as well. So that is the first step, where your network has the capability to know what it has to remember and what it has to forget. And then when we come to step number two is where we actually update all of the cell state values, but then updating all of these will depend directly on the outputs of the step one, because depending on what information needs to be remembered or not, the cell state values are updated based on that. The third step, in fact, also depends on step number two, because here what we're trying to do is getting the network to calculate and analyze what is the current state and which part of the current state should in fact make it to the output and which should not as well. So the most important step is step 3, but then without step 1 and step 2 it is very difficult to directly move on to 3, because you will need what is vital and what is not. Then you have to update the cell state values based on that, and lastly you have to make sure your network analyzes and calculates which part of the current state should make it to the output and which part should not as well. So these are the 3 steps that are very vital in the working of an LSTM network. Now we can come to the 47th question that states what are the elements in TensorFlow that are programmable. So what are the programmable elements whenever you're working with TensorFlow as a deep learning framework? So the answer is very simple. It is very straightforward. In TensorFlow, all the users have the ability to program 3 main elements. One are the constants, one are variables, and one are placeholder entities. So these 3 entities are very important that you state out explicitly, because these are the entities that you can program explicitly, program manually, and work with them depending on whatever model it is that you're working with as well. So after understanding this, we have to check out one more small concept called as bagging and boosting in deep learning. So the question can be, what is the meaning of bagging and what is the meaning of boosting in deep learning? So what happens in bagging is that, we actually take a data set, we split the data set, and we randomly shuffle around, move the data into multiple batches, or in fact we call it as bags since the term bagging is used, and we use it to train the model as well. And then boosting is a different scenario where we take incorrect data points and we force a model to actually produce a wrong output. We give it a wrong input, we make sure it gives the wrong output. So this way the model has the capability to understand that okay, this is wrong, and then it can retrain itself and increase accuracy as well. So this is a negative way of teaching the model, but then it works very, very well. If your model can understand what is wrong, that means that it knows what is right. So this way making use of bagging, where we're splitting the data set, or making use of boosting, where we are giving it the wrong input and the wrong output derived from it to teach it better. Both of these are helping very effectively in the case of working with deep learning as well. Now with this, we can come to the 49th question that states, what are GANs or generative adversarial networks as well? So GANs are again very widely used. They are used to achieve this concept called as generative modeling in deep learning. What it is that it is an unsupervised task that basically is involved in a lot of pattern detection and pattern hunting in the data. So whenever we have an input data, we try to see if we can find out any patterns in it and make sense of it and convert it into a meaningful output. So GANs are very useful for this. So the generative part of it comes from the generator, where it is used to generate more than one example at a time, while we have another entity called as the discriminator. A discriminator will classify the examples which get generated by the generator. So the two entities, generator and discriminator, and it would add some value to your candidature if you actually mention these explicitly to the interviewer as well. So GANs are again they're very widely used, because whenever you think about it, everything is pattern detection in today's world, right? So GANs have a lot of implementation and a lot of requirement by us as well. Now with this, we come to the last question that states, have you earned any sort of certification to improve your learning and implementation process? Well, the answer to this is very important, because as you might already know, a certification program can give you a lot of advantages. Structured method of learning, a lot of use cases, real-time projects, expert guidance, live classes, and to you this is fine. But then to the interviewer, what they are trying to understand from your certification program is, with the certification program, you are trying to show that you want to exceed in your career, that you want to build something, that you want to advance in your career. That is the first important point. The second important point is that, let's say if you're a fresher, if you learned it all on your own without having to learn it in college or something, that shows grit, that shows aspiration. And if you're a person who's moved from another programming language to come into the field of deep learning as well, that again shows very strong aspiration, that you are willing to put some time and effort, and that you've already put time, effort and money into learning all of these as well. And at the end of the day, that adds up to a concept where you're proving yourself to the interviewer that you are effective at what you do and you want to do this. So one very important thing that you have to know whenever you're talking about certification programs, right? So yes, you can list all the certification programs that you have had, but then what will add the most value is to tell the interviewer what you learned and how you used your learning to implement something new. See, because not just certification, any IT concept in the world, right? So we're trying to solve a complex problem using a simpler thing. So we're trying to make the complex problem very simple. So how have you taken a complex problem, how have you worked on it, and how have you simplified it by making use of your certification program is very important to the interviewer, and that is what you should talk about. Explain what you learned from it, explain how you learned and what you took away as well. And here is a small bonus for you guys. Apart from this, what would add a little more value is to make sure that you mention that that you're planning to use your learning in this particular way for that particular company that you're applying for, right? So you would have learned a lot of things. If you put it out in a way where you're telling the interviewer that, hey, I learned all of these and I think I can use it this way to help your company, that will impress the interviewer as well. So that is one very important way on how certifications will help you rapidly increase your career's dimensionality basically. Well, with that, you have reached the end of this top deep learning interview questions. I take this opportunity to wish you all the best for all the interviews ahead. So you make sure to use this guide to understand how you can approach the questions effectively and how you can answer them precisely and with as much content and quality as possible.
Okay guys, a quick info. If you're looking for an end-to-end training in artificial intelligence, Intellipaat provides a master's in artificial intelligence in collaboration with IBM, which covers everything you need to know about AI. So the details are available in the description box below.
So guys, we have come to the end of the session. If you have any doubts, please put down in the comment section below. We will try to answer it as soon as possible. Hope you all enjoyed the session. Thanks for watching.